Hi, everyone. Really great to see familiar and unfamiliar faces. Welcome to Encrypt. I'm David. I'm from D-Wallet Labs. And before we start, I want to say thank you to our co-hosts and sponsors, the MPC Foundation, Silence Laboratories, GSR, and Lightshift. Yeah, I won't take too much of our time. I want to kick off what I think will be a really, really interesting, heavily focused on research conference. And for our keynote, I am very happy to welcome Zvika Brakersky. Zvika is a professor at Weizmann Institute of Technology. Science, sorry. And he's also an advisor at D-Wallet Labs, and he'll talk about the history of FHE. And yeah, thank you, Zvika.
Hey. So I think I turned the mic on. Can you hear me? Excellent, good. And this is my clicker. Can you see this? No, you cannot, right? Okay, so there's no pointer, I think. Never mind, I'll manage. So hi, everyone. Yeah, so I'm Zvika, and so I'm going to talk about fully homomorphic encryption, or FHE. It's doing pretty well recently, which is a great thing. And I'm going to talk about how we got to this point and a little bit about where we go from here. So you may or may not know what fully homomorphic encryption is, but I certainly did not know until December of 2008. I was a first-year PhD student, and I went to my first cryptography event. So this was a workshop, cryptography workshop at Dagstuhl in Germany. And I actually, dug up from my email the preliminary schedule that they sent for this event. And on Wednesday, so it was a week-long workshop, and on Wednesday there was supposed to have been a talk by Craig Gentry. So Craig was recently graduated PhD student from Stanford. I did not know him at the time, but there was no title for the talk. It was to be announced. And later on, when after the workshop already started, they sent an update, and the updated title was Fully Homomorphic Encryption, which to me, I didn't know what that was. But people seemed to be pretty excited, like all the big names. Oh, there's a talk about fully homomorphic encryption. We have to go. Anyway, you go to the talk. This is what you do. You go to the talk. So I went to the talk. And sort of Craig Gentry really sort of laid it on us. There was a lot of new techniques and new ideas. And afterwards, in the coffee break, people were sort of trying to figure out whether these things work and whether they fit together. And so it was obvious that this was sort of going to open very interesting research avenues. Yeah, after the talks, everybody went to get beer. So yeah, this is me. And just by accident, I ended up sitting next to Craig and got this, to me, cool frame, photo frame, where Craig and I are in the frame. And also there was my friend Vinod Vaikuntanathan, who was just graduating from his PhD from MIT, and he's also going to play a role in the story that I'm about to tell. So we were kicking off at a good start. So this is where I heard of fully homomorphic encryption. But to tell you what it is, we need to go even further back in time. So 30 years further back, so almost a half century ago, in 1978, Rivest, Edelman, and Dertouzos published a paper called On Databanks and Privacy Homomorphisms, where they presented this idea, this notion of fully homomorphic encryption. So we used to think about fully homomorphic encryption as something that's kind of new, but people thought about it back in 78. And the motivation then was this notion of using mainframe computers. So back then, you couldn't if you just had a company, you couldn't afford your own computer necessarily, and you'd rent computer cycles from these big companies that had these mainframe machines. So you just have a dumb terminal that would be connected to this big mainframe computer. And then if you did your, I don't know, accounting or whatever of your company, you would do it on this third-party machine. And this raised privacy concerns because this was potentially sensitive information of your company, and it was being processed by a third party. So, the obvious idea was to encrypt it, but if you send encrypted information, if you encrypt the information, then send it to the mainframe computer, then how's it going to compute on it? So the cool idea of Rivest, Edelman, and Dertouzos was that this is actually not contradictory, that you can have both. So they proposed this idea of a fully homomorphic encryption scheme. And that's an encryption scheme that just has ordinary security. And it's a little bit funny that I'm saying it because back in the 70s, they didn't really know how to define security for encryption schemes in the way that we do today. The definitions that we use today only came up in the 80s. But it was, luckily enough, that was good enough. So they were saying, look, just whatever you want to require for your encryption scheme, you require it from this fully homomorphic encryption. But in addition, you want this additional property that if you have some encrypted input to some computation, so you have these M1 up to MK, so these are just, let's say, numbers that you want to compute on, and you have a function f that you want to actually compute on this information, then you can transform the encrypted input into an encrypted output without decrypting it all, so without violating the security of the encryption. So someone can actually perform this sort of translation from encrypted input to encrypted output without actually looking at the data. And they realized that this does not contradict the security of the encryption. So if you do this, then you can send your encrypted data to the mainframe computer. They would compute on it, send back the encrypted output, and then you'll decrypt it on your terminal and get the output. So this was sort of their idea of a solution. So they had this definition, but they couldn't achieve it. And it turns out it was a hard problem to construct fully homomorphic encryption. It was unsolved for a long time. Some people speculated that maybe it was even impossible to achieve. But then Gentry came and showed us that there is a way to do it. And Gentry's original solution, it has like a few different parts. The basic idea is to use these things called ideal lattices. So actually it turns out that it really depends on what kind of operations you want to perform. So if your function, if you just want to add two encrypted values, then people actually know how to do that. But if you want to both be able to add values and multiply, then things become hard. And if you can add and multiply, then you can actually do anything. So I'm just going to focus on multiplication, and we'll just remember at the back of our minds that addition is something that you can do. So how do you create an encryption scheme where you can multiply values? So Gentry had these ideal lattices, they kind of look like polynomials. So you embed your message into a polynomial, and polynomials are things that you can add and multiply in a meaningful way. But you had to find like an ideal lattice that is going to have good structure that can be used for this type of construction. And that was an exhaustive computational process. You had to sample multiple times from this distribution and hope that you're going to get a good ideal lattice that you can use as a secret key and public key for your scheme. So the key generation was like a very exhaustive process. In addition, these ciphertexts for this scheme had this property that's going to sort of stay with us for the entire development of fully homomorphic encryption. There's a noise component in the ciphertext. So this noise is just something that keeps growing as you perform homomorphic operations. And if the noise grows too much beyond like the noise capacity of your scheme, then the ciphertext becomes useless. So Gentry offered a way to do addition and multiplication, but you can only do it so many times before the ciphertext becomes useless. So you can do a few operations, but not everything. And so this was the first component, like a basic scheme. And then he introduced a second component, which is called bootstrapping. So if you read a little bit about fully homomorphic encryption, you probably heard the word bootstrapping. And bootstrapping is a technique for noise reduction. It requires additional computational assumptions, but that's not the point. The thing is that in order for bootstrapping to work, you actually need the basic scheme to have like a sufficiently simple decryption. So the ability to perform bootstrapping actually depends on the complexity of the decryption of the original scheme. So this is like a game of trying to come up with a basic scheme that has simple enough decryption so that you can bootstrap it. And actually, in Gentry's original idea, it didn't work. So Gentry tells the story that he started telling people that he had a fully homomorphic encryption scheme. And then he sort of did the calculations more precisely and figured out that there's like a little gap still between like what he can achieve in the basic scheme and what you need for bootstrapping. But he was already committed because he told people that he knew how to solve it. So he had to think like really hard what to do. And he came up with an additional trick called squashing that sort of made these things sort of closer together so that you can use both of them. Luckily, we realized with time how to get rid of it. So I'm not going to get into it too much. So this was sort of Gentry's sort of breakthrough scheme, and following that, there were other schemes that sort of used a similar blueprint. But with time, Vinod Vaidyanathan and myself sort of realized how you can simplify things quite greatly. And instead of working with these ideal lattices, to work with sort of more standard cryptographic problems, in particular something known as learning with errors, or LWE. And there's a variant called ring learning with errors, or ring LWE. And these are sort of standard types of problems that are, at that point, were used in cryptography. Let me tell you a little bit how to use them in order to simplify fully homomorphic encryption. So this is going to be a little bit of a technical slide, but I'm hoping to sort of introduce some of the terminology that you're going to encounter if you read about fully homomorphic encryption. So hopefully it's going to be worthwhile. So the first thing that we did was to construct this scheme that was based on ring LWE, and we used this method called tensoring. So what we did was to apply these sort of very useful scientific techniques. One of them is called wishful thinking, and the other one is called like squinting really hard. So you combine these. So what do we do? So we were sort of hoping to be able to get a ciphertext that looks like a multiplication of two things. And what we did was to look at the decryption. What happens when you take like an ordinary encryption scheme, not homomorphic, that is based on, let's say, ring LWE, and just look at the structure of these things. And what happens when you decrypt a scheme like that is that you take the ciphertext, and you take your secret key, and you multiply them together. And this more or less gives you the message. More or less because there's this noise that I was talking about, but let's squint and put that on the side, okay? So it's a product of two things. And these two things, the ciphertext and the secret key, are both vectors. So multiplying them means to apply like an inner product. But again, whatever, like, it's just a product to us. And now what we want, again, is to figure out a way to look at a product of two messages and try to write them as a multiplication of something that depends on ciphertext times something that depends on secret key. And hopefully, if you can write it in this way, then you will get like a ciphertext that encrypts the product of two messages. So we have this equation from above that sort of m approximately equals c times s. And now if we have two ciphertexts, c1 and c2, that encrypt two messages, m1 and m2, then we can just sort of plug in the equations. And we get that m1 times m2 is more or less c1 times s times c2 times s. And now, as I said, I want to sort of put all the things that depend on c on one side and all the things that depends on s on the other side. And again, we're going to squint and pretend that we don't have vectors. But if we just had like numbers, c1 times s times c2 times s, then this is actually equal to c1 times c2 times s squared, right? So we can just like, sort of reorganize. And turns out that you can do the same thing with vectors. Instead of the ordinary product, you get like a tensor product or outer product, whatever. So like a big name. But you can sort of put all the C things on one end and all the S things on the other end. And then you get this, like the C1 tensor C2, in some sense looks like an ugly version of an encryption of M1 times M2. So this is sort of in the direction of what we want. We get something that we can compute just given C1 and C2. We get the two ciphertexts, and we get something that corresponds to the product. And when you decrypt it, you do something with the key, and you can decrypt it. So this is sort of what we want. But this is like an ugly ciphertext in the sense that this tensor product actually blows up the dimension of the vector. So if you started with a vector of dimension 1,000, then you're going to end up with a vector of dimension 1,000,000. So that's not so good. But back then, we were thinking about ring LWE. And ring LWE, you start with vectors that have a pretty low dimension. So you can still do a few operations like this before things get stuck. So this was sort of our original idea. And it already sort of makes a big difference in making the key generation really trivial. Because I told you that the encryption is just going to be identical to the encryption of a non-homomorphic scheme. So you don't have to sort of work hard to generate keys and to sort of come up with the right ideal addresses and so forth. You can just sort of use the structure that is already sort of known. And this sort of removed the big hurdle from Gentry's original scheme. But we still didn't like this sort of ugly ciphertext, and we tried to make it better. And what we noticed that if you take, so we want to take like an ugly ciphertext that looks like a tensor of two things, and convert it into a ciphertext that's just like sort of single vector, that just looks like something that you need to multiply with a secret key. And it turns out that you can do it. That if you take a ciphertext that is decryptable using S squared, and you have on the side some side information that is just the encryption of S squared under your original key S. So I can give you this, because this is just like, this is something that depends on the key, but it's encrypted. So at least intuitively, it should be OK to give this to the evaluator, to the person who's not supposed to know what's inside. And this would allow you to actually convert ciphertext with respect to S squared into ciphertext with respect to S. So this is a technique sort of known as key switching. And again, this is something that you're going to see in the literature now. And this was supposed to take ugly ciphertext and make them into nice-looking ciphertext. It didn't work just as I described it. You need a little bit to tweak with it a little bit. Let me not get into more details. But this is sort of more or less the idea. And this means that now the sort of like the syntax of the ciphertext looks OK. But there's still going to be noise buildup. The noise buildup here is going to be very similar to what happens in Gentry's original scheme. So we had like a similar problem of sort of taking the basic scheme and the bootstrapping and make them sort of work together. The second thing that we noticed here is that if you take, so remember, the problem with bootstrapping is the complexity of decryption. We want to make decryption easier. And what we noticed is that if you take like a ciphertext of this basic scheme and you try to decrypt it, actually you don't need all the bits. You can actually sort of remove a lot of the bits of the ciphertext and still get something that can be decrypted. And this is now called module switching. And just because you removed a lot of the bits, you also simplified the decryption process. And this actually allowed you to put the basic scheme and the bootstrapping together without needing squashing. And that was sort of a big achievement, because now you can just rely on this learning with errors or ring learning with errors. You didn't need any additional assumptions, and you can get fully homomorphic encryption. So obviously, we were very happy. But stuff's getting real now, right? Because we're getting a scheme that's built on like a standard cryptographic assumption, and maybe people are actually going to want to use it. This is not like Gentry's previous thing that was kind of like a fantasy land. This is like a concrete thing. So people are continuing to think about like how to do things more efficiently. And then at some point, Gentry sort of very shortly after came to us and says, "Look, guys, essentially said to us, look, guys, you're doing this module switching all wrong. At least this is what I got. Like, this is what I would say to myself. You guys are doing module switching all wrong." So the way that we were doing this was that we performed a lot of homomorphic operations. We got like this big annoying ciphertext, and then we did module switching to make it like more compact. But actually, the right thing to do is after every operation to remove the bits that are unnecessary. So after every step, after every computational step, you remove the unnecessary bits and you keep going. And that actually makes like a huge difference in terms of the way the noise grows. So in this BGV type schemes, the noise is going to grow much more mildly than it did in like the previous BV schemes. So if you want, let me try to illustrate. So you have this black container, which is sort of the noise capacity, like the number of bits that you have for the message and the noise. So the message and the noise sort of live in the same space, and they're not supposed to take too many bits. If they take too many bits, then the ciphertext becomes undecryptable. So in the original scheme, the blue part sort of represents bits that are taken by the message, and the orange part is bits that are taken by the noise. And when you multiply two of these ciphertexts in the previous scheme, like the number of bits that you need for the message is the same, but the number of bits that you need for the noise actually doubles. So this is what happens in the BV scheme, whereas in the BGV scheme, if you start from the same inputs, what you're going to get is that the magnitude of the noise remains the same, but the noise capacity, you look at the size of the container, that actually shrinks. And you might think that it shouldn't make a difference because like here you have more noise and more space, and here you have like a smaller amount of noise and smaller amount of space. But turns out if you do it multiple times, it does make a difference. And this BGV actually helps you save a lot. In addition, in this BGV paper, we also introduced this technique called batching. So this is again something that you may hear about when you or read when you look at FHE literature. So I told you that these ciphertexts for fully homomorphic encryption are pretty big. But what we realized is that you can actually embed more information into like one of these big ciphertexts. You can actually sort of encrypt more than one message at a time. So if you care about amortized performance, then this BGV scheme can actually give you much more throughput than sort of the previous schemes just by encrypting more things and doing things in parallel. So this was actually sort of bringing things into a regime where people could actually start to implement and maybe think, well, maybe for some applications you can actually do it. And there were a lot of papers that sort of focused on trying to optimize and make things actually realizable in this for this scheme. But I was kind of lying to you by saying that I said, well, you might think that I wasn't lying, but I was not in peace with what I said before, that actually there is a difference between like big noise and a lot of noise capacity versus small noise and smaller noise capacity. It doesn't make sense. It didn't make sense to me. It works. Of course, this is correct, but somehow if there's justice in the world, right, then there should be a scheme where it doesn't matter, where like the absolute value of the noise and noise capacity shouldn't matter. Only the ratio should matter. So I was trying to think about it, and turns out there is a way to do it. Essentially, you need to reorganize things. You store your message sort of on the most significant bit of your container, of your noise capacity, and the noise goes in the least significant bit. And then if you do things right, when you do the multiplication, like the noise grows, but it grows sort of outside of the container. So you get performance that is similar to what you get in BGV, but without the need to do the module switching. So you stay with the same modules throughout. And So this scheme was based on learning with errors, and then there was an adaptation by Fan and Vercateran based on ring LWE with a lot of useful optimizations. And this is also sometimes implemented. Now it's called BFV sometimes. So this is, again, another sort of way to try to do homomorphic encryption in a way that is sort of actually usable, practical. I don't know. Yeah, so this is sort of some steps that were taken along the way. The next thing that I want to mention is the scheme by Gentry, Sahai, and Waters. This is like called approximate eigenvalue method. This is what I call it, at least. And they were suggesting something pretty interesting. So I told you before that for LWE and ring LWE, your ciphertext is a vector. And they were saying, let's just use a matrix instead of a vector. So this matrix does not help you to store more information. So you're still using the same amount of information, but you're just using bigger ciphertext. So instead of a vector, it's going to be like, instead of thinking about your ciphertext as one LWE encryption, you think about it as a bunch of those things, and they form a matrix. And then you can do homomorphic evaluation using sort of matrix multiplication, some version of matrix multiplication. And yeah, so in some sense, if you want to think about these diagrams, in the GSW scheme, somehow the information about the message is sort of spread throughout because you have a lot of these vectors. So in each one of these vectors, your message is represented slightly differently. So in some sense, the information about the message is smudged throughout this sort of noise regime, and your noise is still sort of stuck in the beginning. So at least, hopefully, it gives you maybe some vague picture of sort of how things behave in the scheme. And it's not immediately clear what it's good for. So in the original paper, they tried to rationalize some things, but it was like a new idea, and it was very interesting. And it turns out that even practically, it had very interesting consequences. So it turns out that if you think about bootstrapping as done in this GSW manner, then you can actually get very efficient implementations or even certain practical-ish implementations of the bootstrapping technique if you add some additional optimizations on top of it. And this led the schemes like FHE and TFHE down the line, which sort of add a whole family of optimizations in order to make bootstrapping more efficient using the GSW method. So I think maybe a lot of people, maybe in this community, heard about TFHE, for example, but I think it's less known that this is sort of an optimized version of a GSW style scheme. So there's the whole family that lives there, and the TFHE people sort of really did a really great work in taking this sort of very theoretical thing and making it practical. I should say that for theory of cryptography, the GSW scheme is extremely important, both in terms of the asymptotic analysis for noise, for fully homomorphic encryption. If you care about a theory thing, what is the polynomial that describes the noise growth and so forth, then you can do things with this scheme that you could not do with previous schemes. And actually, you can use, this actually started a line of works that created a framework for a large number of cryptographic objects that we don't know how to get in any other way. Things like attribute-based encryption, program obfuscation of sorts, traitor tracing schemes. So these things are still not at the practical regime, but who knows, maybe in 10 years, we're going to have a talk about that. So for theory, these things are extremely important. Another scheme that I want to mention is the FHE over the reals. So we're already at 2017, and the CKKS scheme noticed something that's, again, really cool and interesting. So we kept saying that we wanted to, let's say, add and multiply ciphertext and so on, but we always said that the output needs to be really the correct value. And they noticed that in many cases, if you think about sort of real-valued systems like machine learning algorithms and so on, the least significant bits of the output don't matter that much. So it's OK if the least significant bits are missing, or if they're dirty, or if it's not exactly what they're supposed to be. And then they devised a scheme. Again, I'm using my sort of schematic description here, where when you do a multiplication between two values, your sort of the least significant bits of your output actually sort of dip into the noise. So the noise is actually going to sort of interrupt with the least significant bit of the output. But if you're OK with that, then it gives you it allows you to perform functions that are sort of over the sort of real value. You can think about them as being over the real valued field. And again, this has direct applications like for machine learning algorithms, but also you can think about, so you want to do so I told you the bootstrapping depends on the complexity of the decryption. So now you can try to sort of characterize your decryption in terms of a real valued function, and this can also lead to efficiency gains. So that's another sort of great idea that now people are trying to use for various applications. So these were like a few ways to sort of implement this basic idea of a fully homomorphic encryption scheme that takes an encrypted input. There's a public key, there's a secret key. You encrypt with the public key, maybe you do some evaluation, and then you decrypt with a secret key. Now, people are trying to think, what happens if there's multiple users? So what happens in a setting where you have a bunch of users, each one has their own input, and you want, again, to privately compute some joint function of all of these inputs. And somehow, if you want to use standard homomorphic encryption, then everybody would have to agree on a public key and encrypt their data with respect to this public key. So you can try to do this. So this is one approach. But people were also thinking about this thing called multi-key fully homomorphic encryption. So this is sort of trying to do things in an even more decentralized way. So in multi-key fully homomorphic encryption, each party doesn't even need to know that the other parties exist. They just generate their own secret key and public key. And then they can use their individual public key to encrypt their input. So everybody can know the public keys, of course, like third parties can also encrypt with respect to my public key. But there's going to be a bunch of public keys that are living in the system, and everybody's allowed to encrypt with respect to the public key that they prefer. And you still want to be able to combine, to perform homomorphic evaluations on all of these different messages where each one is potentially encrypted under a different public key. So this is called multi-key fully homomorphic encryption. And turns out that you can do it. You pay, again, in sort of in the asymptotic performance. So you take like a bunch of encryptions and a bunch of public keys, and you can do homomorphic evaluations. You can come up, homomorphic evaluation. You can come up with an encryption of like the function f on all of the inputs. But now, in order to be able to decrypt it, you need to have all of the secret keys that are associated with the parties whose public keys you used, right? Because it's like a function of encryptions, each one under a different public key. So if you want to decrypt the outcome, you need all of the secret keys. So what do? Either you run one of those secure multi-party computation protocols, and sort of each party with their own secret key in order to compute the decryption, or there's a method, it's called threshold multi-key FHE, where this can be done in certain schemes just using a single message. So every party uses their own secret key. They look at this like sort of big ciphertext that depends on everybody's public keys and secret key, apply some local operation with their secret key, send it out, and then there's a way to combine everything and get a decryption of the message that you wanted. So this is multi-key FHE. There's still some questions about even asymptotic efficiency of this type of primitive. So we have all these great ideas. I said efficiency improvements and so on. But now it's, someone needs to write the code, right? So we get to the point where people say, OK, like you convinced us. This is a good idea. Let's try to write the code and see how it performs. And here, sort of, if you do anything that has to do with programming or fully homomorphic encryption and so forth, then this guy should be your hero. So Shai Halevi did this really pioneering work from the get-go on implementing fully homomorphic encryption. Even from the days of sort of Gentry's original scheme, he had this code of implementation and some challenges for the key generation and so forth. And sort of he and others kept working to create HElib, which was the first software library for fully homomorphic encryption. And I think to date, this is sort of one of the most prominent software libraries in existence for this. And HElib is an implementation of the BGV scheme with a lot of optimization. So like obviously there's a lot of ideas that need to go in order to take this sort of very theoretical thing and make it into something that you actually can use. And there's a sequence of papers and a sequence of ideas, and also a lot of very insightful tricks that are not written in any paper that you need to look at the code in order to understand that go into this software library. So like really amazing work. And this sort of paved the way to many other software libraries. So there's a few examples here. Probably by now there are more that I'm not even aware of. Maybe you guys are writing your own thing under the hood, and we'll all know it in a while. But yeah, so people are actually implementing fully homomorphic encryption. That's great. So yeah, so here we are. This is now. This is the mirror. This is you guys, right? Yeah, so it's happening. It's happening. So fully homomorphic encryption is actually becoming a thing in the world. We have these workshops and online resources and libraries and compilers and hardware designs that's sort of targeted towards homomorphic encryption, and for-profit and non-for-profit and government organizations trying to sort of figure out how to implement and use these things, all these collaborations, even standardization efforts trying to come up with a standard for using fully homomorphic encryption. So there's really like sort of a burst of activity for a few years that sort of keeps growing, and that's really, really great. So thanks. And this brings up like sort of a bit of a sort of sign of caution. So we're trying to sort of argue that fully homomorphic encryption is a great thing. And we want to promote this idea and make people sort of realize that they can use it for various things. But we don't want to create misconceptions. Because FHE is so amazing, it's very easy for non-experts to be convinced that it's actually going to solve all of their privacy concerns without needing to do anything. So whatever, I have an application and it's not privacy preserving, so I'm just going to put patch homomorphic encryption on it, and it's going to become privacy preserving. And this is not the case. So while we want to make FHE more accessible, we should make the users aware of where it can and cannot be used. So again, many times you need to think before you apply fully homomorphic encryption, or I guess any cryptographic solution. But here it's sort of very easy to convince yourself of things that are not actually happening. So for example, right, we know that fully homomorphic encryption takes an encrypted input and allows you, again, without violating the privacy, you don't know anything, and you can still convert it into an encrypted output. But this only brings you to the point where you have an encrypted output. If you actually want to get the output and use it, then you actually need to use the secret key in order to decrypt. So someone needs to have the secret key. And with respect to this entity that holds the secret key, there's no privacy at all. So like this whole process that you did, I'm going to do it homomorphically and so forth, this is completely transparent to the party that has the secret key. So you need to think a little bit whether it's okay that you're actually not hiding anything from like an entity in your system. Another example, even if you did everything correctly and sort of managed to do the decryption the way that you wanted and you got the output, it's possible in some computations that the output itself actually contains private information that you don't want to reveal. And in this case, fully homomorphic encryption is not the right tool to use, right? Like if you're doing like running a big machine learning algorithm on a huge number of huge data set, and just like inside, and you derive a model from it or something. I hope I'm not saying like embarrassing words. You derive the model. If inside the model somewhere it is written like some private data of one of the users in your data set, then it doesn't matter at all that you did the whole thing privately. In the end, you're going to release the output, and that's going to violate your privacy. So you need to be careful. That's what I'm saying. It's not like the only tool for privacy, and it's not going to necessarily solve all of your privacy concerns. And yeah, there are even like sort of actual papers that show that in some cases, like if you're not careful, then you can actually get like security faults if you're misusing FHE. In particular, if you're doing things that depend on the key. Like whenever you use the key, you should be careful. Okay, good. So this is sort of where we are. We want to use homomorphic encryption properly. Let's try to take a short look into the future. What do we want? What do we want to achieve? So to begin with, I started by saying, we had all these great theory ideas and we solved everything, and we all get prizes and drink cocktails and everything is great. But are we really done? Are there other additional theory questions that need to be resolved? And there still are. So you shouldn't think that theory of fully homomorphic encryption is completely solved. Even if you only care about like this asymptotic notion where polynomial times equals efficient, and you don't really care about sort of concrete parameters, there are still questions that need to be solved, and there's even bounties. So Vinod has offered bounties to solve some of these questions. Essentially, there's really one family of methods that we know to construct fully homomorphic encryption. You have these noisy vectors, and you put them together in some ways, and the noise grows, and then you need to suppress the noise. And it would be good to sort of realize what we can do in order to break free from this paradigm. So these are theory questions. Of course, like if we're talking about implementation, so if we're happy with the state of things in theory and we want to sort of think about implementations, then of course there's also another set of challenges. So you can think about them as practical challenges, but there are also sort of theoretical questions underlying there. And you want to actually get concrete efficiency, right? Polynomial time is not good enough. We want to actually be able to run things. And the question is, what is the overhead of doing things homomorphically compared to doing them sort of in the plane, so without any encryption? So what we want is to compare the complexity of, let's say, doing a multiplication using homomorphic encryption to just taking like unencrypted values and multiplying them. And again, in theory, we can do like pretty well in theory terms. You can actually get a scheme that whose amortized overhead is only polylogarithmic in your security parameter, whatever that means. So somehow this looks really good if you're talking to a theorist, but the concrete performance is still sort of unsatisfactory. So we're still sort of struggling to bring down the overhead that we pay to perform operations homomorphically compared to just doing them sort of completely unencrypted, just saying, look, I trust you, just take my data, do the computation, give it to me back. So this is one big challenge. I should say that if we're just thinking about the communication overhead, so I was talking about like the amount of computation that you need in order to perform some operations, but you can also talk about the communication, like how many bits of encrypted data do I need to send you in order to send like a specific message. So you can think about the communication overhead for fully homomorphic encryption. And for that, again, sort of from the theory side, we had some pretty good solutions already from a few years ago, where you can get the overhead to be close to 1. So the number of bits that you need, the number of encrypted bits that you need to send is not much larger than the number of unencrypted bits. So again, that's good in theory, but this again only works if you're doing like a lot of amortization, so a lot of batching. You need to batch a lot of messages. And if you want to actually do homomorphic operations afterwards, you need to like unpack this batching. So this helps like to transport things from one point to the other, but we still don't have a good solution that also allows you to do the computation without blowing up the data too much. So there's the cost in computation, but also the cost in like the amount of storage that you need. And if you thought that was bad, the ciphertext or the data overhead of the ciphertext is big, but if you're looking at these keys, so I kind of glossed over the fact that you have a public key, and I said in the beginning, there's this additional side information, which is the encryption of S squared under S and so forth. So there's like a bunch of stuff, like a bunch of side information that you need in order to perform the homomorphic evaluation. We call this evaluation key at some point. And that's really huge. That's bigger than a ciphertext. And again, sort of the way that we were thinking about in the beginning, it's like, look, it's polynomial in the size of your security parameter, so you should be happy. It shouldn't be very big. But actually, so first of all, they're really big. Even just storing them, I think sometimes is a problem. But the bigger problem is not just storage, is that you actually need to compute on them all the time. Whenever you do a homomorphic evaluation, you need to actually access this evaluation key and sort of, I guess, bring it into your CPU, do stuff on it, and so forth. And as far as I understand, one of the big problems is even like the data bus that you have in and out of your processor is just can't handle the load of actually sort of swapping in and out these keys. So some people think about sort of trying to deal with it in hardware, or you can try to sort of improve, I guess the better solution is to just improve the way that we represent and use these keys. So that's like still a challenge in terms of the concrete efficiency of homomorphic encryption. So these are things that are sort of, I guess, actively being studied. Maybe also some people here are thinking about these problems. We can even think about going sort of beyond this. So I told you like a minute ago that I'm comparing how much it costs to do a multiplication homomorphically versus the amount of computation that you want in order to do a multiplication sort of in the clear. But what if you want to do operations that are not in this sort of, this implicitly assumes that you're using a circuit model. I told you that we know how to do addition and we know how to do a multiplication, which means that you need to break your computation into a sequence of addition and multiplication operations. So for example, if you want to do like a branch operation, they need to translate it into addition and multiplication. And that's pretty expensive. So let's think about like a very simple task. You have a database, like an encrypted database, and you also have an encrypted data chunk. So you want to insert value x into location I, and everything is encrypted. All the orange thing is encrypted. If you want to represent it as a circuit, your circuit is actually going to be as big as your entire database. So the way that we want to think about it, the way that I was describing things before, what you want is to compare the homomorphic evaluation of this thing into taking things in the clear, like into taking the plain data, and just running this huge circuit that's as big as the database. But that's probably not the right comparison, because that's not how like we actually do things sort of when we program things. So in general, sort of branching operations are like really expensive in homomorphic encryption. Yeah, it's actually lucky that we managed to do anything at all, right? These things are pretty important, and even though like FHE kind of sucks at them, we still managed to implement kind of a lot of things homomorphically. And sort of like a lot of algorithms that you would use sort of when you design a processor, for example, like pipelining, conditional execution, and so forth, you just cannot do if you have this encrypted data, because again, you're sort of restricted to this circuit model. And this was sort of one of my sort of favorite questions from the beginning. Like, this is a conceptual thing that you want to do differently. Like, what can you hope for? Can you get like fully homomorphic encryption that is comparable to the sort of random access memory complexity of your computation? So, for example, for this computation that's described here, you want to compare it against like a unit complexity, right? The amount of complexity that it takes to take an unencrypted database and an unencrypted data point and just inserting it into the database. That should be 1, right? So we want something that's going to be comparable in this model. And for many years, there's no like even direction on how to do it. But very, very recently, there's like this extremely interesting breakthrough by Lim, Mook, and Wicks. And they actually showed that using ring LWE, you could get fully homomorphic encryption in the random access memory model. So this is super interesting, so it's very new, and people are still trying to understand the properties of this solution. So for example, it has some oddities that we don't have in other homomorphic encryption schemes. Like for example, we know how to do it based on ring LWE, but not based on non-ring, on the sort of plain LWE assumption. And this is something that bugs us in terms of understanding, because for all other schemes, we have like ring LWE is used for efficiency, but you can also do things with plain LWE if you want. Here, this is not the case. And in terms of concrete efficiency, again, so people are saying, oh, it's completely impractical. There's like huge constants. It's very, very far from practicality. But we know that we shouldn't be deterred by these sort of things. So people just need to continue to think about it and see whether there's more that we can do in order to sort of use these techniques and sort of make better schemes and maybe even sort of implement these ideas into the way that we do things. So yeah, so I guess the final question is are we there yet? So is it possible, are we already at the point where we can build like production level systems where FHE actually brings value? So we see in principle it's a great tool, but can we actually sort of get value out of it? Yeah, I don't know the answer yet. I guess that's for all of us to find out. So I'll just leave you at that. So thank you.
Thank you so much, Zvika. If anyone has a quick question from the crowd, I'm happy to take a question. And if not, we can move to the next talk. Great. Thank you so much, Zvika.
Yeah, thanks.
Appreciate it.
Thanks, guys.
Great. So our next talk is from my co-founder, Jonathan. And he's going to introduce some of the exciting research we've been doing at the Wallet Lab. So, Jonathan, thanks.
Okay, my mic on or no? Yeah? Okay, so I'm super excited to be here. Especially the lineup is incredible, so I'm happy and excited privileged to speak next to all these amazing cryptographers. Today I'm going to talk about 2PC MPC, which is a research that we did in DeWallet Labs. We attempted to solve a problem that is at the heart of interoperability and security of Web3. And for that, we needed to actually do some breakthroughs in the normal cryptography theory behind it. All right, so let's start. So I'm Yonatan. I did my Math BSc during the high school, so I finished at the age of 19. Later, I served 5 years in Matzov, which is Israel's national cryptography and cybersecurity unit. I was in the cybersecurity side. I was doing like low-level kernel, embedded systems kind of things. But we have people like Deliver, VP Research, FHE that was in the unit with me on the more cryptographic side. Later, I was doing some hacking. I did Android kernel hacking for about 3 years, and I got to do it remotely, so I traveled the world while doing that, and it was fucking incredible. And I got to the next stage, which was I wanted to come back, do some startup. Took me some time, but after a year, we came up with this idea kind of independently, and then later we merged. So now we're doing this, DeWallet Labs. I'm not going to talk about this. Let's just talk about what we're going to do today. It's not going to be a very use case kind of presentation. I'm going to talk about cryptography mostly, and I'm going to talk about the problems that we have to solve first, and later I'm going to talk about how we solve them and the actual stats and optimizations that we can do. And I'm going to tease you about what we're going to do in the future or what we want to do in the future. So our basic problem is to decentralize ECDSA signatures. And that I'm not sure that it even signifies something when I'm saying that, but let's talk about what were our problems when we talk about decentralizing ECDSA signatures. So the first one is it's a tricky one. It's not the obvious one when you think about this problem. It's actually the maintenance problem. So the maintenance problem is about how do you manage and store keys when you have a permissionless network that hosts decentralized wallets. So if you have a bridge and you have a few like vaults, so you have like just a few keys, I think you can manage storing them independently, where each validator has a key shares and they just hold the key shares. But if you have a permissionless network whose objective is to onboard most of the wallets in Web3 now and in the future to use this infrastructure as their security backend, so you're going to have millions and millions of wallets to deal with. And that could be very hard to maintain. And it's even harder when you think about it being a permissionless network in which the validators change. So you have parties changing in every epoch. And you need to have not only the keys available, but actually usable. And that's going to be hard. I'm going to speak about that very soon. Some problems that I care about, but I don't know if other people care about. Communication in almost all threshold ECDSA, or actually all practical threshold ECDSA signature schemes before 2PC MPC, was P2P communications. Whereas theoretically, a blockchain only allows for a broadcast channel. So I would want a broadcast-based protocol. Now, scalability, throughput, latency was just not even close to what we needed. If we want thousands of parties computing thousands of transactions per second, whereas the state-of-the-art identifiable protocol was doing maybe 20 parties in maybe minutes for a transaction, for a single transaction, then we were very far off from where we needed to be. And lastly, I think, is this idea of involving the user. So we want this to be a completely non-custodial wallet. And for that, we need the user to be cryptographically required for the process of generating signatures. And when we want to do that, we call this, first of all, non-collusiveness. So that's this idea of the network cannot collude and actually steal assets. And when we do this, we actually want the user to not be burdened by the size of the network. As I said, it's going to be a permissionless network. We want it to be as big as possible, so security be as big as possible and as decentralized as possible. But we want the user to not experience that. So this idea of locality means user is O of 1. It's constant in both communication and computation. And we want to achieve all of that while keeping identifiability. So let's start with the maintenance problem, because that was actually quite surprisingly the first problem we tried to solve. At first, we were kind of optimistic. We saw, it's a T out of N protocol when you look at the CGGMP, and we thought, so actually you can just plug in whatever T and N you want. It turned out not to be that way, but we found that out rather late. In any case, we started from the maintenance problem. The maintenance problem, for me, is hard because if you have this network that holds various keys, right, and each validator needs to keep key share for every one of those keys, then the amount of key shares that every validator needs to keep private is O of M, where M is the number of keys. Now, what happens when we have some kind of validator change? Then we need to do a reshare. This is a cryptographic operation in which you keep the same private key. So if you go to the previous slide, you'll see that the keys remain the same in the orange. But what happens is the key shares that every validator holds, they will change. So that the sum will still be the same, the sharing is still the same, but the actual shares are different. And this is an expensive operation. It takes at least O of N or O of N squared for every key. So you'd have an operation that is dependent both on number of keys and in the number of wallets that you need to do in every epoch, which could be as little as 24 hours. That is completely infeasible. Now, what happens if we involve the user? Now, if we involve the user, then actually we would need the user to be involved in this operation as well. So if you have 1 million users, 1 million keys, and you need every 24 hours each of the users to be active, unless if they don't do it, they lose access to their wallet. That's not possible. The solution we came up with was to use a threshold additively homomorphic encryption scheme in such a way that the actual key, the private information that the validator holds, is a decryption key. It's not the signing key. And we use this property where for AHEs, the encryption scheme is homomorphic. So you can have two messages, you sum them up in the encryption of them, and you get the encrypted of the sum. And we use that in order to actually have just one threshold decryption key shared. That's the one in orange in the middle. You have every validator have just one share, this one share. And then we save the signing keys, or at least the network share of the signing keys, encrypted under this key in the state. So now we have many D-wallets. We have one key that every validator needs to change. And better even, one key that they need to reshare. So on the DKG of CGGMP that we started by wanting to adopt, every party also sent their encryption of their share, right? And then you sum them all up, because the encryption is homomorphic, you can do that. And you get just a single encryption of the network side of the signing key of the ECDSA signature. Then in sign, you could apply threshold decryption over the signing key plus some random nonce R. And you would reach a sharing of the private key, and you could use that for signing. So now we have as many wallets as you want in the state, We don't need to maintain each and every one of them. We don't need to save backups. We don't need to refresh each and every one of them independently. And we can change the validator sets as we wish, while still just maintaining this one decryption key. And the actual security of each and every one of the signing keys, the access structure is derived from the access structure of the decryption. We had another problem. There were no practical threshold AHE schemes at the time. After that, there were works. I think most notably is one work about threshold class groups. So this is an assumption that I'm not sure everyone wants to take because it's not as research as standard. But that was also published after we did our work. But we wanted to use a standard one. So we worked on Tiresias, which is a large-scale, it's maliciously secure threshold palier. And we managed to do pretty scalable things. So we managed to do decryptions in under a second. So that's your sub-second latency for the decryption, with up to 1,000 parties. And with Tiresias, we can actually adapt to solve the maintenance problem of CGMP. But we still have the scalability problems. We still have the communication problems because CGMP was P2P based. But we did manage to adapt CGMP to solve non-collusiveness. And we didn't solve locality. So that was the point in which we thought, OK, great success? No. It's not great success because it's not scalable enough. And we want something that could actually be the infrastructure for custody in Web3. And for that, we need something that will be much more scalable. And we asked the question, can we use Tiresias, which has the promise of being this scalable, because we show that we can do decryptions under a second with up to 1,000 parties. And I'm wanting to ask, can we use that to do a threshold ECDSA protocol? There was a work by GGN that was published in 2016 that actually did threshold ECDSA based on threshold additively homomorphic encryptions. I didn't mention it before, but I'm talking about additively homomorphic encryptions, where Zvika was talking about fully homomorphic encryptions. Additively homomorphic encryptions are a weaker, simpler building block. And we show that you can use that. Of course, you could use FHEs for what I'm speaking about, but that could be costly, right? And this work by GGN16, it was even before the first practical threshold ECDSA work that was published by Lindell in 2017. And Lindell's was 2PC, and this one is multi-party. So you ask the question, why is it not famous? And the answer was there was no threshold AHE at the time that was practical, and they relied on trusted dealers. But we'll get there. Let's just have a look about how the protocol goes through, because we are basing ourselves on this protocol, and we extend it. So the DKG, the distributed key generation for this protocol, is kind of like our adaptation to CGMP. So you take every party samples key share, and they broadcast the encryption under the threshold decryption key of this key share. And you sum all up, because it's homomorphic, you get the encryption of the key. And a small recap about an ECDSA signature. It's actually based on kind of two secret things. And you have the key, and you have the nonce. And the thing about ECDSA is that you have an inverted nonce, which is a problem with MPC. But the signature, you don't need to remember this formula, is just based on these two public things, which is the generator G and the message M, and these two secret things, which is X and K, the key and the nonce. And the easy part is to reach, there's two parts in the signature. You have R equals K inverse times G, and you have S tag, which is also includes the key. The easy part is to reach K times G. That is because k times g is actually a homomorphism also. So what you can do is each party can just sample their nonce share, and they publish their nonce share times g, so that's ki times g. And you can sum everything up to get k times g. That's very easy. By the way, the idea is that you cannot reach from k times g to k because of the discrete log assumption, so you can broadcast all of these things. The tricky part, of course, is multiplication and inversion. In MPC, that's always the tricky part in these kind of schemes. But we show that using threshold AHEs, you can do that quite easily. So how do you multiply the secrets? First of all, you take an encryption of one of the secrets. And then what you do is you multiply that secret by a scalar, because you are the party with the secret. You can multiply that locally. And what you get is you get an encryption of your secret share by the total secret. So you have E of x, which is the whole secret key. And you take your nonce share, you multiply that locally, you get an encryption of the secret times the nonce share. And this you can broadcast because it's encrypted, and you can sum it all up because it's homomorphic, and you get an encryption of the nonce by the secret key. And how do you invert in MPC? You use a mask. So you sample a single, use random mask in symmetric encryptions. They call it one-time pads. And you encrypt this, you multiply this, right? So if you multiply this, you get an encryption of a masked nonce, right? You get gamma, which is the mask, and k, which is the nonce. And because it's masked, you can actually decrypt that. And now you have this in plane. Because it's in plane, you can think of it as a scalar, and you can do local operations with that. So you can reveal that, and you can invert that. Inverting gamma times k is like having the multiplication of the inverted gamma and k. And you multiply that by the encryption of gamma, which is the mask, and you reach the encryption of the inverted nonce. So there was a little bit of mathematics here that was not super important if you didn't get it. But the idea is that using threshold AHEs, we can reach all of these factors, the inverted nonce, the secret key, and the message, and the random, and R, which is the first part of the signature. And you can build an encrypted signature from that. And now comes the only threshold decryption part that you need. OK, in GGN16 you needed two, but for us, I'll show you later how you can do it just with one decryption. And then you just decrypt the signature, and you get the signature, right? OK, this was the semi-honest variant of GGN16. Malicious security requires actually using zero-knowledge proofs to actually show that every step along the way follows the honest protocol. That was the problem with GGN16, which was they didn't really have these zero-knowledge proofs that were practical. They required using safe primes, which is just impossible to generate in MPC unless you want to kind of wait the lifetime of the universe. But you could do it if you're willing to trust some dealer. We are not willing to trust some dealer because we are trying to do a decentralized solution. So we had to come up with these zero-knowledge proofs to fix this. Let's do a small recap about zero-knowledge proofs. So this is completely independent of what I talked before. So if you lost me along the way, please come back. The simplest zero-knowledge proof is Schnorr's knowledge of discrete log. What you want to do is actually you have this x times g, right? That's a public. You can think about it like a public key. For ECDSA, that's a public key. And you want to show that you know the witness, x. If I send you x times g, you don't know. It just looks like a random kind of point. You don't know what it is. And I want to prove you that I know what the secret is. So the protocol looks kind of like this. The prover can sample some randomizer, k. and they send you the public value of that k times j. And the verifier can sample some challenge. The prover can do some formula that is a combination of the randomizer and its witness. And the verifier can actually verify that you had to know X in order to do this. And using kind of a generalization of Schnorr, we designed a novel, batchable, aggregatable, zero-knowledge proof system that enables malicious security for GGN16, so no trusted dealer is required. But our proof system is an enhanced version of this. It's enhanced, first of all, it's an enhanced version of Maurer proof, which is a generalization of Schnorr proofs that works for any homomorphism, because Schnorr was just for this knowledge of discrete log. So you have any homomorphism phi in which you can plug in two numbers, A and A tag, and you can sum them up under phi. And Schnorr is just one where phi of x is x times g. And Maurer proofs are a generalization of Schnorr proofs. They work kind of the same thing. They just use the homomorphism as the formula instead of the hard-coded x times j. And we use enhanced Maurer proofs, which add range claims to the language. And that's the novelty that we have, is that we wanted to add range claims to the language. So it's no longer a strict homomorphism because of these range claims. But why do you need them? First of all, encryption schemes like Palier are working in a different group than the elliptic curve group that you're going to do the signature. So we want to work over the integers. Now, thankfully, Palier encryption works in a much, much bigger group than the CDSA group, so you have some space to play around with. But you need to prove that you never went through modulation so that you actually are emulating working over the integers. And for that, you need range claims. You also need range claims if you want to work with RLWE-based encryptions, like Zvika described before. That is because the noise needs to be small. So you need to actually prove the noise is small. If you don't do that, you might leak the key. So how does this work? There's a very simple trick in enhanced Maurer proofs, is that we are using a range proof and a Maurer proof, and we add to the Maurer language the commitment over the message for which we use the actual language that we want to wrap with another range claims. So there's some code here, but you can see that the witness space group element for us, the witness of this language, the enhanced language, is always going to be composed of a message of a commitment scheme, a randomness of a commitment scheme, and some unbounded witness that you can use for a language. And it always maps onto the statement, which is the commitment of the commitment scheme, and the statement of the language that you want to wrap by adding range claims. And the idea here is this commitment scheme, this commitment is going to match the range proof commitment over which you are proving the range. And the homomorphism is pretty simple. You can take this message of the commitment space, and you just transform this by composing the message of the range proof onto the witness of the language. So if you'd think about it, I'll show you soon, but if you'd think about it that you have some range proof that you don't know how it works internally, in the end, it just proves range claims on a lot of numbers. If you could take these numbers and using some formula, transform that into, for example, the witness X, which is the secret key for the ECDSA signature, then you can show that using this witness, later you do the homomorphism of the inner language, and you show that it's the same witness that was proven range claims on. I won't go into much more details here, but basically from this you compose the language witness. From that, you compose the language statement. And you add the language statement to the range proof commitment over the same message. And this is enhanced malware proofs. So you have a proof that's compounded by a malware proof and a range proof. And you verify both of them. And the trick is you verify both of them on the same statement, the same commitment. So then you have this parity where you show that they're linked. There is some other trick that I'm not going to describe that you need to kind of verify that the response of the malware proof does not go through some kind of range, does not go over this range. But I'm not going to describe it, but that's just more of a mathematical trick you needed to add. And using these enhanced malware proofs, we can actually remove the trusted dealer assumptions. So let's give one short example of this kind of language. Is that you have this encryption of discrete log language in which you want to say, here is X, this is my witness, and I want to give you an encryption of this witness and a public key that corresponds to this witness, and I want to show you that it's the same witness used for both. So you know X times G, you know E of X, and you want to know that they match, right? This is the encryption of discrete language. And now the idea is that we want to make it more complicated by saying that X is actually a part of this elliptic group. So you have Q, the order of the group, and you want X to be smaller than that and bigger than 0. So that's your range claim. The encryption of discrete log language just takes the plaintext space of the encryption, so that's a message, and the randomness, and it maps onto the ciphertext and the group element, right, the encryption, and G times X. I'm not going to go into this. But using all of these building blocks, we actually managed to transform GGN16 using Terry CSR threshold Palier and using enhanced malware proofs into a 3-round protocol that actually is broadcast only. It's identifiable. It's large scale. So what's left to solve? I'm sorry, I had a lot of problems. So we solved maintenance, right? We solved it early on. Now everything is broadcast-based because of the encryption scheme, which makes all the message public. All the messages are public, and we have zero-knowledge proof, so it's identifiable. It's scalable because our encryption scheme, our threshold encryption scheme, is scalable. And what's left for me to show is actually we can reach this non-collusiveness and locality features that's by the access structure of 2PC MPC. So that's what I want to talk about next. And the throughput and latency I'll leave for later on. If we want the user to be required for an MPC operation, we want the network to never be able to perform a signature without the user. How can we do that? The very naive solution is to have the user be the same number of players like the network is, right? If you have 100 players in the network, so you're going to say the user is 100 players. It's going to keep 100 secrets, and it's going to do 100 operations in every signing operation. That's very, very expensive, right? Like, that's infeasible. Especially when you think about like the network is going to be like a lot of like very computationally high servers, and the user is just like a web browser. So what we introduced is this notion of 2PC MPC. This notion, I think, is beautiful because you have the network emulates in MPC a two-party player. So if you have a two-party protocol that does ECDSA, one of the parties is going to be a decentralized network with thousands of validators, but the other party is just going to be a user with a web browser, and he doesn't know how big the network is. He doesn't know anything. He just thinks he's talking to one person. Lindell 17, as I said before, is one very good 2PC protocol for ECDSA, and it's relatively simple. I'm not going to describe it now, but what I'm going to say is that there you have, if we're going to take P2, the second player, and we want to distribute that, we see we have two secrets, right? The nonce share and we have the secret key share. And we want to distribute them. Now, I think if you distribute them, but all the messages of the protocol are still going to be the same, then you have the witness X, the secret key of the ECDSA signature, being X1 plus X2. So the user is going to be required in every signature, right? Because the other party just can't do it without it. And the user still receives one message every time and one proof every time. So if we can get that, it still has locality. And it still has non-collusiveness. And how can we imagine doing such a thing? Well, I think it could be imaginable that we do the same tricks that we did before to do a multi-party signature in order to do all of the computations, right? Because they all involve like multiplying and inverting things in MPC. We already know how to do that, right? I think the harder problem is how do you prove one proof over all of these things that you did in MPC and it still corresponds to the statements that you want to prove. And for that, we use proof aggregation. So Maurer proofs are linear. As you see, you have K plus CA. There's no multiplication. It's very easy to aggregate them in multi-party computations. And therefore, Maurer proofs are aggregatable. And then if your range proof is aggregatable, and hence Maurer proofs are aggregatable, I'm not going to describe how exactly they're aggregatable. But the idea is that if you take an aggregatable proof scheme and you use proof aggregation in every place that every party used to send a proof, you can have a two-party computation emulated by a multi-party party. And that could actually solve both non-collusiveness and locality. And it does solve that. OK, lastly, let's talk about performance. I think that public protocols are pretty cool. Now, why I think that? Because there's a lot of optimizations and tricks you can do that you couldn't have done with unicast-based protocols. And I want to say that our protocol is practically O of 1, which should pose some, like, really, on your side. But yeah, let's say why. Well, the thing is, if all the messages are public, then all of the O of n computation is over public values. So you would think that maybe we have some kind of way to amortize this. And we do. The first thing that you could do is to amortize the threshold decryption. Now, I remember that I was very much obsessed with this problem. Like, this was the biggest bottleneck in our protocol, right? You had to do threshold decryption over n messages. In Palier, we use Shamir secret over the integers so that actually the secrets themselves are O of n. And then it makes it so much expensive. And I was very annoyed because I said every one of these players needs to do the exact same thing over the exact same values, get the same result, and they do it for no good reason. And I remember being in like this rock show, and I was thinking about this problem instead of dancing, or while I was dancing. And, and I was like, wait, but the encryption of Palier is deterministic once you know the randomness. And the randomness is not secret once you decrypt. So what if during the threshold decryption, we also recover the randomness, and then you have not only the message, but only also the randomness. So you take this encryption of M with randomness R, and you give to all the other parties both M and R, and then these other parties just need to encrypt M using R and see that it corresponds to the ciphertext that this party they don't trust said they decrypt. So apparently someone thought about it before, and there was a paper describing this. And this was a really cool idea, but it had its problem. First of all, it's just for Palier. It doesn't work for RWE schemes, for example, because the randomness or the noise needs to be kept somewhat private. Otherwise, you might leak the private key. And it adds communication rounds. Now, I'm going to talk about a different story. We have some friends here from that actually were the authors, or part of the authors of DKLS. And I attended the lecture of DKLS in Singapore with Dolev and Avishai. And I remember that they talk about this trick about how to reduce the round complexity. And they have this trick of how to form the signature of ECDSA in such a way. And actually, we thought about it. We walked down the moisty, beautiful jungles of Singapore, and we were obsessed about this problem. Can we make a free-round protocol? Can we make a free-round protocol? And what we turned out to find out is that we could. And the big thing about it is that now, instead of having 2 threshold decryption rounds, like in GGN16, you have just 1. And when you have just 1, it means you're decrypting a signature. And what's cool about the signature is the signature is verifiable. And that does not depend at all about the encryption scheme. So now we have a scheme that is completely generic in using every threshold homomorphic encryption scheme that is also amortized, because in the last stage, the very last round, you decrypt the signature, and then just one person decrypts, all the others verify it, and you have amortized all of 1. So that's the first thing. The second thing is that the proof aggregation, although it's asymptotically O of 1, it does much more lightweight operations, because the idea is, instead of doing n exponentiation when you do verification, so every verification is a very high complexity operation, or at least in computation it's very high weight, you do multiplications, or if you think about, I was talking additive notation before, so you have additions instead of multiplications. And actually, it turns out to be a big deal, because the base rate difference in computation is very high. It's orders of magnitude cheaper to do additions than multiplications. Depending on the group, it can be between 100x to 1000x improvement. So if you have 100 parties, you're practically O of 1. And that's the basic idea. And it can be shown in these graphs. The left one is for verification. The right one is for proof. And the dotted one is if you do have aggregation, and the straight lines are if you don't have aggregation. So obviously, if you do have aggregation, verification is constant because you verify one proof. And obviously, if you don't have proof aggregation, it's linear because you have to verify each of the proofs of every party. You're not going to get it for free. You're going to pay in proof. And the proof time, when you have verification, when you have aggregation, does increase linearly. But you see that the graph does not increase linearly from the get-go. It has this kind of curve where it takes a little bit of time to catch up before you actually feel the linearity. And that's why we say it's practically O of 1, because up to a certain number of parties, which is actually a pretty big number of parties, you feel like it's a constant operation. And now let's get to really asymptotically amortized O of 1. All this that I was just describing is completely public. Our protocol is publicly verifiable. You can take all of the public steps, push it, shove it into a snark, and then all the other parties just verify a snark, which is constant. Now, I don't want to do that actually in practice, because the snark's constant is going to be more expensive than everything I described before. But the idea is that actually you can get to asymptotically O of 1 using this trick, which is kind of naive, so naive that Dolev didn't want to put it in the paper even. But I thought it's cool to point it out. Some statistics. So I think that the idea here is that we are getting to even 1,000 parties, and we can manage to do that, right? We can manage to do that in seconds. Also in pre-signature, you can look this up later. But the idea here is that this is before parallelization, and you get a complete signature in 100 players by, I think, a few seconds. And 1,000 players, you get it like 100 seconds. If you parallelize it over 100 CPUs, you can get it in a second. So we got kind of to where we wanted. What's my conclusion? Well, first of all, public protocols are cool, right? Like you couldn't do all of these tricks before. And with Tiresias and 2PC MPC, like we actually show that malicious security, it can be achieved for free, and I'll show that very soon. But the idea is that 2PC MPC solves all of our problems. Okay, not really, but almost all of our problems. So theoretically, it solves all of our problems. Practically, we have a problem with the range proof. I'll talk about it just now. But it solves definitely the maintenance problem. The communication is completely broadcast. It reaches thousands of parties. It's non-collusive. It's local. It's identifiable. It's actually even publicly verifiable, which I didn't even know what it means before we achieved it. But we have throughput and latency problems a little bit. Why? Let's talk about it soon. But the idea is that using all of this, we can actually imagine a massively decentralized network that offers non-collusive signing mechanisms. And this is going to be the wallet network. And the wallet network is going to, we want it to be, the infrastructure for access to all Web3. And you can use it for various interoperability, custody, onboarding solutions. And that's the basic idea. We're going to have in the wallet networks smart contracts from other networks that are going to dictate the logic to when the validators are going to sign. So you're going to be able to control signatures from any network that you want, like actually Ethereum mainnet, or Sui, or Aptos, or any other chain that you would like. What's our future work? Is to solve these two small problems, not that small. But let's show why I'm very optimistic and I say that 2PC MPC actually solved all our problems. The reason is this is a logarithmic scale, and we show what takes the most in computation in our protocol. And the green is bulletproof, as you can see, because it's a logarithmic scale. It's not like we do this after this after this. Like the green is all of this. So bulletproofs is by far the most expensive thing in our protocol. Bulletproof is the range proof that we used. And without that, if we think that we don't have bulletproof, malicious security is free because malware proofs, we call it Schnorr here, is completely, you don't even see it here. And here is still negligible next to the statement computation. So if we don't have range proofs, we get malicious security for free. And I think we showed this with Tiresias before, and we show this with 2PC MPC now. And I want to claim that you want to go there, you want to aim there whenever you are doing a practical MPC protocol in real life. You want malicious security for free, and I think you can get it most of the time for free. So we need a new aggregator range proof. That's my future work. I would say a caveat here that if you use class group-based encryptions, which is a different assumption that I don't trust as much as I trust Palier, so we chose not to use it. But if you use it, then you don't have range proofs. You don't have range proofs. You don't have bulletproofs. You only have compute statements. That was going to be your bottleneck. And the idea is that right now, we can have all of the problems solved if we trust class group encryptions, because the compute statement phase is very, very fast. The bottleneck in statement computation is the encryption. And Palier encryption, for example, takes 20, 30 milliseconds. You have a few of those, maybe 3 or 4 in the protocol. So you can have sub-second MPC operations right now for free if you don't have the range proofs. But we do want to use Palier, so that's our next mission. We're working on it. We have some promising leads, but let's see. And that's it. I just want to say thank you. It was really I enjoyed talking here. And all of this is open source. It's released. The paper is out. The code is out. We are in testnet. You can look it up. And that's it.
Thank you so much, Jonathan. Let's take a 15-minute coffee break and come back to hear Benny Pincus. Thank you, everyone. Breaks are always tough. We need to regroup. So I'm very, very happy to welcome Benny Pincus to the stage. Benny is, I think, one of the most prominent figures in the MPC space. And we're very happy to have him with us. And he's going to talk about his super interesting work in Aptos. Yeah, I'll let Benny take the stage.
Hi, everyone. I'm happy to be talking here. I'll be talking on joint work with Surav Das, Aline Tomescu, and Zulun Daniel Siang from Aptos Labs on distributed randomness generation using verified VRFs. This is work we've been doing in Aptos, and it's going to be deployed very soon. So this is like a non-corporate slide explaining Aptos, what the Aptos network is doing. It's a layer 1 blockchain. It publishes blocks of transactions about each block every 1 second. So we achieve transaction finality in 1 second. There are more than 100 validators that achieve consensus on every block. They are located all over the world, and each second they achieve a consensus. The way they achieve it is that token owners, they can stake the tokens at specific validators. And validators that have more than 1/3 of, so the consensus ensures that validators with less than 1/3 of the total stake tokens cannot break the security of the consensus. So the assumption is that the bad guys cannot control more than 1/3 of the stake tokens. So if I look at an image from the Aptos Explorer last week, we had 129 nodes all over the world. The amount of staked tokens were about 880 million out of something like 1 billion tokens that are available. And this was epoch 6140, which is important because every epoch, which is something like 2 hours, the stake might change. So new validators might join, others might leave, and the power of each validator might change based on how many tokens are staked on that validator. So this is what I said earlier about 1/3 of the stake. It might change because the delegation of stake to validators changes every 2 hours. So as of last week, there were about 880 million tokens staked. The stake distribution changes every 2 hours. And the amount of stake per validator varies very dramatically. Some of them, very few of them, have about 20 million tokens. A lot of them have about 1 million tokens. So there's like a ratio of 1 to 15, 1 to 20 between the smallest validator and the largest one. This is like the only corporate slide I have. The network should run very, very quickly. We have a block every 1 second. In a recent test, it supported more than 2 billion transactions in 24 hours, which is more than 25,000 transactions per second. This is like 13 times faster than what the network of Visa is doing per day. And this was sustained over a full day. And we cannot break this performance. We have to work with it. So this talk is about generating randomness. Why do you need randomness? So the obvious first example is games. So you can think of backgammon or games like that. But even people who play like action games, kids or other gamers, they want to be sure that the randomness they get, like the boss that plays against them, goes right or left. This is like true randomness. No one is cheating them. So this is actually very important for gamers. And you can think about dice or dungeons or Dragons and Dungeons, etc., things like this. There are other applications like NFT minting, airdrops, selecting leaders for consensus, MEV, protection against MEV, etc., that require randomness. And people want to make sure that the randomness is indeed honestly generated. There's another application I like to talk about, and it's about improving the Fiat-Shamir transformation in cryptography. So what's the Fiat-Shamir transformation? So there are Sigma protocols to prove all kinds of things, like proving the knowledge of discrete logs or equality of discrete logs. And they follow this pattern of a prover and a verifier. The prover sends a commitment, the verifier sends a challenge, and then the prover answers. And there are lots of examples of these protocols. And then the initial protocol, the description is interactive, but to make it not interactive, you use the Fiat-Shamir transformation, which basically says this challenge going from the verifier to the prover, compute it as a hash of the commitment that the prover sent, actually of all of the messages that the prover sent before that, the challenge should be a hash of that, of all the transcript that the prover generated. And then this makes the entire proof non-interactive, just a single message from the prover to the verifier. So this is great, and actually most proof systems, definitely on the blockchain, they use this Fiat-Shamir transformation. The problem is that in practice, this Fiat-Shamir transformation is very error-prone. There's this paper by people from Trail of Bits and other companies that do audits, and they keep finding bugs in how Fiat-Shamir is implemented. Usually, what you take into the hash function is not all the messages that the prover sent before, and this enables you to completely break the proof. Okay? So that's very bad. So something you can do with on-chain randomness, so the prover can post the first commitment on the block. It doesn't need to compute the hash, because computing the hash is error-prone. I mean, and people keep doing these mistakes when computing the hash. It can wait for the randomness that will be published on the block immediately afterwards, which will take something like 1 second, and then it can post the answer in the next block. So the proof will be non-interactive. It will just take 2 blocks, okay? And the fact it waits for the randomness that is posted on the chain after posting the commitment makes sure that the prover cannot choose the randomness to work with the initial message that is sent, okay? And so this kind of might solve the problems in implementing Fiat-Shamir. And also, it prevents the prover from doing a brute force attack looking for randomness that will make enable it to cheat. So in some cases where a longer challenge means a longer proof, this can actually lets the prover send much shorter proof. So what we want to implement is essentially a verifiable random function, a VRF, which is a well-known primitive in cryptography. The random output should be unpredictable. No one can predict it. And it should also be verifiable, so everyone can verify that it's indeed a true random output. That we couldn't just publish a certain value like 17 and tell you that's the output that was given. You should be able, it was computed based like the initial key that was set at, when the system was set up. Now, there are external randomness sources that blockchains are using, like DRAND or Chainlink have a VRF. So blockchains can use randomness from external sources. And the question is, why do we need to generate randomness on-chain? So there are several reasons. One is trust. We don't want to trust an external source, both for secrecy, but also for availability. We don't want if, say, DRAND or Chainlink have an outage, then our network will also have an outage with respect to randomness. Another one is latency. So DRAND, for instance, they generate an output every 30 seconds, okay? We have a block every 1 second. Maybe in the future we'll have a different latency. We don't have to wait for DRAND. Suppose that you're playing a game on Aptos, you don't want to wait for 30 seconds till you know what's the next move is. And another reason is how hard it is to write programs. If you write applications and you wait for external randomness, basically the application needs to commit to a future time in which the randomness will be generated, because otherwise it's already known. And then at that future time, it should fetch the randomness. So it's a 2-transaction process, which is much harder to program than just getting random output. So what we achieve is that the blockchain validators of the same blockchain, they first agree on an ordered set of transactions for the coming block. Then they generate randomness for that block, but after agreeing on the order. And then the applications in that block can generate the randomness immediately, and anyone can verify it. So using the randomness is just, like simple programming language. You don't have to commit your future time. You just write a, you wait range. You consume a random value in a certain range. So it should be very simple. So this is what we implement. Now, the way to implement it usually is using a threshold verifiable random function. So the first thing is for the validators to run a DKG, a distributed key generation protocol, to set up the keys for the VRF. And then each validator gets a share or many shares, depending on its weight, its stake, to computing the VRF. Then every block, the validators collaboratively compute the VRF. And to compute it, we need a certain threshold of the shares. And computing the VRF usually is done through intermediate change of computing a verifiable unpredictable function, which you cannot predict. It might not be completely random, but you cannot predict it. Maybe some bits are fixed, which is essentially equivalent to a signature. And then after you compute this verifiable unpredictable function, VRF, you apply to it a hash function that is modeled as a random oracle. And then you get a VRF. And this is what we're doing, what essentially I think most of the applications are doing, of usages of VRFs are doing. So the construction will use bilinear pairing. So just a reminder what a bilinear pairing is. So you have cyclic groups like G, G hat, GT. And a symmetric pairing takes two items from G and maps them to GT. And the property is that if you map G to the A and G to the B, you get the mapping of G and G raised to the power of A and B. Excuse me for being quick. If someone didn't know about pairings beforehand, you won't learn it from this slide. If you know, it might remind you. But you won't be, you can spend half an hour, an entire course learning about them. And an asymmetric pairing takes an item from G, an item from G hat, the blue and red, and maps them to G, GT. Again, satisfying that if you apply it to G to the A and G hat B, you get the pairing of G and G hat raised to the power of AB. And the security of our construction will be based on the bilinear Diffie-Hellman assumption, which means if you have G, G to the A, G to the B, G to the C in G, and the same powers in G hat, you cannot compute the pairing of G and G hat to the power of ABC. Okay? That's a known assumption, a very basic assumption in these groups. So I'll describe how VRFs usually work, and then I'll mention why it's not so simple to implement, because initially it looked simple. So the first thing is to do the DKG, and for that, each participant, each validator shares a secret. So the sharing must be verifiable. We use what's called the Feldman verifiable secret sharing. Each dealer generates a polynomial for Shamir secret sharing, polynomial of degree t. It broadcasts the powers of the coefficients of the polynomial, g to the s, g to the a1, up to g to the at. And then it secretly sends to each participant the value of the polynomial. Participant j gets the value of polynomial at location j. And each participant can verify that indeed what it got here, g to the, q of j, if it raises g to that power, it matches what it can compute with the powers of the coefficients. Again, if it's the first time you see it, you won't be able to get it. If you've seen it 100 times, it seems familiar. So, and this is what they do. And if the participant, if he gets a share and this equation doesn't match, then it complains. So this is simple. We learn about it, but it's not so simple to implement. So the first thing is that we assume here that the dealer broadcasts this coefficient of the polynomial. For distributed key generation, we're going to have many dealers. So all of them have to broadcast something. And the degree of the polynomial will be a few hundreds. Okay? So if we have like 100 dealers, each one of them broadcasting a few hundred items in a group, okay, it's going to become very large. Okay? So we don't like it. And the other thing is that if a participant receives a share, it does this check, and the check fails, it has to complain. And then others have to decide, whom to agree with the participant or agree with the dealer. And this is also broadcast. And this is like quite complicated to implement. So we don't want this phase of complaining that the participant has to complain. That's very inconvenient to implement and to do it correctly. Once we have this PVSS, what people usually do is a distributed key generation using Peterson DKG, which basically says each participant shares a secret, as I said before, using this PVSS. Then we see who complained against whom, and then we decide who was not working properly. Then each participant sums the shares it receives from those who were not cheating. And then we have a sharing of a secret, which is the sum of all the shares that were sent from participants which were valid and were not cheating. So this is nice on paper. Again, the problem here is if you want to implement it, if someone receives a bad share, he has to complain. If he complains, others have to decide whether the complaint was correct or not, whether it was justified. Then they have to decide whom to blame, and then they have to sum the shares of those who did not cheat, and this is quite complicated. And then to compute the final output, suppose you use BLS signatures. If you were working in a non-threshold setting, then you had a private key X and a public key Y, which is G to the X. Then what you would compute is age of M, hash of the message, raised to the power of X. And you check the signature using pairing. In a threshold setting, what you will like to do is each participant takes age of M, raises it to the power of its own share of X. X is the private key. And everyone can verify that this is correct using a pairing. And then you combine everything using interpolation in the exponent, and you get the right output. So this is what people usually do. And again, you have a problem here because you're going to get T shares. T is a few hundreds. You have to verify each one of them using a pairing, which is quite inefficient. So this doesn't scale very nicely if T is large. And remember, we have to do these things every second, and we cannot wait a second to compute this. It has to be much faster. So this, I asked GPT to generate me an image of threshold verifiable random function. This is what I got. So there are some problems in addition to what I said before. Our validators are not like that. Each one of them has a different weight. They're not right next to whoever needs to see the output. They're all over the world, so communication might not be very fast. The weight changes every epoch, so every 2 hours we have to change the weight of different validators, and the function must be very fast. Okay, one issue, and I still don't get into the mathematics, is who should run the DKG. So this is also from GPT. These are the validators of the first epoch, and this is the epoch next to it. So every 2 hours, we have the change from one set to the next set. So the reasonable thing is that for the validators of the new set to run the DKG and agree on a key. Okay? That's not very good because doing the DKG might take a few seconds. So this means that the new epoch will not be able to generate randomness in the first blocks that it has, and this is unacceptable. So instead what we do is that the validators of the previous set, they do a DKG and generate the shares for the new set. They can do it maybe 10, 20 seconds before the epoch ends when they know who are going to be the validators in the next epoch. And so they share the keys, and then they also publish the verification key to verify the randomness. Okay, so to do the DKG, each validator shares a secret. The secret, the way it's being shared, we don't want this complaining game that everyone checks the share it receives. If it's not good, it complains. Instead, the sharing will be publicly verifiable, meaning that everyone can check that everyone got a good share. Okay, so to verify the secret sharing, you don't have to blame. I can verify that another participant, Alice, got the right share. So this simplifies the way they have to interact. And the new key is the sum of the secrets shared by validators who sent a good PVSS, and everyone can identify this. The new key should be shared by validators who own at least 1/3 of the stake, and everyone can identify these validators. About identifying whose share to take, so the common implementation of DKG does something like this. These are the validators of the previous set. Each one of them does a PVSS and broadcasts the result. And we use some ordered broadcasts, which we have on chain. That can be on a block. So we have the PVSS messages from everyone. All of them, we publish them on the block. And then each of the validators of the new epoch takes, say, the first PVSSs in this ordered block is the same order that everyone sees, that have a weight greater than some threshold W, and it takes its share from them. So that's the obvious thing to do. However, it's too costly because each PVSS is going to have a few hundred items multiplied by a small constant of, say, 4. You have 100 validators here. It's going to be a lot of items. It might not even fit on a single block. And broadcasting things is much more complicated than just sending a peer-to-peer transaction. So instead, what we do is that each validator sends the PVSS message using peer-to-peer messages to all other validators. So it's not a broadcast. We don't verify that all of them got the same message, but each one can verify that the messages it got are indeed a correct PVSS. Then one of the validators, could be the first one or any other one that we decide, aggregates all the messages it got. And it's important that it be able to aggregate PVSS messages from many validators and generate from them a single PVSS of the same length as only one of these PVSSs, and publish it, and then it broadcasts it. And everyone can verify that this is indeed the sum of PVSSs from validators with a weight at least W. And then it broadcasts only a single PVSS, and everyone can verify it. So to do this, the PVSS must be aggregatable, meaning that you take PVSS messages from many validators, you can combine them to a single message, which is like the length of about the same length of a single PVSS message, and it shares the sum of the secrets that they shared. And the only aggregatable PVSS that we could use is due to Gurkhan et al. And the problem is that it shares group elements rather than field elements. So what it shares is not a secret A, but a secret something like G to the A in a secret group, so we have to work with that. So this makes using it more complicated. But this aggregatability property is really important for us. So summing it up, we have the validators of the previous epoch. They do a DKG, which is aggregated to a single transcript, single PVSS transcript. This is broadcast. Every validator gets the private key from that published PVSS. And then for each new block, which is every second, they compute the VUF. And the nice thing is that computing the VUF takes messages of constant size. So this validator, if its weight is 1 or 20 or 50, it's always going to send the same length of messages, which is independent of the weight that it has. Okay, so one initial thing we have to do is moving from stake to shares. If we have 800 million tokens, which is the total stake, we don't want to use 800 million shares. It won't be scalable. So instead, we give a share for every B token. Say B is like 1 million or something like that. And the validator, we take its stake, we divide by B, and then we round to the closest integer. And we can analyze and show that the loss of accuracy there due to rounding is quite small. And we typically use something between 500 to 1,000 shares. Performance of cryptographic operations, the important thing to know is exponentiation. Exponentiating is fast. Multiplying many exponentiations makes the cost of his exponentiations even faster. Doing a pairing is slow. And there's like a 2 orders of magnitude difference between doing a pairing and the time of doing an amortized exponentiation. So instead of doing, say, 1,000 pairings, it's much better to do a single pairing and one multi-exponentiation of 1,000 items. You get like two orders of magnitude performance boost from that. So this is what we do. We want to minimize the number of pairings that we use. Okay, so the function we're going to use is something like that. So this h of m to the power of a, this is the well-known BLS signature, which is known to be secure. What we are using as the output is the pairing of h, some generator, and h m to the power of a, which if h of m to the a is pseudorandom, then this will also be pseudorandom or unpredictable. Yeah? And the way we're going to implement it is we're going to do a W out of capital, no, lower uppercase W VUF. You need small w shares out of w shares to compute the function. And the way we do it, the shares will be values of a polynomial. So validator 1 has W1 weight, so it's going to get W1 shares. And the shares are going to be in this format, powers of values of the polynomial. And the master key is the value of the polynomial at 0. And then we compute the function where each validator will send a single message. Can I be like 3 minutes longer? I'll try to. I can be 30 minutes longer, but I'll do it like 3 minutes longer. OK. So I'll just describe how the VUF works. So in the setup, we just generate two generators of the two groups, G and G hat. And as input, we get the weights of the validators. The validator 1 has weight W1. It should get W1 shares, etc. Now, suppose that like we have a central guy dealing the secrets. Of course, we shouldn't understand what's happening here just from this talk. But basically, he's doing a Shamir secret sharing, little w out of capital W secret sharing of a secret. And what the validator gets is its secret key is values of exponentiations of its weight number of values in the first group, and the public key is these values in the second group. And that's it. So the total number of shares is the total stake, which is quite large, something like 1,000, which is quite large, but we only do it when an epoch changes. Now, each validator should augment its private key, its public key, so others can verify that it's sending a good input to computing the VUF. So the important thing is that the validator picks a random value Ri, validator I, and then it publishes powers of its private key and also of h raised to the power of Ri. So if its private key here was h to A1, A2, etc., what it's going to take is going to take all of these values and raise them to the same power. Okay, and this doesn't give information. And then he's going to publish this information, and then others should verify that he published the right information here. So basically, okay, this should be the first component of its private key raised to the power of Ri. Also, we have here h to the raised to the power of Ri. The public key also had something raised to that value of this value of the polynomial, so you do a pairing to check this. Okay, we won't go into the math, you just do a single, one-time check with pairings to verify this. Now, the important thing is computing the VUF because this happens every second. So to compute its own share of computing the VUF, the validator takes the input m, its secret key, what it generated previously, Ri, and basically computes h to the m raised to the power of 1 over Ri. This is the only information it sends. And this is independent of its weight. Even if it has 20, 30 shares, it's only going to send a single item. Now, when we get this item, we need to verify that the validator sent us the right value, right? So remember in the previous slide, it published h to the power of Ri. Now it has to send us h of m to the power of 1 over Ri. We have to verify that these have the same exponent Ri in them. We can check this using a single pairing, which is quite standard. And then we need to compute the final output. Computing the final output, you take a subset T of validators whose total weight is at least the threshold that we need. And then you need to combine the values that they sent. So the first thing you do is you verify that they indeed sent you the correct values using the check I mentioned here. And say that this subset T, maybe it has like 20 validators, something like that in it. Then you have to verify, have to kind of work to generate the right output. So this is the augmented public key that the validator published. So it's basically each of its items of its private key raised to the power of Ri. And here you had age of m raised to the power of 1 over Ri. If you do a pairing, then you multiply things in the exponent. So this 1 over Ri here cancels with the Ri there. So basically what you get is the pairing of age and age of m raised to the power of the share of that validator. And then these things you can combine together using interpolation in the exponent. So this is basically what's done here. If you look at the math, this is what's done. And the nice thing is that you only send a single message. OK. So the setup cost depends on number of shares. But verifying a validator is order of 1, and computing the final output depends on the total number of validators that is used in the interpolation. Now, I won't go into the security. I won't go into the DKG because I'm quite close to the end. I talk about performance. Okay? So these are micro benchmarks. The red is ours. The part which is not colored is using threshold BLS signatures with the same threshold. The time it takes and the x-axis is how many shares you have. You see that the signing time in our scheme is constant. In BLS, it grows depending on the number of shares. Aggregation time, both in our scheme and BLS, depends on the number of shares, but it's smaller in our case. And the signature size in our case is smaller and is constant and much smaller than BLS. If you look at an end-to-end evaluation, then the DKG to do every 2 hours, including the agreement, takes you something like 20 seconds. Okay? This is about the number of shares that we use. And generating an on-chain value takes 160 milliseconds or so. And actually, we have it now running in PreviewNet, and performance on PreviewNet is even better than that. So we can do it every second, and it doesn't make the network wait at all. Right now, we're running a hackathon that different application developers are using this randomness to generate it, build cool apps with it. And we hope to have it running in the main network soon. And that's it.
Thank you so much, Benny. If anyone has a quick question, feel free. If not, we'll move to the next call. Thank you so much, Benny. Appreciate it. I'm really happy to introduce Jakob Pachter. I hope I did it the right Danish way. Jakob has he has over a decade of experience working with MPC-based key management. He's now the VP of MPC at Blockdaemon, right?
Yeah.
And he's here to talk to us about MPC management for wallets. Right?
Thank you. Yeah, so I used to work for a company called Sepia, which was acquired by Blockdaemon a year and a half ago, and we were allowed to choose our own titles, so I thought that one sounded kind of cool, so I went with that. Blockdaemon, this is a kind of less technical talk with a more maybe corporate stuff in it. So it's a blockchain company providing hosting of nodes, providing staking APIs, and basically the infrastructure that you need when you use different types of blockchain and cryptocurrencies. Since they acquired us, they added the wallet part as kind of the third leg in their wallet infrastructure business. They have a number of, or we have a number of investors, and we are working for a number of companies that use different types of solutions that we offer. Some of those are using the MPC-based key management system that we've been building. Yeah. Oh, I didn't know that was. I don't know. So anyway, so my name is Jakob, and thanks for all the care in trying to pronounce it correctly. I did my PhD at the University of Aarhus, and after that I worked for a place called the Alexander Institute, which is kind of like Fraunhofer in Germany or the MITRE in the US or something. It's like a private research organization, but it's kind of with an applied flavor. And we've been doing applied cryptography there for many years, working together with the cryptography group at the University of Aarhus. One of those infamous papers is the sugar beet auctions, which I'm pretty sure that everybody in MPC is fed up with hearing about now. But on the back of that, we actually founded the company Partitia. And then after a few years trying to commercialize MPC-based auctions, which was not a great success, we founded Sepia, which is basically using MPC, multi-party computation, to do key management. We had some ideas about how to leverage that for cloud-based security and other applications in the beginning. It turned out that we were a bunch of geeks that didn't know what the market wanted. And then the market came to us and said the market wants blockchain stuff. And so here we are. Another thing I had a small stake in is founding something called Partitia Blockchain, which is a level 1 blockchain for orchestrating MPC computations. In theory, you could take the work we did back in 2008 and then you could run it on this network. And this is something which is live now, and you can Google that and find more about it. And now, since 2 years ago, I've been working for Blockdaemon that acquired Sepia after we spent some years trying to build a business. I'll talk a bit about that, how we talk about MPC and some of the problems we see in MPC-based key management. So for us, when we communicate with people, we have kind of this MPC in a nutshell. So everybody here who worked in research in the area knows the millionaire's problem. And as you can see, I'm not sure any of these are the richest person. I don't know. They were 10 years ago when I made this slide. So the idea is here you can compute the value of any function. It's like FHE really, but in a kind of a different setup. You can compute a function without revealing anything about the input. And this gives you some very nice properties, and you have well-defined security models and assumptions and so on and so forth. And so this slide is really about communicating the core idea of being able to compute any function, and that it gives you, and I think a lot of the people we talk to, the interesting part here, right? When we talk to them about what is the security they get, it's the same type of security that they're used to. For instance, typically when you're doing ECDSA, it assumes that ECDSA is secure. It doesn't, necessarily throw all kinds of weird stuff into the box. Yeah, and then I'm not sure where this realization came from. Maybe it was some of the Unbound guys. But the idea basically is that you can view keys, cryptographic keys as secrets. You can secret share them, and then you can use MPC to do cryptographic operations. So it's really a simple and elegant idea. And then obviously you have these properties. For instance, if you're doing secret sharing, you're going to split it into a key into a number of shares n, and then you have a threshold t, so that you always any T players cannot reveal the secret or get access to the underlying key. And this is, this is confusing for people because people compare this to multisig, and it's always confusing. Is it T or is it T+1? So, but that's another matter. Yes, so that's threshold cryptography. That's what it is. I think NIST is also using this term now. They have this project about how to do MPC-based key management, and they're using the term threshold cryptography. So that's where I had that from. We have two products that realize this. The first thing is called the Builder Vault. It used to be called the TSM, so on this slide it's called the Builder Vault TSM, and this here shows its architecture. So basically, you have a number of MPC nodes, N. In most cases we work with, N is 2 or 3, and T is thus 1 or 2, depending on kind of the parameters. We do have one application where we are running one of our protocols, an honest majority protocol for ECDSA signing, with about 1,000 nodes. So it can scale. If you talk to our marketing guys, they will tell you this works for any choice of N and T. And as normally when we talk to the customers, it's more like, yeah, as long as N is 2 or 3 and T is kind of like, so it does scale to some extent, but there are a lot of details to be worried about. One of the things we also offer is the ability to have, in the beginning it was 1, but now it's really any number of the nodes can be running on a mobile device. And that has its own challenges in terms of the network connectivity, the timeouts, and all kinds of practical issues you get into when you have a protocol that will typically run over multiple rounds of communication. But it is something that works also with the ability to have a setup where you're only using mobile nodes to do the MPC protocols. One of the things we have done is that we have taken this architecture and then we've kind of shrink-wrapped it into something we call a policy authority. I'll get back to that shortly. But really this, in the end, this amount, there are a lot of moving parts here, but really the interesting part is over here where we have the MPC nodes, which will do key generation and signing for the different types of blockchains that this wallet architecture then integrates with. From our perspective, we have this box here. If you ignore the air gap stuff, it's a kind of a copy of that with some other properties. But we, in this box, we don't assume anything about the security of this thing over here, right? The wallet, it has addresses, it knows users, it knows all kinds of things. But in terms of security, all the keys are generated inside the box on the top right, and all signing happens inside there, so everything is under the threshold security policy. And even users, we have like third-party approvers with mobile devices, they also live in the same closed ecosystem, so that we're sure that there's not a single point of failure outside of this box. So based on that, the stuff we did with the Builder Vault and the stuff we've done with building our own wallet, we're kind of seeing some trends, and I think many of you will probably recognize these. It's not rocket science as such, but it is the actual problems that are out there, and the actual trends are kind of the hard nuggets when you're doing MPC-based key management, in particular for wallets. So the first one is policy enforcement. So a typical problem when people are building MPC-based or threshold security wallets is that they have this nice secret sharing of the private key. They're doing fully distributed signing and key generation and whatnot. And then they have a policy layer which is not under threshold, right? So you have a single point of failure outside the system. And then the MPC layer will effectively blindly sign anything you send to it, right? And so you kind of, in some sense, if you have an existing policy engine and you like that, it makes sense from a kind of practical security point of view, but from kind of a more purest point of view, it's no longer MPC security, right? Because you just need to compromise the policy engine. So what we have tried to do, and I'm following these trends because it's things that we're trying to put into our products now, but I'm sure a lot of things will evolve over time to give. We're trying to build even better solutions, and I'm sure others will try so too. But the idea is that the policy enforcement happens inside the actual MPC node holding the key share. So each MPC node holding a key share will also have its own view on the policy that's being evaluated. And that means that each MPC node in the system will need to know all the external approvers. If you have like a quorum with 2 out of 3 or some number of users that needs to approve a policy, then they need to be in the same ecosystem. On top of that, some of the things that you could do in our solution, we have the backend nodes that are on the threshold security. You could move it further out and have the quorum. If you have a set of approvers, you have these rules where you need 2 from this group or 3 from that group to approve a transaction. That you could do the MPC-based signing all the way out to those mobile devices or whatever, using generalized access structures or approaches like that. We have not seen a kind of a commercial pull for that type of solution, and I also think that from a practical perspective, maintaining replicated secret shares keys across a big number of users where there's some churn in the users who are using the system, this will be painful for our customers to operate. Another trend we see is cold wallets. So that's something which is a necessity for a number of regulated wallet providers. And what we see is that people want to have the same type of threshold security for their cold wallets as they do for their hot wallets or the warm wallets. So it means that you want to do MPC signing with nodes that are not able to communicate with each other. Maybe they're allowed to communicate with each other during key generation, maybe they're not. Some of the things that we're looking at is using stuff like partial signatures. You mentioned pre-signatures before, the fact that in ECGSA you can pre-compute a lot of the rounds, and then you don't need to do be online for the signatures to take place. This doesn't solve, you still need to bootstrap it, so you can, in our system, if you really want to, you can actually do a kind of a sneakernet key generation protocol if you have the time, in particular to educate the users who's actually going to do this, to do key generation in a way where they're manually using USB sticks or whatnot, carry messages back and forth between the different nodes. That's a possibility. I think what it turns out for us is that one of the big chunks is really making this system usable, right? So finding out what's the right trade-off between, or the classical trade-off between security and usability. Because if you want full threshold security, so what we typically do is that for key generation, it's acceptable for the nodes to be online on a closed local area network maybe. And then after that, you've generated a bunch of pre-signatures, and then you can do partial signatures after that. So stuff like that. Also key things like how do you ensure that you have proper backup of the keys which are distributed across a number of offline nodes and that type of thing. So there are good solutions to be found yet in this space. Another thing is HD wallets. So if you look at stuff like Bitcoin, something called BIP44, which means that you have this hierarchy of addresses to make it easy for a customer to publish addresses without reusing the same address all the time, and make it easy for them to find out which private key they need to access those coins. So what BIP44 is an instantiation of something called BIP32, which shows how to build this hierarchy. And when you're doing this derival from the kind of the master seed or the master private key, then you're doing derivation, which can be done in two ways. It can be done in what's called hard derivation, or you can use soft derivation. So the difference between those two things is that hard derivation is taking the private key as input to the hash function. So if you're doing MPC-based HD wallets using BIP44, it means that you need to do general purpose MPC because it's an asymmetric primitive, and I mean, at least I don't know any way that's more efficient than doing general purpose MPC. So that's slow. And typically it's too slow. Sometimes if you know that in BIP44 you do pre-generation for the top 3 layers, and if you know exactly which coins and blah, blah, blah you want to support, then you can pre-process that if you have time before you publish the wallet. But it's slow and it's costly. We're talking to customers that want to do this on mobile devices, and right now it simply doesn't work because it takes too long. And that's really how we started when we did the sugar beet stuff. It's like you sit down and then you do tricks and hacks and whatnot and try to figure out a way, can we do this better somehow? Can we maybe loosen if we have like a dishonest majority, can we maybe temporarily switch to an honest majority setup, or can we do something else, and what makes sense, and what can we communicate to our customers, what works, what's performant enough. So there's really a lot of stuff. I think, from a security point of view, we're completely happy with soft derivation, right? But customers, they have existing wallets they want to import, and they want to give their customers the ability to move to another provider if that becomes a problem. So it's not something we decide. So I'm thinking better solutions are required here as well. The fourth trend I want to talk about is trusted execution environments. And it's not something as an MPC software-based security person that I've been comfortable talking about. But I think maybe half of our customers, in particular those that come from traditional finance, one way or the other, they want hardware. They want, they want this. They're saying, do you support Amazon Nitro? Do you support SGX? Do you support AMD SEV or whatever? They want it. It's a check mark that they need for compliance and maybe also for practical security. So it's something you need to do. And the challenge from our point of view is really, Amazon, they have this Nitro platform, which they say you can just take anything and run it inside, and that's true. But if you do that, then you really don't get the full security. You need to do remote attestation and all kinds of things and make sure that the whole key management setup makes sense. So it's costly. And then you have customers that say, okay, now we want to run this on Google instead, so we want AMD SEV, and they have a different way of doing remote attestation, and the security model is slightly different. So, and then you talk to the marketing people, and then you really need to be careful about the statements you make and how you get this whole thing set up. So I think trusted execution environments is a benefit for compliance. It's a benefit for hardening as well. Let's not neglect that. But it's complicated. It complicates life. The nice, simple security assumptions that I was kind of brought up with from my time in academia, they no longer exist, right? Because there's so many practical things going on. The final thing, the final challenge, third-party validation. Software has errors. I think it's pretty common. We see that all the time. We try to do the best we can, but what we really have is that we have simple cryptographic primitives like ECDSA, EDSA, RSA, AES. And maybe AES is not that simple, but it's well understood. And then you build complex protocols to implement those rather than just implementing them, right? So you get something where it's a lot easier to make mistakes. And that it is what it is. You can do formal verification. You can do standard validation in frameworks. I'm not saying that actually improves security, but it gives your customers confidence that you know what you're doing. And it also checks off some compliance requirements. We're trying to get FIPS 140-3. And how can I put it? The fact that everything needs to happen within the same physical security boundary kind of makes the whole MPC model complicated in a FIPS world. We're doing third-party validation. We had NCC group a couple of times reviewing our implementation, really doing two things in parallel. One thing, checking up against the research papers, our own, others that we've implemented, that the software actually implements those correctly. And two, that our software does not have any traditional errors in terms of missing input validation or whatever it could be. The final thing, and something which is quite popular, is open sourcing. So we give it to the community, and the community ensures that the quality of the software is good. So I'm a big believer in that, but there's an assumption there needs to be an ecosystem, there needs to be a community that can actually do this, otherwise it doesn't work. For OpenSSL, stuff like that is great. For us, I don't think we can rely on that necessarily. You need to build an ecosystem, and that was not our take from the get-go. It's something that you can always discuss what is the right solution, for us at least. Yes. So what we're seeing is that everybody who's doing wallets, they want MPC. Some of them understand what it is. A lot of them understand that it can improve the security. And I think if you look at the wallets, I mean, today we had some very sophisticated protocols, but if you look at the MPC wallets out there, the kind of the basic problems are solved. You can do ECDSA and the other primitives that are relevant. And then I think what I've talked about is some of the more advanced features, and those are not advanced features for people who are used to using wallets. They're advanced features for people building MPC protocols, right? So, yeah, and what people are looking for when they're buying this type of product is that they want people who have the right pedigree, they want solid engineering, and they want compliance. So, yeah, there's no dark magic as such, but that's what I think is going on. Thank you.
Thank you very much, Jakob. If anyone has any quick questions, or if not, oh yeah.
Thank you so much. I'm a researcher from Anatolia. I would like to ask about why the Danish sugar beet auction use case is not really adopted by the industry.
Why not commercially? Yeah.
I heard that's a brilliant use case. And that's
yeah.
One of the first.
So what happened with that? Yeah, maybe there's a conversation for beers, but really there was a change in the regulation in the sugar beet market. Is like so basically it's like production rights, like fish quotas. So these farmers, so they were all across Europe, they were changing the regulation. So the farmers, they needed to reallocate these production rights to the places that were more efficient. And that happened across all of Europe at the same time. So we built a solution for the Danish market, solved their problem, and then we tried to solve it. We were in Cambridge, where the UK parallel takes place. But they found another solution because they had the same problem at the same time. So it's like a 1 year, time hole where you could get into that market. And we spent that year and a lot of time up to it, building a solution for the Danish market. And then once we started looking at the rest of the world, they solved it in other ways.
What was the other way? A trusted party or what?
What?
What was the other way? A trusted third party? Or?
Yeah, exactly. Yeah. One way or the other.
Exactly. I mean, it was solved.
Yeah, a lot of fun stuff about that. Yeah.
Great. Thank you so much, Jakob. We're now going to have a lunch break, and we'll see everyone back here in around 45 minutes. Thank you so much.
בעיקרון הפונקציה שמנסים לעשות אותה הכי מגעיל שיש. כאילו, כל הפעולות מעבד אתה דוחף לשם. איזה שם חיבור. קודם כל יש שם גם פעולות ביטווייז וגם פעולות ביטווייז. זה קשה שלפחות גם וגם, כן. יש נקודה אחת שאתה מצפין, זה או שזה FHE ביטווייז, או שזה... אז יש שם עוד ביטים, יש שם שיפטים, יש שם חיבור, יש שם מודולים, יש שם... יש כפל ויש כפל. כן, לא נראה לי שזה... קודם כל זה האש, אז יש לך הרבה סרטים, לא יודע כמה בשעה שלוש נראה לי אתה לא יודע איזה סיבוב, יש 12 סיבובים, וכל סיבוב כזה זה כמו להפעיל פונקציה לבלוק, זה כמו שיש בה את כל הפעולות המג'ילות, נכון? אני גם חושב שזה יותר זה לא באזור של 30. אבל למה אתה רוצה... זה בעיה של הרבה אנשים, זה לינדל דיבר על זה, לינדל באנפארט דיבר. קודם כל לינדל דיבר על זה לכאן זה בעיה גם בתקופה. אבל פשוט, הפתרון שלנו זה
Great. Hope you enjoyed lunch. I'm David from DWallet Labs. For those who missed the first part of the day. And at Encrypt, we kind of put a spotlight on researchers who do real-world research in modern cryptography, but a very large part of doing modern cryptography and advancing state-of-the-art in real-world scenarios is also how that research gets funded. And in academia, there's a pretty clear process on how that happens. And it's not really connected to the real world, right? And it doesn't need to be. It's more about just scientific advancement. But in the real world, or in the, let's not call it the real world, in the for-profit world, things are different. And I'm really happy to have here for venture capitalists who are focused on research and deep tech in Web3 and in modern cryptography. And I'm actually personally very excited to hear some of their answers as an entrepreneur who does real research. Maybe we can start with a round of introductions, and you can just tell us a bit about you, your background, your fund, and we can go from there.
Hello. So I can go first. My name is Nihal. I'm an investor at Pantera Capital. So Pantera is a $3 billion fund based out of the US that focuses solely on digital assets. We're investing out of a $1.25 billion fund now. We've been in the Web3 space for a very long time, since I think like 2013, 2014. Some of our notable hits, probably like Arbitrum, Starkware. We did the seed for both of them, Polkadot, etc. Over 200 portfolio companies. Myself, I don't come from a cryptography background. I come from like a technical AI ML background. Did my bachelor's at Berkeley. Wanted to do an AI startup, failed, and so I went the failed entrepreneur to VC route. And so I was actually an AI ML VC, but then I got the blockchain bug, and once I kind of saw the rabbit hole, I couldn't get out. And so I switched jobs from VC to 0x, where I was working product over there. It's a liquidity aggregator, if you guys have heard of it. And yeah, a year ago, I switched roles, went back to the dark side being a VC. And so I've been at Pantera ever since. So I focus mostly on the DeFi infra stuff, including ZK. So yeah, happy to be here.
Hey everyone, I'm Caleb from Big Brain Holdings. We're a pretty old fund in the space, been around since 2015, 2016, just investing across the entire crypto stack. Big fan of DWallet Labs, of course. Myself, I'm fairly new professionally speaking to the space. I was a passive investor since 2017, started deploying smart contracts in 2020, was on the founding team of Franklin DAO, which is a governance and consulting group in the space. And yeah, happy to be here.
Hi, everybody. I'm David from Lightshift. I'm a partner in CTO. So Lightshift is an early stage fund focused mainly in investing in projects that can have, let's say, a meta impact in the industry. We have our own engineering team that not only helps us do research and due diligence in the space, but also contribute directly to the projects that we actually invest in. That's essentially from the 0 to 1 phase. So what we consider the most critical phase of innovation. So we're very happy that we're lucky enough to have had the chance to invest in DWallet at an early stage, and have been working with them since then. And this is probably one of the best cases of what we typically do when we invest. Myself, my background, I was a founder for around 20 years, mostly playing the role of co-founder CTO. And yeah, at the fund, I lead the engineering team.
Hey everyone, I'm Alexander. Recently launched Reforge, early stage fund focused on 3 core areas: blockchain, network infrastructure, privacy, enhancing tech, so obviously relevant to today, and then the intersection of crypto and AI. But specifically, cryptography, not necessarily digital assets in AI. Launched that about a month and a half ago, so still early innings of the fund. Previously was at Shima Capital, another early stage crypto fund. I was head of research there and on the investment team. I came from a technical background, studied applied math, computer science in undergrad, got into crypto in 2012. I ran a bot farm in college, a RuneScape bot farm, and I was sold my accounts for Bitcoin. And then I've kept up kind of my work in math in my career. So I was building AI products at Teeds, an ad tech startup, originally founded in France. We were acquired in 2017 by Altice. So I was really focused on kind of the AI ML side as well. But then being part of the whole surveillance capitalism and kind of enabling that side of the world, I realized that I should probably switch over to what we were focused on and sovereignty and empowerment of human autonomy. And so that's kind of what led me to fully transitioning into crypto full time and spend a lot of kind of my time bridging the gaps between being very research heavy and investing.
Yeah, can you hear? Okay. Thank you so much for being here, and I'll also try and leave some time in the end for questions from the audience, which usually is relevant after this kind of panel. But maybe to kick things off, I'd like to hear a bit about your high-level thesis. What do you believe are the greatest opportunities that are created by modern cryptography primitives like ZK and FHE and MPC? What do you see as the largest opportunities and why, if you can just give a very high-level thesis?
So I can take a stab at it first. I mean, there are always a lot of opportunities just in general. And if you're doing deep research, I don't think you need to time the market as, just when the bull run's happening, to be honest with you. But I mean, things that I've seen specifically or I'm paying attention to a lot is kind of encrypted mempools specifically on kind of the sequencer side. There's this big milestone that's going to happen eventually when people are going to decentralize sequencers and L2s. And the fact is that using, ZK or just cryptography in general to encrypt mempools, because MEV and front running and all of these are huge issues just in general, and encryption is going to be the key to solving that. And more so than even the decentralized sequencer part. So just in general, when it comes around MEV and the type of encryption around the infra around there and what do you want to use, TEEs, or different types of ways to kind of solve this specific issue. And so that's definitely a big part of an application basically of a lot of the cryptography that I see people or in the VC space, or namely me, I'm definitely looking into, but I'm sure others are too. Again, there's a lot of hype around FHE. I think there's a lot of interesting kind of experiments running in FHE. I think FHE is a pretty, I don't know. I still don't know, actually, and I would love to hear from the other members of this panel if it's more hype than not, because it's been there for a very long time and it's pretty slow. So I think groundbreaking stuff happening in FHE is also a big open space. I don't think, even though a lot of money has gone in maybe in the past couple of months, I still think there's a long ways to go before FHE becomes practical use for specific for practical applications in blockchain. But I'm happy to be proven wrong. I don't know a lot of things. So yeah, that's from my side.
I'd like to say first off that FHE is very new. It's 2009 is when it was invented, so we still have a long ways to go. But yeah, I mean, so on the ZK side, obviously ZK brings a lot of economies of scale to Ethereum in particular and a lot of other blockchains. That's why there's been a lot of capital pouring into that space recently, or not recently, but the past few years. FHE, there's some people like to comp it to ZK, but it really just brings the privacy side, right? It doesn't bring the scalability. In fact, it brings the opposite. So kind of like Nihal was saying, it's super slow right now. So really figuring out ways to make it faster, whether it's through hardware or just new algorithms, seems like a super interesting space to invest research in right now. Also on the threshold side, I think there's a lot of improvements to be made right now. You look at kind of all the chains that Zama's putting out right now that can only have 5 to 10 validators running. you need like a 1/3 of them to decrypt. So it's like not that secure, not that private. So there's still a lot of room to grow on that side. So super excited about that as well.
Yeah, maybe a couple of things. Reiterating on the FHE part. Yeah, it's quite new. I think I'm old enough to remember when people would talk about SSL being mainstream use in the web, and there's no compute power to be able to actually sustain it in most cases. And today we all use it every day in pretty much everything. So I think that's, you asked about the thesis and maybe hinting a little bit how you have to approach this type of technology from an investment perspective. You have to not be cynical. You have to be skeptical. So, and skepticism comes from, of course, a place of trying to find the truth and a lot of patience, right? Because it takes a lot of work to understand where some of these breakthroughs that will eventually actually make Web3 mainstream. For them to happen, you need people like people in this room to have the time and the resources to be able to do it. But ultimately, just like cryptographic primitives was essentially what allowed blockchain to be a thing, to be a proof of concept initially, these are the technologies and the research that is being done by some of the people here, what will actually allow it to become mainstream. So yeah, not sure. It's a bit of a generic answer, but I think just to complement a bit.
Yeah, I think trying to group everything that we're looking at into a thesis is really difficult. But I guess the way that I kind of think about it is first, a big core thesis is just bridging all of the gaps that exist in existing tech. So like, for example, the scalability concerns, the computation heaviness that exists within some of these, private PETs. I would also say that there's a really big opportunity associated with just understanding how this will become applicable and how it would be implemented by on the application layer, and assessing, what is the education and what is the what is needed from the application layer to say, hey, we can actually leverage this in some of our products in a scalable way. So I think that's just such a macro level view that we have to have, because at any point, right, very similar to the AI side of things, where you have a transformer paper come out and then it kind of changes the approach, right? You go from a very old form of, or I guess relatively older form of supervised learning to transformers, and how transformers change generative AI and LLMs, right? And it becomes something that all of a sudden you have to, you kind of can't play catch up at that point. You already have to have had some understanding associated to it to be ahead of the game. So in terms of kind of more forward thinking stuff, I think quantum resistance cryptography is something that is top of mind, just purely based off of the impact that it'll have in the future. But it could be 10, 20 years from now, 30 years, if not more. But just ensuring that stuff remains top of mind, because at any point it could be more relevant, is important. And then just how everything interops together, right? So obviously the cryptography plays a big role in how it impacts the AI side of things. And so, what does that look like? So for instance, I think a more specific area is around like kind of bio-enhanced or bio-driven private keys. I think we as individuals are nature's private key in a way. And so how do we kind of ensure the security of that? How do we implement that in products, and how does that relate to identity on chain, for instance? So I think that there's so many derivatives associated to kind of the topics that we're talking about. So kind of just piecing things together in a different lens is, I guess, my thesis for now.
Great. Thank you for that. So maybe let's get a bit more concrete. So I can say that as a co-founder of a company that is based on research, I always felt like I wouldn't want to be on the other side, talking to crazy entrepreneurs with crazy ideas, where they themselves are not really 100% sure they'll be able to achieve the research that they need, and trying to make those decisions. So I'm really curious to hear how, when you look at an opportunity or a company that does research, how do you evaluate it? What's your process? How do you try and determine whether they'll be able to do the research that they need to do in order to make that a reality?
Sure, I'll take this. So I guess I've been fortunate enough to be in the space for a long time. So I think, or I guess particularly around blockchains, and so I think one is understanding what I have, which is not much compared to most of you guys in the room. Definitely the dumbest one here, but I think, for me, so I studied cryptography and distributed systems in grad school. I studied under R.A. Jules and the IC3 guys and at Cornell, and so I had a really good opportunity to kind of be also in the room with very intelligent people who kind of guided me along the this world that we're in. And so I think from that perspective, it's having some level of deep domain expertise and technical acumen that aligns yourself with the founders that I'm talking to. So one is just being fortunate and knowing that you have that background and then saying, okay, like these are the things that that fit within the realm of my understanding. And if it doesn't, then I go out and speak to pretty much everyone else that is tangential or I guess related to the particular topic at hand. So it takes a lot of time. It is effectively what it is. So I think that that's it. It's just a very aggregate, comprehensive approach to data gathering. Trying to do it in person is incredibly important, because at the end of the day, when I'm talking to founders, it's very difficult for me to assess not just my understanding of what they're building, but can they build, to your point, can they eventually build out what they are focused on or what their objective function is? And then how do I underwrite that? Like, what are the questions that I have to ask for then a founder to let me know or persuade me that they are capable of achieving that goal? And I think doing that in person is way easier, or assessing that in person with the founders or with the team is way better than doing it virtually. And so I think that that's incredibly important. And I think that so we focus predominantly on early stage investments, pre-seed, seed, and so we have very little data. And given and on top of that, being more on the technical side and research driven side, there's just so many unknowns. And so then it becomes a lot about the character of the founders. And so I guess this is a bit more cliche, but like I'll play poker with my founders when it comes to understanding how they assess risk, how they react to me taking their money, or how they react to them taking my money. So I think there's just so many soft skills outside of specifically the research or whatever the company is focused on building that impacts the end outcome, or essentially the journey to achieving that outcome. So it's a very abstract process, but hopefully those are some, I guess, 3 points that I just wanted to bring up.
I'll just add to that and say that if we knew how to build all this crazy stuff that you guys are building, we would not be VCs. So that's for one. I would say like the process for assessing like really cool new deep tech is twofold. So like, I think we're very fortunate that cryptography is super new and that it doesn't take that much time if you really study it to get up to date and then continue learning, but it's actually very difficult to contribute, right? It takes a lot of effort to contribute. And so that kind of, if you put in the time there, like I studied cryptography under Tal Rabin in undergrad. And so that gave me like a bit of a boost, like a bit of like a bullshit filter per se on some of the white papers that I'm reading. Aside from that, it really just comes down to referrals and building up your network in academia and, understanding like who's really the most cited, who's on the cutting edge. I know Svika's in the audience today, so he's a great person to get references from and see who he's working with and what they're building. So I'd say that's like another big indicator that we look at.
Yeah, maybe double clicking on the founder traits just in general from like a founder perspective. If you're going to a VC like Pantera, like understand that like my technical background will not be in cryptography when you're talking to me. So the thing is that when we're looking at a very deeply technical kind of project at the early stages, we're looking for like, and this is super cliche, but it's actually very important because you'll be talking to VCs that are not at the same technical level as you, and you'll be explaining this to a host of individuals that will not be at the same technical, level as you, and it's to be like a truly kind of a visionary that can break down what you're building. Like in the end of the day, yeah, we don't expect it to be a finished product, project when you're presenting it to us. We understand there's going to be like levels of research that's going to happen. Like when we did the seed of Arbitrum, like fraud proofs, like they were the first to implement fraud proofs, but I mean, we didn't know when that was going to happen eventually, right? And so the thing is that you need to be able to break down your concept and like explain it. And those are, we found, the best founders specifically. When you're thinking of like building a company on top of deep research, we're looking for like, and there are different types of profile. Like the charismatic leader, you don't need to always like do public speaking and whatnot. But the fact is that there are different profiles, but we're looking for like a visionary who really believes in the mission that they're actually, striving for. And that's very apparent. Like, and if you see all the PhD leaders in the space, like Sri Ram, you can tell like there's a certain profile of the people who make it. And it's like people were saying in this panel, those kind of soft skills are definitely something that we're looking for, especially when it's really really early and the research is very let's say dubious in the sense that will it be reached. So we're looking for someone who at least has their conviction, because if you can't convince us, and we don't know anything about it, how are you going to convince people that know something about it and it's still kind of like at the off chance? So that's definitely something that we look at when we're assessing whether they can not only like complete the research but also build a company on top of it.
Yeah, I mean, can you? Yeah, okay. Yeah, a lot has been said, so I'm going to try to not repeat too much on any of the topics already expressed. I would say that from Lightshift's perspective, because we have the characteristic that we have an engineering team in-house that essentially tries to cover as much as we can in a lot of these technologies, it does give us an advantage than a typical early stage investor. But at the end of the day, we can't do it alone, right? So we need to, just the same way that when we approach something holistically using the entire team in-house, we do have to go outside and rely on peers that we recurrently go to around specific technologies, and essentially also depend on their opinion to form our own opinion, which at the end of the day has to be one. I would say that maybe to reinforce a little bit of the things that have been said as well, what Nihal was now describing about the founder, they don't have to be super charismatic, but they have to be charismatic enough to convince not just the outside world, but I would add to convince their peers to actually join them, because it is the same case for them. They can't do it alone. And typically, actually, the founders are not necessarily the most technically capable. They can be, but it's not always the case. But they're technical enough that they're able to essentially put together a team that is what will allow to cross that threshold, to break what they need to break to reach what they actually want to do. The last thing that I would add is that it is quite different, and we do invest in projects that are not necessarily as technical at Lightshift. It is a quite different approach than your typical maybe product-based investment or very business-focused investment, because the way that you have to essentially come to the conviction to invest has to rely a lot more on doing game theory based on systems that are not necessarily as systematic as if you were investing in a business-based investment. So the way that we approach that is we try to get as close as possible to the founders. We try to put ourselves in the position of the founders, and yeah, I think we also have a little bit of an advantage there, because a lot of the team, including myself, we've been founders as well. So we strive to be good at essentially understanding what their challenges are, and kind of from their perspective see will they actually be able to overcome all of these challenges.
Great. I think that's actually a good segue to the next question, which Web3 is kind of notorious for running on hype cycles, and quite like significant hype cycles. The hype is real and the fall is real. It's all it's all very extreme. And many Web3 investors, even the ones who are serious tech savvy, they have this dilemma, or I don't know how to call it, financial nihilism versus, bringing value to the world, where they have the commitment to their LPs to, return profits. And even if they don't believe that this creates real value, or maybe it will be worth nothing, but before it will be worth nothing, it will create a lot of returns. So I'm curious, how do you deal with that dilemma? How do you balance those things out when you look at investment opportunities?
Yeah, I wish I could be a sage person and say like, no, this is not the reality of the world. But like right now, I'm looking at a bunch of AI Web3 companies that I would definitely not be looking at if this was not the hype cycle that it was. And so I would say that for companies in these like bulls and bears are going to be part of fundraising just in general, but you should look at that as a separate part of the equation. Like what you're building specifically, this is kind of on the job of the founding team to create a great narrative and understand what's hot out there, and then understand how your technology basically applies, especially if you're doing deep research into the narratives, right? I see the Monad hat over there. Like, how many times Keone had to pivot specifically, like before parallelized EVM became the biggest narrative in the space. I mean, Say was a live product over there, and it didn't become a narrative until Monad made it a narrative. So, and they're doing some crazy innovations on kind of parallelized consensus with Monad BFT and the Monad DB. But like, so what I'm saying is that innovation and deep research, like as a founding team, you're going to have to be very cognizant of the narratives of the time, and also understand that if there's a way that you can kind of fit yourself into that narrative, like, okay, decentralized sequencer, like you're creating like encryption, and it's like, okay, so mempools are going to be needing to be encrypted. You're going to have to draw that line basically and kind of develop those narratives and try and iterate time after time again. Like it's not like a set process of what you are and how you fit in kind of the stack and of the bull and bear. That's going to be ever changing, and you'll find a hit at some point, but that's definitely on the founding team to kind of do that, and you should do that. Like I would like to say that, hey, if you just focus on the deep research and you just plug along the way, that funding will come to you. Unfortunately, that's not the case. You would definitely, I would say, to give yourself the best bet, definitely understand narratives, understand the market, understand that's the best way of like basically you got to play the game. I don't know. It's not a good thing to say, but I would say that if I was giving advice to like my friend who's a founder, that's definitely something that helps a lot when it comes to fundraising.
Yeah, so unfortunately, I agree with a lot of what Nihal is saying. I feel like, especially when numbers going up, it feels like you're investing and you're playing a game of chess, and you're making moves expecting your opponent to like hang their queen, basically. So, there's a lot of kind of like hype related stuff that just gets funded because they can fit the narrative and whatnot, and the tech actually sucks, and that's really unfortunate. I would say that like during the bear, everyone just wanted to do research and just focus on the tech, and now it's more about narrative, and like crypto trades on virality, so it's kind of by nature of it. Maybe that will be fixed when it gets more regulated and leverage goes down and whatnot. But right now, it's a lot about just going viral, and so obviously the best situation is to have really good tech and go viral. But a lot of times, we see one or the other. So getting that sweet spot is really important for sure.
Yeah, I mean, it's of course a very good question. Adding a little bit to what you guys are saying, from our perspective, we really are much more long-term investor than we see in the industry. So it's a little bit easier for us to essentially not depend so much on the cycles, especially if we're investing so early. Where, I mean, most of the times there's no lines of code. There's maybe a light paper. Sometimes there's only a couple of founders that have very high conviction about what they're building. Something like that, especially if it involves doing research that involves tens of people, that can take a decade. And of course, at the end of the day, we're mandated to literally make money to our LPs, and everything that we do needs to be in accordance with that. But the difference with us is that we can do it with a long-term approach, and that's a very big advantage. And then the other thing is that I do believe that as the industry evolves and it becomes more mainstream, and as it becomes a lot more obvious to the participants that are not just, maybe whoever's setting the price is not necessarily, a big native institution, or, the degen community that is following a specific narrative, it will change a little bit over time. And we believe that we will be in even further advantage at that moment, because we're always investing from the perspective of, will this actually bring value to the industry and the world in a way where at the same time we're able to make money. So we are maybe dreamers in the sense that we're always looking for a project that gives us both, right? Strong narrative, but at the same time that it's bringing a lot of value to the industry.
Yeah, excuse me. It's not mutually exclusive. I think we always get asked, do you want to be right or do you want to make money? And I think that's such a stupid question, because it should be both. And it's possible to be both, but I think that a lot of investors in this space particularly have a very myopic view. If you followed me on Twitter, I shit on other VCs a lot, but it's real. It's a real problem, because VCs are supposed to be the earliest allocators, capital allocators, and supporters of founders and teams, particularly in frontier tech, right? And so when you have these structural flaws of attaching everything to a monetary component, it's very easy to become detached from that. And so I think a lot of VCs are hedge funds that call themselves VCs because they can get in at earlier prices or lower prices. And then as soon as the token launches, then you essentially have a misalignment to the founder. And then as a founder, you, specifically Web3 companies, if you do plan to launch a token, you are essentially getting underwritten by like a Goldman or a Morgan Stanley about to launch on the NASDAQ while trying to find product market fit. Like that's ridiculous. So I think this is very important. So like, in order for us to navigate that, I think just sticking with, let's focus on both. I think it's very possible to invest in companies that will actually move the needle in this space while also, achieving our fiduciary duty of making money. And I think it's our job to identify the best founders and teams that do that. I will agree with the narrative piece, though. I think that you have to play the game as a founder. And so that's just the nature of the beast. And then we as investors have to decide whether that aligns with our thesis, and then whether it's the right time. But I mean, if you look at Gravity Blanket, like there were heavy blankets that existed in life, right? But they just called it Gravity Blanket. They positioned it in which they made it very attractive to buy a heavy 25-pound blanket for an absurd price. And so all it was positioning. That entire multi-million-dollar company that raised, $1 million over 24 hours was just a positioning exercise, and they got really good at it. And so I urge all, founders to kind of keep that in the back of their minds, even if they're building something super technical, super research oriented, to play that game, because it'll only, benefit you in the long run.
Thank you so much. I'll maybe have like one question from the crowd if anyone has a question. And if not, we can move forward to the next one. Okay, no hands. Great. So I want to really thank you so much. It was very interesting to me, and I'm sure the audience as well. So thank you for participating, and we'll move to our next session that I actually don't know what it is, but let me check. Thanks. Oh, awesome. Actually, this one will be interesting for you, Nihal, I think. Yeah. So I'm happy to invite Tomer Ashur to speak about algebraic ciphers.
Yeah.
And Tomer is the CEO and founder of 3MI Labs. And yeah, thank you, Tomer.
Okay, yeah, thanks. Thanks for the introduction, David. So indeed, my name is Tomer. I have to apologize in advance. I haven't been on stage, I think, since before COVID, so I'm not sure I still have it. We'll see. Today's talk, it's not a talk, I'm not a professor anymore, but today's presentation is about advances in algebraic ciphers. I am Tomer from 3MI Labs. What's 3MI Labs? We are a research company, in cryptography and Web3, providing commercialized research as a service, if you will. We are partners with the Wallet Labs, Polygon. We previously worked with Starkware and a few other companies. But that's not what you came here that's not what you want me to talk about. So I'm saying up front, this is the most cryptographically heavy slide that I have today. The background of algebraic ciphers is with Starkware. Starkware had their idea in 2018. They wanted to use zero knowledge for scaling Ethereum. And they realized quite early that in ZK Starks, you need a hash function for it. What is a hash function? It's a function that takes a string of arbitrary length and returns a digest of a fixed length. And for those of you who are less techy, we can informally say that it takes data and shrinks it to fixed size fingerprint. And just like the fingerprints of two people are supposedly not the same, this is actually not true in reality, but that's what we claim. The same holds for hash functions. They provide the fingerprint that is unique. And I'm sure that you've heard of some hash functions like SHA-256 and Ketchuk. Now, what we need, like I said, this is when Starkware came to talk to us in 2018. The motivation is for application in zero-knowledge MPC and FHE. And why is that? Such protocols have an algebraic structure by their nature. I think maybe I can tell you a secret from the cryptography world. There are two branches of cryptography, like maybe more than two, but for the sake of this talk. So there's the public key people, and that includes theory, all the zero-knowledge MPC, FHE, and these are mathematicians. These are smart people who understand math. I'm not one of them. And mathematicians think in terms of algebras and prime fields and stuff. And you know, we say that the fundamental theorem of algebra, not we say, Gauss said it, that the fundamental theorem of algebra is that a polynomial of degree n has at most n roots. It sounds fancy. There's the other branch, the symmetric key cryptographers and the hardware acceleration people. We are engineers. We descend from engineers. The fundamental theorem of engineering is if it's ugly and it works, it ain't ugly. So we do stuff to make them work. That makes us somewhat incompatible, or at least has made us in the past incompatible. All these smart things, they come from the mathematicians. Okay, so what do we need to run a Stark-based hash function? At this point, we're only talking about verification of Starks, on how to make them efficient. We need a hash function that is efficient to verify in zero knowledge. And concretely, what we want is for this hash function to have a compact description like this. Yeah, okay, this isn't working. But like this, where you can write it as a polynomial or a set of polynomials, but something that mathematicians like. We need them to work in finite fields, finite field FQ. Now, these are two Matsy slides, and from there, it's only pictures. A field is a set F. So, for example, all the numbers between 0 and 11, not including 11. And we have two operations defined over it, addition and multiplication. Sometimes these operations don't look anything like the addition and multiplication you are used to. That's the name we use for them. Examples include the binary field F2 that has the 0, 1, XOR, and bitwise AND. F3, it's 0, 1, 2, modular addition and modular multiplication. And essentially, every prime field defines every prime number defines a field over the set from 0 to p minus 1 with modular addition and multiplication. And every power of a prime field also defines a field, we call it an extension field, from 0 to p to the e minus 1 with some addition and multiplication depending on what p is. That's it, I'm done with the math. So here's a counterexample of what wouldn't work well in a Stark. This is a stream cipher called Cha-Cha, and you see that it mixes, like we have here in green modular addition. That's the usual addition that we think of modulo a number, so like when we compute time. And the red parts are XORs. That's addition in F2. Now, again, as engineers and computer scientists, you give this to someone to implement, there's no problem. They'll write 2 lines of code, A plus B mod P, and then they'll use the result of that and XOR it with someone else, and you won't hear any complaints. For mathematicians, this slide is painful because it mixes operations from 2 different cinematic universes. Imagine Yoda working with Captain Picard to achieve a cryptographic goal. And incidentally, it's also the same people who don't like when we mix Star Trek and Star Wars that don't like that we mix modular addition and XOR. So this is not good for us. Luckily, there's the best cipher ever created, the AES. AES, in case you don't know, the Advanced Encryption Standard, is a block cipher co-developed by 2 Belgians and won the competition for selecting block ciphers that ran by NIST, the National Institute of Standards and Technology in the US. This was in the 90s. And it happens to be, this wasn't the plan, I can say that because one of the co-designers was my PhD promoter, so I can tell you that they didn't plan for this. It has an algebraic structure. AES works, the state of AES is this matrix that I have there. These are bytes, and being bytes, so we can call them bytes, but we can also call them elements in F2 to the 8. So already the state is algebraic, and then it has 4 operations. It has the S box. I'll go back to these 2 subpoints in a second. It has the shift rows, the mixed columns, and the add round key. The shift rows, mixed columns, and add round key are all linear operations, and unlike the real world or the other world, linear operations come for free, almost for free in ZK verification. So we don't mind having them. It's non-linear operations that don't come for free, and which is the case for the S-box. Now, on the other hand, security requires that you would have non-linear operations. You can't have security without including them. So now it's a trade-off between having the right amount of non-linear operations to ensure security, but on the other hand, not too much to not damage efficiency. So maybe I will, yeah, that's what I just said. So we said that the S-box is nonlinear, and in fact, it consists of 2 nonlinear operations. The AES S-box starts with the multiplicative inverse, that is y equals 1 over x, or the way we write it, x to the minus 1. And then a fine polynomial, which is here. I'm not going to read the entire polynomial. In a previous version of this slide deck, I had like the entire derivation of how and why the multiplicative inverse requires 14 multiplications, and the affine polynomial requires 7 multiplications. I decided to save you to save your time and not have it. So just trust me on this. But in AES, we can say that the total cost is 7 plus 14. That's these 2 operations, times 16, because we have a state of 16 bytes, times 10, and it results in 3,360 multiplications. And that is a good first order approximation of the cost of verifying AES in a Stark. But Starks have some cool tricks that we can use that are not available in the traditional computation models. And one of them is that for verification, we already know the answer. So we only need to verify it. Now, if y is equal 1 over x, it also means that x times y is equal 1. That thing requires only 1 multiplication to verify. And in fact, it requires 2 because AES is not just 1 over x, but so we have 2 multiplications now. The affine polynomial has 7 multiplications, and this is actually inherent to the security. So we end up with having now AES, after we optimize on how we evaluate it, 1,440 multiplications, which is a good number, but we would like something better. This was still not efficient enough for Starks in 2018. So that's where we came along, and we invented a new hash function. Right? AES is a block cipher. Now I'm talking about hash functions. I guess that for most people in the audience, that difference doesn't matter, but it matters a bit if you want to be formal. So I'm just giving this disclaimer. The Jarvis hash function looked at what are the cost drivers of AES. So when we calculated the cost, there's a 16 there in the equation. That comes from the state of working with bytes. But there's no reason to work with bytes. You can work with one big element in F2 to the 128. And, well, OK, I'll actually talk about the cost in a second, but you can do that. We also took the affine polynomials, and we used the same trick that we had for the inversion, also with the polynomials. So we took 2 low-degree polynomials, both of them of degree 4. We used one of them directly, that's B, and the other we used its composite inverse. The composite inverse of a linearized affine polynomial of low degree is a linearized affine polynomial of high degree, which is excellent. That's really what we want. And this property of Starks that you can compute in more than one way really allows to evaluate this efficiently. So the cost of Jarvis is 2 times 3 times 10, 60 multiplications. And there's only one problem with that. It's insecure. So, and unfortunately, it wasn't us who discovered this. It was someone else after we published it, as it happens. And this is the point where we understood. Again, I can't speak for all cryptographers, but I can say about myself, at this point, I was already doing symmetric key cryptography for about 8 years. That's enough to develop a certain level of intuition about what works and what doesn't. That's what I thought. And then this showed me that all the intuition that I have as a symmetric key cryptographer isn't necessarily true when we move to algebraic ciphers. And sure, I took it badly when this was broken back then, but it made me a better researcher because it forced me to start working from first principles. Can't take anything for granted, even if you have seen it work so many times. So Jarvis was insecure, but we can still do better than AES. So building on Jarvis, we did 2 things. You can't have just one field element. And to be honest, we don't yet know why. There's still so many open research questions here. We're not sure why. We know what would happen, but we don't know why there's a symmetry break when you move to 2 elements. Our new cipher is called Vision. It's now a vector of field elements, whatever size you want, whatever size support your Stark system supports. So a vector of elements, they go through the multiplicative inverse, followed by the inverse of the affine polynomial B. And an MDS matrix. Now you see in Jarvis, we only have the affine polynomials because the point of a linear layer, for example, an MDS matrix, is to mix elements. But if you only have one element, then there's nothing to mix. You don't mix an element with itself. Now we need, again, an MDS matrix, which would affect efficiency later. That's why I'm pointing this out. And this is one step within the round. And then the other step, again, goes through the multiplicative inverse, followed by an affine polynomial and an MDS matrix. And to evaluate this, you can fold these 2 steps and represent them as a single round that is evaluated efficiently from the evaluator's perspective, but still remains hard to evaluate from the adversary's perspective. So that's Vision. Yeah, OK, the cost, we've derived the cost for this. This cost is based on some mathematical reasoning. And I've heard that I'm not the only one who works with wishful thinking, squinting your eyes, and hoping, and experimental evidence. So this is less certain than what I would like it to be. I can't really justify this equation. I just know that it works in practice, and I have some arguments for it. A good thing is that nobody has broken this in 5 years, while many newer functions were broken, so I'm quite confident, at least that it won't happen to me again. In terms of the Stark systems that people use today, so I'll start with the second one, where we have m equal 12, so that's the number of elements in the state vector, and n is 64, that's the field size. Then you get 192 multiplications. That's already pretty good. I've seen newer companies working with, that are starting to work with smaller fields than 64. So when I started working with Polygon about 2 years ago, 64-bit fields were the state of the art. Now I can see companies starting to work with 32-bit fields. It would increase the cost of the hash function, but apparently it makes everything else more efficient, so I don't know. But it's still good numbers. But you know, the Bible says that there's no rest for the wicked. Every time we think we've got to where we need to be, then someone throws a curveball at us. We published this, and then people started moving to prime fields, because prime fields are more efficient anywhere outside my niche area of algebraic ciphers. And again, this comes from the fact that the mathematicians who are developing these things prefer, and there's something more mathsy about prime fields than binary fields. This brings us into an entire new domain of unknowns. Symmetric cryptography has not worked with prime fields. There are some maybe synthetic examples, niche cases, historical stuff, but mainstream symmetric cryptography has always been with binary fields. We have about 50 years of theory of symmetric crypto to build on, about the properties of the building blocks we're using to design symmetric ciphers in the binary case, and we have none of that in the case of prime fields. We also don't know, and we have seen that it actually doesn't always happen, that some basic truths translate to the prime field case. There is a construction called Merkel-Damgård, that's a standard way of building a hash function, doesn't seem to be secure for prime fields. Not clear why yet. I see that Ben is also surprised by this observation, but it's true. Like, we see attacks. And the attacks that we are used to, so my background is in cryptanalysis. I actually come from breaking ciphers. There are two basic attacks in symmetric crypto. They're both statistical, differential, and linear cryptanalysis. And almost every paper you'd read opens with the sentence, differential cryptanalysis is one of the two most powerful attacks in symmetric crypto, the other one being linear cryptanalysis. Both of them don't apply the same way to prime fields. And so they are not important. I wrote a PhD thesis on something that is going to be obsolete. That sucks. And algebraic ciphers, the kind of that mathematicians do, which I am not, is actually very significant in this field. So we all have to learn our stuff. But surprisingly, attacks in public key crypto are often algebraic in nature. They don't translate very well also to this setting because of the completely different structures that we use. The public key crypto has a lot of randomness and entropy involved in each instance of the problem, where we have compact representations with a lot of redundancy, and it really changes the algebraic properties. So there's so much to study in this. And I'm, by the way, also having PhD students if anyone is interested. But of course, it's not that we decided, okay, we don't know how to build them, so we won't. We did what everybody in this room is doing and hoped. And we have Rescue, or we had Rescue. Rescue is algebraic hash function efficient for Starks over prime fields. It supports any prime field. We did notice that inversion doesn't work the same way when you move to prime fields. It took us a while to understand why, but we do now. If there's time, I'll give the answer. But instead, we couldn't use inversion. So instead, we used something called a power map, x to the alpha. We need x to the alpha to be, or we need the exponentiation with alpha to be a permutation. There's a very easy way to check if a certain alpha is a permutation over a given field. You need a small prime. We first thought that that prime would be 3. In today's fields, 7 seems to be the smallest prime that is a permutation. And to have a high degree, like we still need a high polynomial degree, because again, cryptography, then we use the composite inverse, so x to the 1 over alpha. And because of folding that I've mentioned, that you can evaluate instead of 1 over x, you can do x times y equals 1. You can also do fold this round and evaluate it efficiently as if it was only power alpha without the high degree that is 1 over alpha. But I do want to stress this is for verification. We'll soon go to efficiency of proving. Yeah, the cost, I already gave my disclaimer. We get about 650 multiplications, quite independent of the state size. That's also something that needs explanation. But then we were asked, okay, so then Polygon came. Oh no, so this is still the Neptune project. They needed, so okay, at this point, verification was efficient enough. Now they want to start proving efficient. After saying that it doesn't matter, they decided that it does matter. So we came up with a new hash function, rescue prime, where after this was, I think rescue was out already for 3 years by then, and we saw that attacks are not progressing, so we reduced the number of rounds from 10 to 8 and made a few more smaller changes. So rescue prime. All of these functions, by the way, are used in production in different systems. And none of them is broken. That's a good sign, or not broken yet publicly. And then we had the rescue prime, and that's where Polygon said, but we want to push it to the edge device to be able to create the proof. That requires that you improve the efficiency much more. So we worked on a hash function called RPO. The trick here is that the MDS matrix, this M block over there, is tailored to their field. So finally now all the other functions I talked about can work over any field, but RPO works over this field. It's called the Goldilocks field. 2 to the 64 minus 2 to the 32 plus 1. And we can then fix the MDS matrix, and that gave us something between ×2 and ×4 improvement in the proving time. And they still wanted a yet more efficient hash function. And that's now that at this point, the well is starting to dry. We've used all the tricks. We've optimized everything. What we need is to identify an operation that would be efficient, more efficient than the ones that we already have. And that's not easy. Like that's something you make a career out of. And so did I. So we introduced operations over extension fields of prime characteristic, of odd characteristic, that's the term. So this x to the 7 here is happening over a cubic extension field. So you take 3 elements in the base field, merge them together, and now they are 1 element in an extension field. And you run the x to the 7 on that. And that does good mixing and is more efficient than the other tricks. And that allows to remove some of these rounds, the 1/7, which are the performance bottleneck, but are necessary for security. Now I'm venturing, so this was past, present, and now I'm venturing into the future. We are looking into having a version of xhash that is xhash 8, where we don't, in this layer, we don't have all the 1/7s, only some of them. That seems to be still fine. Like, we're pretty confident that this will still be secure. And the effect is direct. Like you remove 1/7, it saves time. That's immediate. We're also considering, in terms of future direction, to have an X-4. So only 1 out of every triplet would have the 1/7 operation. That one already starts to be shaky in terms of security. We think it's secure, but we're really finding it hard to argue this security formally. So to complete this, we would need a more evolved theory for the security of algebraic hash functions, the thing that I said that we don't have. Another direction that I'm seeing, we're working with Ulvetana. That's a hardware acceleration company from Serbia. Well, they do hardware acceleration. They created their own zero-knowledge proof system that is Stark-like. It's called Binius. It works over binary fields. So we went back to Vision. And this is our design for them. So that's Vision again. But they have had, now we're again prover efficiency. They had problems with the high degree of this. And sometimes all it takes is a small observation. So the usual way to represent this B to the B inverse would be in polynomial form, and that would eat up some resources. But noting that this is an affine polynomial, you can also represent it as a matrix multiplication with bits, and then it's super efficient in hardware, and it's exactly the same thing, doesn't require to change anything. And that's possible because of their new system and because they work in hardware. So in software, it probably would be less efficient. What else? We also see, okay, so I was unfortunate to miss most of Zvika's talk this morning. I know that he spoke of FHE. I don't know if he mentioned transciphering. One way to improve the communication complexity of in FHE setting is that you symmetrically encrypt the text on the user side, then upload it to the FHE server, and then decrypt homomorphically that string. We developed a cipher called Chagri that is super efficient for this decryption. It is about 2 or 3 times faster than AES in this context. And AES is already pretty good for FHE. Yeah, okay, that's how it looks like, but I don't have time. Yeah, okay, there's also represented R1CS. I'll skip that. But the last thing I want to mention is beyond hashing. So now we have hash functions for the star case. But if you want to do privacy, if you want to add privacy using zero knowledge, you're going to need to encrypt stuff. And this is something also D-Wallet are interested in, on how to encrypt in a way that would be efficient to verify in zero knowledge. So we are also designing authenticated encryption schemes and the protocols to use them. And I believe that's all right on time. Thank you all for listening.
Tomer? Yeah, thank you, Tomer. Always great. I'm happy to bring on the panel of our research leaders. So we have Akash and Dolev and Michal, and where's David? Can someone go fetch David? Yarden, can you go fetch David Noguera from Lightshift? Tell him the panel is starting. Great. So I'll let David take this away. We're already... Sorry. Yeah, no worries. Okay, thank you very much.
Hi, everybody. Sorry about that. Yeah, so I mean, I think if you were here earlier, you already know who I am. I'm not important anyway in this panel. So here on to my right, we have Dolev from D-Wallet, and then we have Akash from 3MI. This is an internal joke, sorry. And then we have Michal from Netherminds. And actually, I really believe that it's much easier if they introduce themselves and not only pronounce their names properly, but also say the things that matter about who they are. So yeah, please.
Okay, hello. You pronounced my name perfectly, by the way. So yeah, I'm Dolev. I'm the VP Research at the Wallet Labs. Before that, I was serving in the IDF for 5 years in the National Cybersecurity and Cryptography Unit, 3 years of which I was the cryptography team leader. Within these 3 years, I did manage to integrate into the IDF different worlds of modern cryptography, zero knowledge, MPC. So that was very challenging and fun to do because they are very strict people. And getting new ideas into there was quite challenging, but we got some good ideas there. And yeah, then I went out to the industry and started working at the Wallet Labs. I got there basically because I had good relationships with Scully, the CTO who presented to MPC this morning. We had good work together back in Matsov. And we proceeded to work together at the Wallet Labs, and it's great.
Hello, everybody. I'm Akash, but thinking of rebranding myself as Akash for the Web3 people. I'm head of research at 3MI Labs. We are a research house, all things cryptography, Web3, distributed systems. We are based in Belgium. We are 7 researchers, and none of us are Belgians. And a bit about myself, I have a bachelor's in computer science, a master's in AI, but then I got the blockchain bug like Nihal did. And I got into a PhD in blockchains at KU Leuven with Professor Bart Perneel. Yeah, that's about it. Thanks for having me.
Hi, my name is Michal. So you pronounced my name very well. Thanks a lot. I'm head of research at Nethermind. I think now it's on. Okay. I'm head of research at Nethermind. My background is in cryptography. I did a PhD in cryptography. After my PhD, I went to Tartu to study zero-knowledge proofs under supervision of Helger Lipma. After that, I decided to leave academia and joined a blockchain company to work on the zero-knowledge proofs in the blockchain space. And in 2022, I joined Nethermind to create a cryptography research team. And from that time, the team grew. Now we are no longer focused only on cryptography. We have 4 teams now. So we have the cryptography research team that focuses on this fundamental research in cryptography. We have research solutions teams that takes cryptographic building blocks and create more complex protocols out of it. We have DeFi research team that deals with everything related to risks. And we have protocol research team that helps blockchains and L2s to be economically secure.
Thank you for that, all 3 of you. So maybe to kick off, a question that I think is quite important, which is, I mean, as researchers and cryptographers overall, you of course have to have a specific mindset, and this is a work of passion that requires a lot of persistence, and a lot of times it also becomes a little bit of an individualist approach. But at the end of the day, you have your own ambitions, but working for companies that have their own goals that are, at the end of the day, for profit, how do you essentially find a way to still be able to be passionate about your work while at the same time not necessarily following blindly, but for a purpose that is tied to a company specifically?
Yeah, that's an interesting question. From my experience, actually, oftentimes the financial considerations and management restrictions can lead to interesting cryptographical problems, actually, and it can make actually the problem more interesting. So in the 2PC MPC work you saw beforehand, there were a lot of restrictions that led to some very nice design concepts, and it's really fun actually, and I really enjoy combining the two. And for now, I didn't see any problem with that. As long as we work in a field that we're passionate about, we will always find a way to get ourselves doing interesting stuff, and it shouldn't be mutually exclusive.
Well, fortunately for us, our passions turn out to be profitable, so that usually helps. But we're actually more focused on the research itself. So our clients are the ones that are profiting off the research. And our main passion is actually solving hard problems. That's what drives us as a company. We spend hours arguing with each other, coming up with better ideas to make products much, much better. Especially like, for example, I don't know if anybody here plays cricket. There's a very hard ball called the Yorker, and that's usually meant to get you out. And we enjoy getting Yorkers because that really brings us together, and we then are passionate about solving those problems.
So in Nethermind, we try to build like open opt-in world, and this vision is like super inclusive, and that actually makes for us very easy to find partners to work with other projects. So when a researcher comes to me and tells me, hey, I would like to work on X, then for me it's okay. So where can we find a partner to work on that? Who we can collaborate with? Which project would benefit from that research? And that way you can also build like sustainable like research team, right? By finding partners. Also, Nethermind started as a Ethereum execution layer client. And when you build an execution layer client, it's hard to say it's like for profit. Like it's hard to monetize the client itself. But when you get this expertise in building such systems, then the clients come, right? Because they want to have like their bespoke solutions, right? And that's how you ensure like the cash flow.
Okay, maybe continuing with you, Michal, just to follow up on this, because you're describing your vision as the individual, but at the end of the day, your roles are leading teams of people that are essentially as passionate about this field as you are. How do you build such a team? How do you build a team that works in harmony, it was working towards the same goal, and while they also have to keep their passion going?
Yeah. So building teams is super difficult because hiring is very difficult now. I think like we are quite in a niche. So even though like Web3 like got a lot of people into cryptography, there is still quite few people with necessary knowledge and qualifications. So hiring is very difficult. But when you have people, I would say like you need to talk with them, like to understand like what they want. Because like in my team, I have researchers that are like purely focused on the research, for example, and they are not interested in like leading teams. But I also have people who are very good researchers, but also enjoy leading teams, like provide like new think about like new research problems and like drive people like to work on them. Yeah. Sorry, one more thing, like what Dolev, you said that this real life applicability of some research is also like a big factor, right? Because it is interesting to see your own research being like implemented or like influential for something.
Yeah, right. The fact that we're doing things that are actually in deployment is a gift, I think, and it makes it more interesting and more fun. And you can be more proud of your work when you know that it's actually applicable in the real world, I think. Some cryptographers don't like it. They try to get away from these fields once they get implemented. But in my opinion, it's a gift. I also want to jump in and say that you don't want your team to be too harmonic, and it's interesting to point that out. But I do think that we need at least one person that will ask the hard questions and try to tackle the solutions that are offered to make sure we don't miss anything. And we also want people to think differently and be open-minded and suggest different solutions. And yeah, I have a partner from the unit that also works with us that always does that, and it could be very heartbreaking sometimes, but it's important to do that. But yeah, all in all, we want to have good environment. We want people to be embraced and to be able to build themselves from bottom up, because it is a niche, as you've mentioned. And not everyone understands cryptography. So I think essentially anyone with good math background, maybe even a first degree, with the right training, if he has the right passion to it, and that's something that in crypto you can get a sense of really fast. Like you can see one presentation about garbled circuits and know if you like it or not, I think. I think that's the right path. So you need a good environment, good training, good people, open environment, but you also need critical thinking, and I think that's the right way.
I agree with both the speakers here. Like they made really good points. Now I'm trying to think what I should say. But I do believe that we're fortunate enough to, like the initial team of 3ML Labs, we've been working together for years because we were in the same PhD department. So we have found a way to be a team and work cohesively. We recently hired a few more people who, according to you, are critical thinkers. They challenge us a lot, and I personally really enjoy that, because when you have a set mentality in the team of working cohesively, there has to be somebody who questions what you're doing. And we're specifically looking for people like that who question what we do. We also make sure that every week we have a day where everybody can actually work on what they're passionate about, because ultimately that might turn into a product where the cash flow will come out of. So it's a mixture of all these things. I think you have to be open-minded, but you also have to be critical, very critical about the actual research going on.
Okay, cool. That's cool. Maybe I'm going to jump or at least change the order here, because I think it's a good segue into, do you think that the Web3 industry is conducive of what you're describing, meaning that tangibility that you're describing about the things that are being implemented? Do you think that the fact that you are in the doing things in Web3 industry, using essentially your ability, your skill set, your long investment of time in cryptography to something that can actually become tangible, do you think it's a good conducive medium for what you do?
So the reason why I switched to blockchain space and Web3 itself was because I did a master's in AI and data science, and I was not happy about how data is being capitalized on. And I really think that Web3 has opened doors for like a lot of good research in co-ed technologies like computing over encrypted data. What we as a company have been working on together is to actually build on this, I would say, cycle of growth in the community, in security and privacy. And yeah, I am kind of losing train of thought here of what I was trying to say.
Right. I think you're going on the right direction. So essentially, you do think that Web3 is a good medium. It's conducive for what you're doing.
Definitely. I mean, it's not just cryptography, it's also the research in distributed systems. I mean, I think George Denez is here from, and he's going to talk about Mysticeti. Excellent work. And also, we ourselves have been working on something pretty cool with distributed systems. So it's really a culmination of amazing research in cryptography, like the guys at Devolver Labs are doing, and also consensus stuff.
Yeah, I also think most definitely. Wow.
You have a voice.
Yeah. No, but it wasn't like that beforehand. Okay. So yeah, I wanted to say that just as the Web 2 technology boosted cryptography in symmetric cryptography and public cryptography, the need for decentralization and Web3, which is believed to be the next generation, which is something that's gonna be orders of magnitude, at least that's what expected to be, orders of magnitude more effective. In turn, also boosts the crypto world. So you have massive advancements in FHE, in consensus domain, MPC domain. All of that essentially comes from Web3 and from also the financial considerations there too. And I think it actually goes inline. So if there's a lot of money, it means that the community is large. It's where the world wants to go, and therefore it's where it should go. It's a good sign, not a bad one. And that's also where the wallets want to be. We want to contribute to Web3, and it actually does mean that we want to contribute to all of these areas in cryptography, and that's what we're planning to do.
Yeah, I can only agree. So for me, it's amazing how development of Web3 speed up development of certain crypto fields in cryptography. So we have massive advancements in zero knowledge, in distributed systems. I think like we see like more and more understanding in the Web3 community that other research branches like algorithmic game theory is also like very important, right? And like people like from that fields also are getting sucked into Web3 into a Web3 world. When I started my PhD studies, my perspective was mostly like, okay, I will stay in academia, right? Because there's not that many jobs out there, and maybe there was not that much interesting for me. But when I was in the mid of my postdoc, I realized that wow, there's actually a lot of going on outside academia. So that's the amazing part. Like when Dan Bonnet made a course at Corsia, I believe in 2022, over 1 million people subscribe to listen to him talking about cryptography. So yeah, most of these people are not going to be researchers, but that shows the scale of how cryptography was somehow like popularized, right, in the society.
For sure. And I just like to, sorry. I just like to add to that all of us in this room are like at a cusp of something huge. I think we're all doing excellent work. And tying to your earlier question, that's where we, I think, tie in the for-profit nature of this industry and our passion, because the passion about being groundbreaking, like groundbreaking some new technologies is in itself pretty fulfilling.
Okay, cool. Maybe to expand a little bit, how do you convince a top cryptographer that is skeptical or even cynical, which is I think more common about Web3, to join a team that is working purely on Web3?
Yeah, I think we have such a person in our team. We sucked him in there without mentioning names. But I think the cryptographical problems are very interesting. You just need to look for them. And you get him like that, just like that. So you ask him an interesting cryptographic questions, you don't give him the context, and he starts working on it and thinking, and yeah, and then you tell him what's the application, and then he has nowhere to escape. That's at least my experience.
Yeah, I think it's the combination of a really hard problem that you throw at interested minds, and at the same time they get to see their product in practice and how people react to it. I think it's very satisfying to see that people are actually using this amazing research that they're doing. So it's quite easy actually to pull in really hardcore researchers.
Yeah. I can agree. So there are like the 2 points. You can abstract away the problem, right? Like put blockchain on the side, and on the other hand, like show that, okay, you solve this problem and there will be like practical application of the solution.
Okay, cool. Maybe switching a little bit and asking you, each one of you individually and indirectly to your team as well, each of your teams, like what is one achievement, one breakthrough that you've had with your team that you're the most proud of?
So the Wallet Labs is quite a new company. We have many things to come, which I cannot talk about yet. So the project that we're most proud of is what we presented today, the 2PC MPC. I really like the process of it. So it started from a very simple question, at least to me, that we could have solved in a slight adaptation of existing work, the maintainment problem, which for some reason wasn't looked at the time. But then, once we solved that, then Jonathan came in and said, here are problems 2 to 8. Or actually, it was back and forth. So we kept improving it, and we have some additional results to come. But at least along the process, we had a lot of ideas. Everyone participated, and it was very, very fun. And eventually, we got a product, and it's in testnet, and it's very fun to see, and it was great.
I'll be very prompt with this question because actually the work we're doing right now with the Wallet Labs, and I mentioned before that it's not just cryptography, but also really huge advancements in distributed systems research. One of the products that we have basically come up with, really, I think it's really cool. I'm very proud of it, but unfortunately I cannot talk about it right now because we're still the next Encrypt. I think we'll talk about it, but this time, yeah.
So I think I will mention two achievements. One more concrete. Our team managed to fill the security gap in Stark's security analysis. So more precisely, we shown that FHE protocol is secure under Fiat-Shamir transformation. And to add to that, we were quicker than Starkware team by like 2 weeks. So I think that's also like a big part of this achievement, to be quicker than Starkware on that. And the second achievement is to see like how our team grew, because like a lot of researchers we have now like came to the company as interns with quite little knowledge about cryptography and blockchain, and now they are leaders in their domains.
I'm a bit jealous of the answers Michal gave. So I'm going to talk about the stuff that Tomer itself has been doing from our company. He's been working a lot on like making hash functions really efficient for not just Starkware or Polygon, but also companies like Ulbetana, which are trying to accelerate hardware for like co-ed technologies. So I think we're also very proud of that. It's a more personal effort. That's why I did not mention that 3MI Labs did it, but it's we're still proud of it.
Okay, cool. Yeah, maybe just to conclude, because we're coming to the end of the clock here. Are you actually able to celebrate another team's breakthrough, even if it's something that is competing with you?
We can, because we are very collaborative in nature. So yes.
I think that's easy to say, but I don't like when it happens. But oftentimes we can take it like we saw with DKLS, and we can, lift it for our product as well, so we can build on top of that and utilize observations from previous works to also improve our product. So at the end of the day, the environment is very fruitful, and ideas come from different directions, and we need to jump in and use them. And it's also nice to see competition. It means that the market has a lot of interest, and that the community is growing, and that we're doing important stuff basically, and not just, it's also interesting and we're very passionate about it, but it does mean that it's a good field to work in for the world. I don't know.
Well, it's easy for us because we're a research house, so we just try to work with the team that's coming up with the breakthroughs and make their breakthroughs even better.
That's a good strategy.
Nice. Okay, maybe do we have time for one question, or you think it's too? Yeah, one question. Okay. Oh, sorry. Well, thank you guys. I'm sorry I was late again. Thank you. That was quite cool. Very interesting. Thank you.
Thank you.
Thank you.
Thank you very much for our team members. Do you have the mic on, Yashwant? Yeah. Go back. He'll give you. Oh, it's okay. It's there. Okay. He'll come and give you the mic. So I wanna invite Yashwant. That's how I pronounce your name. Yeah, Yashwant from Silence Laboratories. Silence Laboratories are a great partner of ours. They're also co-hosting this event, and he's going to talk about threshold ECDSA with identifiable word. Yep. So give it for Yashwant.
Yes. Hi. Yeah. So.
You have the clicker.
No, because it's connected to the laptop.
Oh, it's connected here? Oh, okay.
Because they didn't have a Mac, so. Should the timer be on?
Sorry?
Should the timer?
That's the time, yeah.
Okay.
Working?
Yeah, now it is. Hi. Yeah, thanks for the introduction. I'm Yash. I'll be speaking about my work on threshold ECDSA with identifiable abort. And I'll be making the case that the honest majority setting is an interesting one to look at. This is joint work with Divya Ravi at the University of Amsterdam. Okay, so just as a quick recap, we're going to be looking at threshold signing, which is a scenario in which Bob, who has all of this Bitcoin on his laptop, which is secured with some signing key, decides to sort of decentralize the management of his key. In particular, he takes his key, he splits it into many parts, and he stores each part on a different device, so that when he wants to actually sign a message, these devices have to run some sort of interactive protocol to produce a signature. And the idea behind this is to distribute the risk in managing this key. In particular, an attacker will need to compromise multiple devices before it gets anything useful about Bob's key. So a quick overview of this talk. If you take nothing else away, this slide sort of gives what's interesting to take away from this. I'll quickly go over the setting that we work in this talk. I'll talk about identifiable abort, what it is, why it's interesting, and how we can actually achieve it. And I'll particularly focus on broadcast for identifiable abort. And I'll spend a relatively small amount of time talking about the ECDSA protocol itself. Most of this talk is going to be focused on sort of the network assumption and not so much on the concrete ECDSA signing protocol, but I'll touch upon it briefly. As a running example for this setting, I'm going to be looking at sort of a network of nodes managing key shares. And I'm interested in identifiable abort in this talk, specifically in the context of mitigating denial of service attacks. And of course, I'll get into how this works and why. And I'll give a quick overview of what the anatomy of an ECDSA protocol that works in this setting looks like. And what I'll really be diving into is what broadcast looks like in this setting, why it's important, and what it achieves. Right, so given that a lot of existing works, and as far as I know most works in this area, assume some sort of broadcast channel, which can be pretty expensive to instantiate, I'll define a slightly weaker notion of broadcast that I'll argue is good enough. And I'll show that you can't really achieve this in the dishonest majority setting, that's t less than n. And in the t less than n by 2 setting, which is the honest majority, it's fairly simple to achieve this intermediate notion of broadcast. And finally, there's a clean honest majority protocol for ECDSA signing, which I'll just give a short overview of. And come ask me after the talk if you're interested. Right, so in a nutshell, the case for the honest majority setting to study ECDSA signing
is the following. Broadly, especially in the sort of network of nodes type of scenario, there is a global honest majority anyway, because you need sort of extra redundant parties to help you recover the key if it were to be lost. And honest majority, as we show in this talk, is sort of necessary for a fundamental building block to get identifiable abort anyway, especially when we want to use point-to-point channels only. And finally, ECDSA signing, which is usually somewhat painful because you have to use some kind of cryptographic machinery in the dishonest majority setting, becomes pretty straightforward in the honest majority case, because secure multiplication in particular is fairly straightforward if you have an honest majority. So you don't need tools like OT or PyA or whatever other thing. All right, so this is our running example. There's a network of nodes that Bob from earlier is using to manage the secret key. There's a different fragment of the secret key on each node. And to make things a little more concrete, let's say we look at 3 out of n signing. I mean, n is 5 here, but what 3 out of n means is that any set of 3 nodes can get together to sign a message. Cool. So if you think about it for a second, you'll realize that the best possible security that you can achieve is security against 2 corruptions, and in particular, 2 corruptions out of 5. And this is why I say that there's a sort of global honest majority, in that if there are 2 corruptions, you can assume that 2-party states are completely irretrievable in the worst case, and so there must be at least 3 overall, that is another 2 honest parties, who will help you reconstruct the signing key. So you need at least 5 parties to make sure that the signing key isn't lost. Right, and while it is the case that there is usually a global honest majority, what's common to do in practice is that you keep 2 of these nodes offline just to help with key recovery if such a situation might arise. And when you actually want to sign messages, you run some sort of dishonest majority protocol with just the 3 parties that are necessary to reconstruct the key. I mean, you don't actually reconstruct the key, but you run a signing protocol between these 3 parties. And in particular, you use a dishonest majority protocol that achieves malicious security, in that if any of these nodes, or rather even 2 out of these 3 nodes, if they were to send malformed messages, the secret key still stays safe. But in the event of a failure that some of these nodes send malformed messages, the MPC fails. And while the secret key is still safe, there isn't a signature that's output by the protocol. So this is what I'll be calling a denial of service in this context. And broadly in the MPC literature, this is called the security of the bot model. The folklore remedy, or rather one of the folklore remedies for this type of situation, is to consider this stronger notion of identifiable abort. So what does that mean? Let's consider this situation where this node on the right is corrupt and sends some sort of malformed message. A protocol that achieves identifiable abort lets you figure out exactly who sent this message, and in particular lets you prove to other people that this is the party that deviated from the protocol. And so once you identified who caused the problem, you can bring up your global honest majority from earlier, rotate out the nodes so that the misbehaving node is kicked out, and you can do whatever you want with this one bad node. Now that we figured out who was cheating, we can maybe slash them and remove their stake or penalize them in or whatever other way is appropriate. And that's it. Once we've thrown out the misbehaving node, ideally signing should proceed as normal and we should get our signatures again. So we're back to the mode where we're receiving output. So in principle, you could always use out-of-band methods to figure out who caused a problem. Right? And this arguably is enough for many scenarios where, for instance, if there's an institution that's controlling all of the nodes itself and it has the ability to debug what happened, what went wrong in a protocol by like examining all the nodes and so forth, maybe an out-of-band method is perfectly fine. But what we want, or what we're interested in this talk, especially in a sort of network where we can't really rely on everyone getting together to debug and so forth, we want a certifiable mechanism within the protocol itself that figures out who caused the protocol. Sorry, that caused who crashed the protocol. And in a little more detail, we want to specify that every party either gets output, or if a party doesn't have output, it has an explanation as to why it doesn't have an output. In particular, it has the identity of someone who caused a crash, in addition along with some sort of certificate that says this is the person who caused the crash, and you can't, of course, you can't falsely accuse an honest party that actually followed the protocol. Very broadly, most protocols have 2 ways in which they could be crashed. two ways in which you could induce a crash. One is to send a malformed protocol message that's deviating from the protocol specification, or you could more simply just send no message at all. Right? If you're just quiet through the protocol, observe that for instance, in the three-party setting or in the three-party signing setting, you really need all three parties to participate in the protocol, especially if you want security against all but one corruptions. You need everyone to speak in the protocol. So just by not speaking, you can crash the protocol, and there's no way to get a signature out. Right, so with those very broad attack strategies in mind, let's figure out how we can mitigate these kinds of denial of service attacks. So usually we can start with some sort of baseline security with the bot protocol for threshold ECDSA signing. And under the security of the bot protocol, we can include some sort of mechanism that guarantees that every party says something in each round. Right? So this rules out not saying anything. So the form of denial of service where you just simply refuse to speak is ruled out by this mechanism. And on top of this, we want some mechanism to guarantee that conditioned on sending a message, all of your messages are well-formed. So this rules out the other form of denial of service where you send bad messages. So yeah, I mean, this on quick inspection, this seems to solve the problem that there's a baseline protocol that is secure against every form of attack except denial of service. And both forms of denial of service have some mechanism that handle it. You're forced to speak and you're forced to send good messages. And right, so for the upper mechanism, that's to make sure that every message is well formed. There are standard mitigation techniques, just a couple of them. The canonical one goes all the way back to GMW, which is basically every party preemptively proves in zero knowledge that all of the messages that it's sending are well formed. That there are well-defined statements for every message, for like the next message function of the protocol, and every party just proves that they're following the next message function. It's of course really expensive to instantiate this generically, but there have been tailored ways to do this for ECDSA signing. For instance, there's this work of Canetti et al. From a few years ago, and also the talk from earlier today. Yeah, this is doable. And right, so this second thing is arguably, or to some extent, somewhat ignored. In particular, how do we actually make sure that people speak when they're supposed to speak, right? So a standard way to kind of work around this is to run all messages or to send all messages over a broadcast channel. So by default, all parties are obliged to broadcast any message that they were supposed to send. You can instantiate private channels over broadcast by, let's say, encrypting to a public key or something, but ultimately, every message is passed through some sort of secure broadcast channel. And yeah, this is annoying because this gives you external trust assumptions, because of course, broadcast is quite painful to construct yourself. So maybe you outsource to some sort of third-party service, which is, there could be some sort of latency in using the service. It could also be expensive in terms of gas and so forth. Alternatively, you could have maybe like one designated node that acts as a coordinator and that de facto implements a broadcast channel, but then that's another assumption because a coordinator is also a single point of failure as far as broadcast goes. So ideally, we want to avoid secure broadcast. So I know that the term broadcast tends to get thrown around a lot, and I want to be more specific about what it means. I'm talking about secure broadcast channels where everyone is guaranteed to get a consistent message, and every honest party gets the same message. So it's easy to see why this works, because if all protocol messages are over a broadcast channel and if let's say party P0 doesn't send a message on the broadcast channel when it's supposed to, then we know that P0 is the one who's cheating because it's been quiet when it was obliged to send a message on the broadcast channel. So that's kind of why broadcast works, but it is a somewhat expensive tool to use that we'd like to avoid. And the rest of the talk, we're going to be predicated on wanting to avoid a generic broadcast channel. So for this work, we defined a sort of weaker notion called broadcast IA. It's more of a placeholder name. It's nothing too glamorous, but it's just what sort of works for this particular setting. We show that it's impossible to achieve with a dishonest majority over point-to-point channels only. This is more of a sanity check than anything. And we also give a simple honest majority protocol that does achieve this notion in just 2 rounds. It's nothing like groundbreaking, but it is useful to have this for this useful to have this particular notion for this setting. For the baseline security with the bot protocol, we borrow an idea from this DKLS paper. It's not the main protocol from the DKLS paper, which is dishonest majority. There's like a section at the end that sketches an honest majority protocol that we kind of flesh out. And finally, for the mechanism to guarantee that every message is well formed, this is also pretty straightforward, because recall that the difficulty with computing ECDSA in a distributed way is doing secure multiplications, which in the honest majority setting is pretty straightforward. And naturally, this extends to also verifying that the multiplications are done correctly. In particular, there's a simple Schnorr-like zero-knowledge proof that just proves that you follow the protocol honestly. And also, there's like these standard techniques from verifiable secret sharing that you can use to sort of prove that somebody had sent you a malformed message, like that somebody didn't send you what you were expecting. Concretely, it's sort of this, you didn't get the right point on the polynomial or something like this. Again, the details aren't super important for this talk. Right, so let's talk about broadcast and identifiable abort. The most basic guarantee that you can expect from broadcast is consistency. In particular, we want that a malicious sender can't trick two different honest receivers into accepting conflicting messages M and M prime. And that's the most basic thing. And in the security with the bot setting, that's in the sort of denial of service susceptible setting, this is pretty trivial to achieve. There's this paper by Goldwasser and Lindell that makes this explicit, in that you can just echo messages across different parties when you receive them. Our work is going to be kind of based on this. So what we want in the identifiable abort setting is that if the sender cheats, every honest party obtains a certificate of cheating, that it's able to prove to any sort of third party that the sender in this broadcast protocol didn't actually follow the protocol specification. So in the event that the sender attempts to violate consistency, that's if the sender tries to convince two different honest parties to accept different messages, you get a certificate of cheating that are called capital omega. And if the sender sends nothing, that's if the sender stays quiet when they were obliged to send a message, what the honest parties get is some certificate of non-responsiveness. I call that little omega. And I want to highlight here that these are two different things, or like we make a distinction between actively deviating from the protocol and not sending a message when you were supposed to, because an active deviation is a definite corruption, and you probably want to penalize this heavily. Like this is a hacked node that's deviating. As opposed to not sending a message when you're supposed to, which could just be because the network has failed you, or you've been cut off from the network briefly or something like this. So we don't want as heavy a penalty for parties that just don't speak when they're supposed to. But again, at the level of this protocol, for the scope of this work, all we care about is distinguishing between these two aborts. Like some sort of higher level protocol logic can decide what to do with this information. All right, so as a quick sanity check, is this notion of broadcast achievable with a dishonest majority? Right? It's pretty easy to see that it's, or rather we show that it's not. So consider a standard three-party scenario where there are two parties that are corrupt. I claim that there's always going to be an attack in which the two colluding nodes can frame P0. And in particular, they're going to be able to prove that P0 is corrupt even though it's not. In order to see why, just consider an alternative execution of the protocol where it's in fact P0 that's corrupt. Right? So being corrupt, P0 can just refuse to participate in the protocol and not send any messages. And by this like certifiability notion, what the honest node should get is a certificate little omega that proves that P0 was in fact offline when it was supposed to have been online. So given that that mechanism exists, let's come back to our actual scenario. P1 and P2 could collude to effectively cut off P0 from the network. They could just pretend that P0 was offline. And given this, they can use the same mechanism that I had mentioned earlier to produce a certificate that says that P0 is offline. These two scenarios are basically indistinguishable except for the fact that P0 in this case is actually honest. And these two nodes have managed to produce a bad certificate against or rather a verifying certificate against an honest party. Right, so that shows that it's impossible. Now, let's look at what's possible, or like, let's see what's feasible with an honest majority. Right, so remember that we have this we were assuming a global honest majority for making sure that the key is still safe and so forth. And I suggest that we can use this proactively, the fact that there is a global honest majority. Concretely, if you have these 5 parties with their corresponding public keys, I assume a public key infrastructure, and we assume that, let's say, P0 wants to broadcast a message M, the protocol proceeds in just 2 rounds. It's just a small tweak of the Goldwasser-Lindell protocol. The first round, P0 signs the message that it wants to send and sends it to all parties. In the second round, every party PI does one of 2 things. If it received a valid signed message from P0 in the first round, it just forwards this message to everyone else. If it received anything except that, that's either received a message that wasn't signed or P0 just didn't send anything to PI when it was supposed to, it signs a message saying bot and forwards it to all the other PJ values, all the other PJs. So basically, after the second round, we can think about what to output, right? So what each PI does is it sees if it's possible to assemble a certificate of cheating. Again, there are 2 options. One is if the dealer P0 was trying to violate consistency, it would have sent 2 different messages, M and M star, to 2 different honest parties, and that gets caught in the second round during the echo. Right, so that gives a pretty straightforward certificate of cheating. And for a certificate of non-responsiveness, which to my knowledge this is the first time we're looking at, if PI sees at least 3 signed messages saying I received nothing from the sender in the second round, then this is enough to certify that the sender P0 actually did not send enough messages or did not follow the protocol honestly. So that's the certificate of cheating and the certificate of non-responsiveness. In both cases, it's just a bunch of signed messages. And of course, if neither of these certificates are found, I'll show in the analysis that it's safe to output whatever message has already been received. This is for each PI. As a quick note on the analysis, so as a sanity check, we can see that an honest P0, that's an honest sender, will never be blamed with any sort of certificate of cheating. There's no capital omega because there's no conflicting pair of messages that the honest sender is going to send. And there's no little omega, that's the certificate of being offline, because you need at least three signatures to certify that somebody was offline. And because there are at most 2 corrupt parties, and P0 followed the protocol, nobody is going to be able to produce 3 signatures saying that P0 was offline, because there aren't enough colluding bad parties. And in the case that the sender P0 is actually corrupt, if any honest parties receive conflicting messages, that yields a certificate of cheating. That's pretty straightforward. And if P0 is quiet, that it sends no messages to any honest parties, then that certainly results in a certificate of non-responsiveness. So conditioned on, given these 2 facts, what we can establish is that there must be at least some honest party that receives something, right? And like one step further, we can look at this and say that every honest party either gets one of the 2 bad certificates, which is straightforward, or if it outputs something, it will be consistent, because any inconsistent message will be caught. And there's no scenario where you output nothing as an honest party, because in the worst case, you'll always get the certificate of non-responsiveness. Yeah, I mean, I'm kind of breezing through it, but really it's a pretty simple analysis if you're looking at it like written down. Yeah, and a couple of notes on this, because this is, of course, not the end goal. This is going to be used in a higher level protocol. Every broadcast message is going to be accompanied by a signature on it. So if you want to blame a sender for sending a bad message later on, you can always use this. But just because you're able to produce a message along with the signature from someone doesn't prove that anyone else got the same thing. Because the other party, because if the sender is corrupt, it can arbitrarily sign messages after the fact. So it does not, in particular, it does not establish agreement. It does not establish consensus, which is why we circumvent a whole bunch of impossibilities. But it can prove that somebody sent you a bad message. Right, so a quick note on how to build an ECDSA protocol out of this. We took this, there's a pretty straightforward way to get ECDSA signing in the honest majority setting if all you want is security of the bot. That comes from this DKLS paper. intuitively, it's just one broadcast round on top of verifiable secret sharing and distributed key generation. In this work, we just take the baseline thing and we add that layer that I talked about. So underneath the broadcast, the layer underneath is the broadcast that I just mentioned, and the layer above that is the message consistency. So the layer below this ensures that everyone sends something. Then we use the ECDSA protocol itself as the baseline, and then the layer on top makes sure that every message sent by everyone is consistent. So that's the NISIC and the identifiable abort component that I mentioned. Yeah, so just to sort of breeze through it really quickly, these protocols are based on the standard class of like Feldman and Peterson type of verifiable secret sharing and distributed key generation. Intuitively, in a successful execution of the verifiable secret sharing, we will all get secret shares of some Peterson committed value. And the only way that this protocol can fail is if a dealer sends a bad ciphertext, which we have a mechanism can be caught pretty easily in that you can just open up whatever ciphertext you received that was badly formed. And you can build, given this VSS as a black box, you can build distributed key generation, which just unmasks the Peterson commitment, like prices apart the secret and the message from the Peterson commitment that was sampled in the VSS. Yeah, that's super high level. I didn't really go into it because this isn't where, or this isn't really worth focusing on for this talk. All I want to say is that overall we get, with 3 broadcast IA rounds, so 3 rounds over broadcast, where broadcast is instantiated, as I mentioned earlier, and no like cryptographic machinery in terms of PIA or OTA or anything, we get a threshold ECDSA protocol in the honest majority setting that also achieves identifiable abort. And importantly, runs only over point-to-point channels. Right, so in conclusion, dishonest majority protocols are in a lot of ways inherently susceptible to denial of service. And while you can get around this by making external assumptions, it's also worth thinking about how you can keep the assumptions contained to within the system. So no external broadcast or anything like this. Yeah, so we define this notion of broadcast that seems to be kind of tight for identifiable abort. In particular, you're able to catch parties that are silent, that don't speak when they're supposed to. We showed that this notion is provably impossible to achieve with a dishonest majority. And we give a simple construction over point-to-point channels when there's an honest majority available, which I argue is a reasonable assumption in many scenarios. So starting with verifiable secret sharing built on this broadcast, we build DKG, and then finally ECDSA signing itself. And all of this is pretty simple in the honest majority setting. It gets around a lot of other issues. And yeah, we're still in the process of implementing this. We estimate that it's a few orders of magnitude lighter than signing with a dishonest majority, which is generally falls in line with our understanding of how honest majority versus dishonest majority works in MPC. And stay tuned for benchmarks and our full paper. Okay, thanks.
Thank you so much, Yash. Are there any questions from the audience? Yeah. Go ahead.
Shall I just go ahead?
Yeah.
Yeah. I wanted to ask, what is like, where is this like used? In what context is this relevant?
Like ECDSA signing or like
The honest majority.
The honest
What you
Oh, yeah. So if you have, for instance, this network of nodes, and assume for a moment that you don't back up your signing key anywhere else, you really rely on this network to keep track of your key, right? I mean, of course, this assumption is not always true, but like assume that you really don't want to bring up any cold storage where the key is stored in a single place, right? So the network should have should have enough shares of the key to reconstruct the key if you want it, right? Because of these 5 nodes that I showed, for instance, and if you have 2 parties that are corrupt, right? That's it. Like you cannot have access to these shares of the key anymore. So, or whatever, 3 parties. If you have 3 parties signing, of which you want security to 2 corruptions, you cannot assume that you will get these 2 shares of the key if you want, like when you want it. So you need to have enough redundancy with these extra parties to recover the key when you actually want.
I think it's just assuming, not assuming an adversary, but just redundancy, right? I think that's a generalized use case.
Yeah, I guess it's adversarial redundancy against adversarial attacks. But yeah.
Anyone else? Yeah.
Sorry, I'm curious. Have you considered whether there would be any difference if the only thing you need is identifiable words for signature aggregator?
I'm sorry, I missed the last part. What about the signature aggregator?
Are there any sort of implications or relaxing of this honest majority thing if the only thing that you need is identifiable words for signature aggregator? Like if there is an omission or commission fault, you just need to detect it when the signature aggregator.
Yeah, then you had to trust the signature aggregator. If I'm understanding your question correctly, you're proposing a model where there's a signature aggregator that receives everything and is responsible for the output, right? So imagine that there's some party who's supposed to send a message to the signature aggregator for it to finish its job. Now the signature aggregator can say, that party didn't send me the message, even though it did, and like blame that party, right? So you're sort of making this assumption that you trust whatever the signature aggregator says in terms of who's speaking to it. So that model is used, but and it makes things easier if you're willing to assume that you can trust the signature aggregator. But for the sake of
I understand what you're saying. In fact, that the last paragraph of identifiable abort section of Lindell 22 does this coordinator
exactly.
thing. But like signature aggregator here could just be any other party. Like it need not be an external entity, but you only need to detect an identifiable abort in the aggregation phase, not in like round 2 to round 3.
Oh, okay. So I think I understand your question. It's that let's say you have a 3-round protocol. Can you detect, and you're okay with the first 2 rounds, and then the last round you want to detect who sent you a bad share? Yeah, I guess that's a subset of this. And your question is, does it become easier? I think that the last round message also kind of depends on protocol context. So at least for ECDSA signing, I don't think it becomes easier.
Okay, great. Thank you so much, Yash. Let's take a quick 10-minute break, and after that, George from Miston Labs will tell us all about their new consensus, which I'm very excited about.
Yeah, that's live.
Omri is not here.
Oh, this is the bell.
Yeah, okay. Yeah, the bell is rung. Omer, let's go. Great. So we'd like to move forward. We're a bit behind schedule. I'm very excited to invite George from Miston Labs, the co-founder and chief scientist who co-founded SUI Network, to talk about their new consensus algorithm, Mysticity, right? That's the pronunciation. Amazing. So yeah, thank you, George.
Thank you for the invitation. It's a pleasure being here. It's the first time actually I'm talking about Mysticity in public, and I'm glad the audience is more technical than other audiences, so I can actually really go into a little bit more of the detail, even though we don't have time for the full details. This works? Okay, so I am indeed George Danezis. I'm a co-founder of Miston Labs. Before that, I was with DM. I'm still a professor at UCL here in London as well. And today, we're going to talk about one specific aspect of blockchains, right? So there are many ingredients you need in order to build a blockchain, and to some extent, many of us who have built kind of blockchains have kind of looked at many of them. You need some way of sequencing transactions in common, or in general, more generally, try to make sure that there are no inconsistent transactions. Then you need some kind of way of executing either that sequence of transactions or the set of consistent transactions. Then you usually need some crypto magic to do a bunch of things, either to verify things, to prove things, or to hide things, depending if your blockchain also does some privacy or not. And then you need to sprinkle on top of all of that some tokenomics in order to make sure that you incentivize good things and disincentivize bad things, broadly speaking, right? And if you have all of these ingredients, you usually make a new blockchain, right, depending on how new they are. Today, we're just going to deal with sequencing, right? I'm going to talk about Byzantine consensus. And first, let me give a very brief and an opinionated history of Byzantine consensus, right? Because it is one of these primitives that is very old, actually, much older than many in the room maybe, and not quite as old as me, but nearly. And it has seen really a resurgence in the last few years. Like many other kind of cryptographic techniques that people thought were of theoretical interest, now actually we're engineering with them, which is fantastic. So in 1985, basically, a bunch of people from the theory side proved that consensus is impossible. Okay, this is a good starting point for any kind of inquiry, and this is not just about Byzantine consensus. Byzantine being in the context of some parties actively misbehaving. They actually prove it's impossible even if some parties crash. In fact, even if one party crashes in a big group of people, these people cannot agree on a common value. Now, this is not a very helpful result, of course, because from our intuition, we tend to be able to agree on something. So indeed, there were relaxations on that model that were possible in order to make consensus broadly possible as we understand it, right? And I think that the most significant result and the kind of pinnacle of the early work on consensus, in my view at least, and as I said, it's my talk, so it's opinionated, is practical Byzantine fault tolerance by Liskov and Castro in 1999. This is a seminal protocol because if you look at it, the latency is great. All the great ideas are already there. It's using modern cryptography, at least digital signatures in some of the versions, right? And they show that you can actually do Byzantine fault-tolerant consensus. You can tolerate a third of parties being actively malicious. Safety is unconditional, right? And in the asynchrony model, conditional on cryptography working, of course. And in order to get liveness, you just have to make some loose kind of like synchrony assumption, like eventually messages arrive within some time delay. That was fantastic. And then what happened is we enter what I call the dark ages, right? The dark ages is just this loss of interest in the broader industrial and research community about this topic. That doesn't mean that there were not very interesting papers published in that time. There were. Actually, some very interesting results were published in that time. It's just that basically the mainstream community around both cryptography and, broadly speaking, computer security, network security, was just openly mocking basically that field as being of, largely theoretical interest. In fact, there is a login article that is called "The Saddest Moment," and it says, watching a presentation on Byzantine fault tolerance is similar to watching a foreign film from a depressing nation. Okay, people were actually openly mocking people who cared about Byzantine consensus because they were like, look, we have these data centers, right? Everybody is trusting these big companies to process data in the data center. What's the problem, guys? Like, stop, thinking about, being paranoid and thinking about Byzantine parties. No one's Byzantine here, right, in the room. Like, what's your problem, right? And of course, that topic became again relevant when blockchains became prominent. Tendermint, I think, and the Cosmos ecosystem is the first large ecosystem that really put Byzantine consensus on the map as a way of doing blockchains. This is pretty cool, and we owe a lot to that ecosystem for that. And then Dalia Malki and collaborators created and designed Hot Stuff. And Hot Stuff was actually adopted as the consensus system in Libra DM as part of Facebook. I was part of that adventure, and it kind of became the kind of go-to protocol for people who want to build blockchains based on Byzantine consensus for a while after that. So that's pretty cool. Byzantine consensus is back in vogue. This is what we're doing. And in parallel with Hot Stuff, and actually as a result of us in Libra DM looking at Hot Stuff, we also started developing ideas of how to do consensus based on directed acyclic graphs, right? And in fact, it did came out of some of our frustrations working with Hot Stuff at the time as part of DM. So let's look a little bit at the kind of traditional, and I call traditional, like the kind of Hot Stuff Tendermint-like consensus versus this DAG-based approach, right? Because we're going to spend some time looking at it. So in traditional consensus, there is a leader that plays a very active system role, as I call it, right? The leader collects transactions, determines a valid sequence of transactions to augment the sequence that already exists there, and then broadcasts these blocks around, maybe gather certificates, and helps the protocol progress from a systems perspective, right? They are a very active participant. Now, this is great. Hot Stuff shows that as a result, communication overall in the system is linear, so it scales in the number of validators. That's pretty cool. Has low latency. You can basically do it with few round trips. That's great. But the problem is that leader, because there are system participants, very often can act as a bottleneck, right? Everything goes through that leader. The leader has to use a lot of bandwidth to share with everybody else all the transactions and the proposals and all of that. And if that leader fails, things kind of stall, if you want, right? I mean, things wait until a new leader is elected, accepted, and then the protocol can resume, which is cool. So we're like, that's not really great, right? So we started thinking, okay, what kind of alternatives there are? And we started developing this line of work, Narwhal, Tusk, Bullshark. Largely my colleagues developed Bullshark at the time. That takes a slightly different approach, right? In DAG-based protocols, what happens is all validators that take care of the consensus kind of are acting symmetrically, and there is a leader that only basically plays a logical role to break symmetry, as I call it, right? Everybody produces blocks, everybody links to previous blocks and other people's blocks. Then basically the DAG of blocks contains transactions, and then what happens is that every so often you look at that structure, right? You use some logical notion of leaders in order to decide how to break symmetry, and that leads to basically a sequence, and we will see about that in a second. Now, what are the advantages of this approach, right? The advantages are that everything from a system perspective is symmetrical. All resources are used symmetrically. Networking, CPU, storage, everybody is using all of these resources symmetrically, and as a result, no one's acting as a bottleneck for each other, which is great, right? There is also a separation in a Narwhal-based protocol between sequencing transactions and actually performing the consensus, agreeing on the sequence, which means that if there are failures, even the leaders are not there to play that logical role for a while, throughput doesn't suffer. You keep basically agreeing on transactions, and then when a leader comes, you just commit a whole bunch of them without actually loss of throughput. You just basically increase latency, which is pretty cool. However, There is one downside to these families of protocols. They have higher latency. They have higher latency than the traditional hot stuff, PBFT even, like protocols. Like how much more latency, and what is the problem that creates more latency? Let's look at that for a second. So this is a graph from Bullshark. My colleagues are authors of that. It is basically a partially synchronous variant of a narwhal-based consensus. And we can see here this very lovely graph, which plots basically the throughput that can be achieved on the x-axis in thousands of transactions per second, and the latency on the other side of commits in seconds on the other side. And in orange, we have hot stuff for different numbers of nodes. And we can see that hot stuff, can basically achieve latencies of, a little bit higher than 1 second. Now, the throughput is much lower than DAG-based protocols. It peaks at 50,000, etc., for very low latency. But that's pretty cool. You can get a commit pretty much every second. That's nice. We would like that, right? On the other side, the kind of Tusk, which is the asynchronous version of Narwhal consensus, and Bullshark, which is the partially synchronous version, these things can really scale up in terms of throughput. You can really pump those transactions into like hundreds of thousands transactions per second and beyond, right? But look at the latency, right? Tusk, which is a fully asynchronous protocol, which is pretty cool that we can do this at all, right? For a while, we never thought these things would be practical, has a latency of 3 seconds. So you lose 2 seconds over hot stuff. And Bullshark, which is a great improvement, still has kind of around 2 seconds latency. That's not great. Now, you can do a few things to reduce, a little bit here and there, and great engineering progress has been made, but, those kind of gaps remain, if you want, right? I mean, you can improve all protocols and they kind of move up and down a little bit. So, can we have nice things, right? Can we get basically very high throughput and latency that is close to the latency of traditional kind of hot stuff like protocols? That's really the key question that we set to answer. Now, while we were working at DM was using hot stuff, and it's difficult if you work in a big company and they have like a system that is working to convince them to totally change their consensus, right? It's a sociological fact. We said, well, maybe we could just use narwhal-like dissemination of transactions to get really high throughput and use hot stuff on the other side for the agreement, right? And maybe we'll get the best of both worlds. Sadly, this is not quite the case we found at the time. This is again from the original Narwhal and Tusk paper. When we basically use Narwhal with hot stuff on top of it in order to do consensus, again, we're stuck at 1.5 seconds because Narwhal adds some latency to hot stuff. It is, again, 1 second to half a second more than just using kind of batched hot stuff, which is the baseline we evaluated against. Better than using Tusk at the time, so that was cool. But effectively, Bullshark has nullified that difference. Like doing Bullshark is the same as doing Narwhal with hot stuff. So that composition doesn't solve the latency problem. It doesn't bring latency down to the 1 second range we would like to have. Okay. So, what makes Narwhal-based consensus slower, to put it bluntly, right? And we have really identified 3 sources of latency, right? The one has to do with DAG certification. The other one has to do with how the leaders are structured across rounds. And the third one about the fact that there is a single leader. I'm reading it in a different order. And basically with Mysticeti, we are reimagining DAG-based protocols to try to eliminate these 3 bottlenecks. That's basically how to think about Mysticeti. So let's actually look at Narwhal and try to look at these 3 problems one by one. Now, on the Y direction, we have 4 nodes. On the X direction, we have the blocks they generate over time. This is how to read these graphs, even though they look like some religious ceremony every time. So what happens is in Narwhal, each node produces, each validator produces a block. The block, let's say the yellow block, each of the blocks basically is certified, means that you share it with two-thirds other parties, they sign it, they give you back a certificate, you broadcast the certificate. That is what this little circle does. And then you basically broadcast it to all the other parties. And the blocks basically contain two-thirds links to back blocks from the previous round. That's the kind of like logic of Narwhal. And then you perform that protocol round after round after round. This is just a Narwhal structure. And the bull shark rule on top of that, which is simple, so I'll present that, is that every even round, you basically agree on a leader. This is like a predetermined schedule of a leader, right? Let's say the first round, 0, you pick the first node, then the second node, the red one, then the third one, the green one. So every even round has a leader that you have predetermined. And then what you're looking for is this shape that I have highlighted in red, right? If you see that the block of the leader, that big red block, is in fact contained on two subsequent, 1/3 plus 1, technically speaking, subsequent blocks that are certified in the next round, okay? Then you have a commit. So you know that this will never change. Everybody will eventually observe it. You can commit everything behind it, which are all the ones that I have basically behind. So agreeing on that red block commits all the nodes that have, the blocks that have one after that. And now the same applies, of course, to block 2. You can see that block 2 is actually contained in 2 blocks in the next round. And that, again, commits all the previous blocks that are connected from that block. These are the blocks that do 2. Anything that was committed before with 1 is already committed, so we don't recommit it. It's already in the sequence. OK? This is roughly how Narwhal works. Now, first of all, notice that you might, the rounds are not just like sending a block, right? I mean, they involve having a block, certifying that block, sending and including the block in next, basically, blocks, right? So that's basically at least a round trip and a half of delay. That's one problem. Now, also notice, of course, that you might get unlucky. You might get really unlucky. Look, that node, that block in the first round there, just after the yellow one, it takes a while for that block to be committed. Right? In fact, that block there, the unlucky one, only gets committed here. Right? This is when I observe actually that I have 2 blocks that contain 2 that goes and commits all of that. Right? So the inter-block timing is longer because you have to certify things, and you might actually get very unlucky and have some transactions that are just not connected for a while to a commit. Okay? This is a problem, of course, because if you have a transaction there, you're like, why is my transaction waiting there? There have been commits on the way, but I just was not included. Okay, so one thing that we do in Mr. SETI is we try to reduce the time between rounds. We're not going to certify anymore. We're going to remove these little circles, okay? Now, as I said, this big line of 2s, right, this big delay between that unlucky block and its commit, feels a little bit unnecessary, right? And it is, in fact, unnecessary. If you think about it, we picked the red block here as a leader that then gets committed. But honestly speaking, that top block here, that is the blue 2 there, also has a lot of support. It is also included into subsequent rounds. Actually, it is also going to be seen by everybody eventually, right? So wouldn't it be nice if we could actually commit more things here that definitely will be seen by everybody who commits in the future, right? And we could. It's just that we don't do it, right? In traditional kind of bull shark. So what we're going to do in Mr. SETI is to say, well, actually, we're not just going to have one leader every time we're trying to commit. We're going to commit multiple ones because actually we might get lucky and more things can actually be committed during a particular round. Okay? More things that are safe and that have support can be committed during a particular round. Finally, notice that, again, in Bull Shark, we have leaders every even round. But why is that, right? Let's take, for example, an odd round, this one, right? This particular block, again, is connected to two others, right? Everybody is guaranteed eventually to see it and to agree that it is part of the DAG. There is no question about that. That's what these two links guarantee, if you think about it. But we're not actually using it to commit anything. We have to wait here and subsequently in order to actually commit it, right? Because we have picked to actually have leaders every 2 rounds. Wouldn't it be nice if we can actually make a decision to commit every round? And this way, maybe we will commit this sequence of 2s that otherwise would have been committed here already here. Okay? And this is, again, what we're going to do in Mr. SETI. We're going to commit every round, or try to commit every round, in order to, again, reduce the latency of unlucky transactions that are in these blocks. Okay? So, as I said, Mr. SETI is the solution that just gathers all of these insights into just one protocol, right? And tries to apply these 3 learnings, if you want, into one consensus protocol and improve on narwhal-based protocols. Now, what I say is that consensus is a little bit like hummus. Many people try to make it, but the best one comes from Israel. Okay, in my experience. It's the same with consensus protocols. If you look at the sequence of consensus protocols that I talked about, one of the authors is usually Israeli for reasons that I don't entirely understand. So when we came up with Mr. SETI, we're like, oh, wow, we came up with a good consensus protocol as far as we're concerned, and we don't actually have an Israeli co-author, right? It's a bit strange, or do we? I don't know. But then what we discovered, right? What we discovered is that actually Edith Kedar's group in Israel has actually discovered the core of the protocol already, right? So we actually did some parallel work there. So all is good. The best consensus protocols still come actually from Israel. So this is how Mr. SETI works. And actually, this shape is in Edith's paper if you read it. So how Mr. SETI works is, again, all the validators build blocks with transactions and backlinks every round, okay? But now they don't certify them, they just sign them. They sign them and send them on, right? So this block is signed, sent on. This block waits for a few blocks, 2f+1 blocks. It's signed, it's sent on, etc. Okay? That already reduces the latency between within a round. And then what we're going to do is we're going to pick many leaders, and we're going to commit every round. But here I'm going to show you just one commit, like how is one commit decided? And the commit needs to have basically this structure in order to be decided, okay, in Mr. SETI. What we're going to say is, okay, I'm going to try to decide this block as a leader, okay? And we will see that we have many different leaders in a second, but let's just consider that one. What I'm going to look for in the DAG is, in the next round, I want to have 2f+1 nodes that vote for that block by including it into their blocks. So these are votes. And then in the next round, I want to have 2f+1, 2/3 basically of the blocks, certifying that block by linking to 2/3 of votes for that block. And if I see 2/3 votes and 2/3 certificates, I know that this is going to be in every sequence subsequently, and I consider that block committed. I also can make the negative statement, namely, if that block is missing, if it is not there, and I do see 2/3 of nodes not including it in their block, and then I see 2/3 of nodes including the votes that the block has not seen, I can also decide that the block will never be included. Okay? I can basically decide both that the block will be included or that the block will never be included. Okay? And these are the two good cases where I can actually move and make a decision. Now, This is easy. If you see that shape, either with the block present or the block absent, you can decide that the block is the next agreed on leader and commit everything in its history. The bad case, of course, is if you don't see that shape. What happens then? Then you have to continue the protocol until something subsequent is decided, and then look back and try to commit or not commit basically that block. We are not going to go through that case because it's painful, and it doesn't give us as much insight as possible. Okay? So besides theoretically being an interesting protocol, that protocol also has advantages from a systems perspective. There is a single message, the block. It just is broadcast around, and really the delays are quite uniform in order to make it work in partial synchrony. So that's all good. And then what we do is we take that simple commit rule here, that simple shape, and we just say, well, instead of actually having a leader that we decide every 2 rounds, right? What we're going to have is multiple leaders potentially. So here in the first round I have 2 yellow leaders. In the second round I have two red leaders. In the third round I have 2 blue leaders and then 2 green leaders. So every round has multiple leaders, and we basically designate potential leaders in every single round. And as you can see, in the happy case that all the leaders are committed, basically we just commit basically as we go. Why is this blue? Oh yeah, it's blue because it's connected here. Good. It's good. The color coding is fine. Yeah? So as you can see, the delay in the happy case is much lower than having this very long kind of like potentially delay to commit. In fact, we show that this matches the kind of PBFT commit latency, which we believe, without kind of any optimistic tricks like everybody's honest and acting, is as good as it gets. We don't have a theorem about that. We would love to have a theorem that you cannot do better than this. Maybe you can, and that'd be exciting. Cool. So what does that all lead to? It leads to good things, right? As we said, here we have the same graph as we had before, right? Hot stuff is that red line that actually has outliers that are close to 1 second. It doesn't actually have very high throughput, sadly. It kind of saturates, even though it saturates at around 50K normally before the latency becomes too big. Narwhal and bull shark, as we have said before, can scale up the throughput, but are around 2 to 3 seconds. We actually have improved a little bit our implementations since then. This is narwhal with hot stuff here. And this is bull shark at 2 seconds as before. And Mr. SETI, let's not take that line. That's a 10-node line. It's not particularly interesting for a blockchain. But the 50-node line is actually more interesting for a blockchain. As you can see, for even 100 transactions per second, these are half a kilobyte, we still maintain a latency under basically a second. For more reasonable loads of less than 50, we actually can have sub-second wide area network latency using these improvements. That's cool. That shows that you can really actually have sub-second latency and still scale up your throughput a la Narwhal. This is basically the result. Now, there are a few details here and there. We are actually planning on integrating this consensus protocol as the consensus protocol of SWI. SWI actually has a fast path that allows you to do transactions that don't need consensus quite fast, and then basically agree on a sequence to checkpoint, etc. It turns out this is great because you can have lower latency. This is not so great because now you have to actually certify each transaction individually. So in the paper, we actually show how to integrate that fast path into Mr. SETI as well, in order not to have to do as much signature verification, which is a pain. We can also reduce a little bit the latency of the combined fast path and consensus. We can also do auto and lock in case, in some cases, basically the fast path locks objects, etc. So we kind of worked in order to integrate a fast path as well as a consensus path into that. Now, one additional thing that Narwhal does is it dissociates transaction dissemination from consensus. namely you send blocks of transactions and then you agree on them, we actually took that out. This separation of transaction dissemination and consensus added one more round trip of latency, and we have not seen yet a blockchain that needs that, right? Which means that, sadly, our blockchains are not widely enough used to need hundreds of thousands of transactions per second, and until then, we can actually serve the needs of a blockchain just by having one, basically, instance that basically inlines the transactions. So we did away with that. There are many strategies. We can reintroduce that in order to get higher throughput than hundreds of thousands of transactions per second when our systems take off. This is it. This is my conclusion. The conclusion is we can have DAG-based consensus with the symmetry and the system simplicity that they bring at sub-second wide area network latency. We can also integrate fast path into them if we feel this is still useful. And we can have high throughput, the kind of high throughput that these DAG-based protocols provide. And they use very little CPU power. They're not like very fancy cryptographically. They just use a ED 25519 signature. So you don't really notice that on your validator. You have a lot of space to actually do execution. We have a tech report out. Feel free to read it in its full glory. And thank you. Very happy to chat with you.
Thank you very much, George. If there are any questions from the audience?
Up more than 50 nodes.
So we ran out of money. So, we ran out of budget, I should say. Doing these AWS experiments with more than 50 nodes, because you have to do lots of repetitions for each point as well, gets really expensive after a while. And, people are like, well, when we productize it, we will actually benchmark the production thing. I think for the research is fine because we're comparing also with the previous work that has 50. So that's basically the truth of it.
But there's no reason to think it will scale not in a good way.
So it will scale the same way as Narwhal does. There is a quadratic element to all these Narwhal DAG protocols in terms that all validators need to send their blocks to everybody else directly, right? So it's not going to scale to thousands, but it will scale the same as Narwhal.
For SUI with 150 validators.
Yeah, it will do hundreds, which is where we're thinking SUI. Sub-second should be the case, yeah. Like the block metadata should not actually, really touch the latency too much, yeah.
Someone else wanted to?
Yeah, it was very similar because I noticed that the 10 node and the 50 node design separate faster for MPC than the other two.
Yeah, yeah. I think it is the quality of the implementation. So we have literally spent the last 5 years optimizing our hot stuff, Narwhal, Bullshark implementations, and we always compare to those. The Mr. Set implementation measurements were literally done, on the kind of new artifact. There is no reason for that kind of smooth way up, if you want. There should really be a very flat kind of like, on the latency graph that then shoots up at some point, because at some point the quadratic thing becomes dominant, right? That's the way to think about it, that while you're transferring data with some overhead, most of your overhead is transferring the data. At some point, you reach a scale where actually the transfer of data is not the overhead anymore. Your overhead is the overhead, not the bottleneck. Your overhead is the overhead, and that should shoot up at that point. So there is no reason for that gradual degradation. Yeah.
Great. Thank you so much, George. It was very interesting, and thank you for talking to us about necessity. I want to invite Michal from Nethermind to talk about the difference between security proof of snark and their actual applicability, right? I'm getting it right?
Yeah.
Yeah? Okay. So, Michal from Nethermind.
Okay, does it work? Okay, I think it does. Perfect. Okay, yes. So, Hello, my name is Michał. I'm head of research at Nethermind, and today I would like to talk about the security difference between what we see in a scientific paper and the protocol that actually we get to deployment. So there are some steps in preparing the protocol for practical deployment that actually reduces the protocol's security, and that's what I would like to discuss today to make you maybe more aware of some caveats of security analysis. Okay, so let's start with like super basic primer and on zero knowledge, and let me introduce some notation. So in zero knowledge proofs, we have these two parties, prover, verifier. Prover gets some statement X that that belongs to some language L and wants to convince other party, verifier, that that's true, that X indeed belongs to the language. Verifier knows X itself, but does not know the additional information W, called the witness, that certifies that X indeed belongs to the language. So for example, X could be some statement like circuit C executed on input A gives B, and W could be some private information included in the circuit. And we have a number of properties that we require for a proof system to have. We have completeness that tells that honest verifier always accepts a proof from an honest prover. We have soundness, which is much more interesting property, which tells that dishonest prover, and during this presentation I will use this P star notation to denote provers that are dishonest. So dishonest provers should not be able to convince the verifier to accept some false statement except with some negligible probability. We have a stronger notion, knowledge soundness, that basically states that if the prover was able to convince the verifier on the veracity of some statement, then prover knows the witness corresponding to the statement. And finally, we have zero knowledge, which basically tells that the verifier learns nothing about the witness except, the verifier learns nothing new except the veracity of X. Okay, so now, how snarks are built. So usually snarks are built in a quite similar manner. So everything starts with PIOPs. PIOP stands for Polynomial Interactive Oracle Proof. And this is idealized model that is super easy to analyze because of the very nice algebraic properties. So here we introduce like magical third party, which is an oracle. And prover sends its proof as polynomials sent to the oracle. So prover does not communicate directly with the verifier. It sends some polynomials to the oracle, gets some challenges back from the verifier, and replies with even more polynomials. And at the end of the day, the verifier picks some evaluation challenges, here Z, and asks the oracle to get polynomial evaluations at Z. And then with that polynomial evaluation, it decides whether to accept or reject the proof. So the oracle always like this magical party that always tells truth here. The biggest problem with this is like we don't have such oracles in real life. And the second is that these proofs are really, really huge. So if you have like a computation of size 2 to the 20, then these polynomials also are expected to have like 2 to the 20, say, field elements. So the polynomials are of the size of the computation. So how we get rid of the oracle? We use polynomial commitment schemes instead of polynomials themselves. Right, so instead of sending polynomial, we send a commitment to a polynomial, like very short digest. And at the end of this conversation between prover and verifier, when the verifier sends the evaluation challenge to the prover, prover replies with evaluation along with proof that the evaluation was computed correctly. So now the problem that remains is that this protocol is interactive. And this is an issue because we don't want to deploy in practice interactive protocols, right? When you have your favorite ZK rollup, you don't want to talk with, we say, Ethereum to get the challenges from there. You just want to post the proof and be done. So what you do Fiat-Shamir transformation, where you basically replace verifier's challenges by random oracles. So you send information, partial transcripts of your conversation to this idealized third party, random oracle, and get random challenges from there. And this, importantly, this transcripts needs to be computed in a quite carefully because there are some vulnerabilities that come when you do when you don't include some information in these queries. Finally, random oracles don't exist. So instead of using random oracle, we use hash function, right? So now here the prover computes all the challenges himself by making queries to some random oracle, by computing the challenges as evaluations of a hash function. Okay, so there's a number of questions that come when we go from PIOP to concrete snark. So first of all, our first step introduce polynomial commitments. All right, so we need to analyze like how secure the polynomial commitments are. Like, do they have all the properties we need? What's the security laws that come with using polynomial commitment instead of this idealized third party, the oracle? Now, we replaced the interaction with random oracles. So the question is whether this introduces some new attack vectors. And this will be the main topic of my talk. Finally, we replace the random oracle with hash function. And so the question is like how good the replacement is. Okay, so let's get into Fiat-Shamir transformation security. So on the left-hand side, we have an interactive protocol where a malicious prover tries to convince a verifier about veracity of some false statement. On the right-hand side, we have the same protocol, but with Fiat-Shamir transformation applied. And the intuition why Fiat-Shamir transformation introduces some security loss is following. If I'm a malicious prover and I talk with verifier, when I cannot reply to some challenge, and that's the expected result because I don't know the witness. The statement does not belong to a language. When I cannot reply some challenge, the only thing I can do, I can start from the beginning of the protocol, right? Because otherwise the verifier will just reject. On the other hand, if I have a hash function and I compute challenges on my own, then when I see a challenge that doesn't fit my needs, that I don't like, I can always get back some points in the protocol, change something in my proof, like re-randomize the proof, for example, and try again, such that I have a new challenge with every query. And in that way, I have bigger chances of getting challenges that fit my needs, that would make the verifier accept. So here, let me introduce lucky set and lucky states. So lucky set is a set of challenges sent by the verifier, such that if I, as a malicious prover, get a challenge from that particular set, then I know how to make this conversation further on such that the verifier accepts. Okay? And I say that at this moment, when I get the challenge from lucky set, the protocol gets into lucky state. And the verifier accepts only if the protocol at the very end of the conversation is in the lucky state. So to introduce some notation, let's have epsilon, the probability that P star makes V accept a false statement. Eta will be the probability that pi gets into the lucky state in a single round. So the probability that during k rounds, pi doesn't get into the lucky state is 1 minus eta to the k, like the interactive case. So finally, we can express our epsilon as 1 minus eta to the k, which is roughly k times eta. So this is without rewinding, right? This is the interactive case. So okay, so let's go into rewinding. Let's see what happens when we allow adversary to rewind and to check like new possibilities. So here I will also introduce Q. So Q will be attacking budget. So basically it will tell like how many times I can try to rewind. So okay, again, 1 minus eta is a probability that P star does not get a challenge from a lucky set in a single round. Then we have rewinding. So I divide my budget for rewinding as follows. I have Q budget. I have K rounds. So in each round, I'm willing to spend like Q by K. I'm willing to do like Q by K rewinding, right? So this probability that I'm not getting into lucky set drops to 1 minus eta to Q by K. Finally, I have K rounds. So I multiply. So I have product from I equals 1 to K of 1 minus eta Q to the Q by K. Okay, so the security of this Fiat-Shamir transformation is actually much worse because it's eta times Q. Previously, we had eta times K. So the question is, like, how big is Q? So let's take, as an example, epsilon equals 2 to the minus 100, okay? So this is the security of our interactive protocol. So it looks pretty decent, okay? But then let's say that we utilize the Fiat-Shamir transformation. So what's the Q? As an illustrative example, let's look at Bitcoin network, at how many hashes it can compute. And then let's use the number of hashes that are computed by Bitcoin network as our measure of how many rewinds the adversary can make. And this is, of course, like computing hashes is a bit different task than what we are asking for, but there are some big similarities because, well, when I rewind, I basically what I do is that I have some message that I send to the verifier. I randomize the message and I compute the challenge that comes from randomization of this message. And that's very similar to what Bitcoin miners do. They need to find the nonce such that if I add this nonce to a Bitcoin block, the hash of that block has certain properties, right? So there is a lot of similarities here. So with Bitcoin network being able to process 60 million terahashes per second, they process around like 2 to the 85 hashes per day. So with our formula, we get that epsilon is like 2 to the minus 100 times q, and this is like 2 to the minus 15, right? So that's our probability that during a single day, our protocol will be broken. So the security difference actually here, when the Fiat-Shamir transformation got applied, is huge. Okay, so we can do better. So we can actually bootstrap the security of our protocols by utilizing parallel repetition. Okay, so parallel repetition, as name suggests, means that my protocol is repeated in a parallel fashion. So the prover now gets into interaction with verifier in like two protocols. I don't know the maximal probability that the protocol enters a lucky state. I have k number of protocol runs, and t is number of parallel repetitions. Okay, so when I have that's an interactive case, right? For a bigger number of executions. So in the interactive setting, when I have bigger number of executions, the security actually grows to eta times k to the k. And for some concrete example, let's set t equals 8, k equals 4, eta equals 2 to the minus 20. So if I have a protocol that is secure with eta equals 2 to the minus 20, so it's like really not a secure protocol, right? Then after repeating in parallel 8 times, I get the security of 2 to the minus 144, which is significantly better. So for Fiat-Shamir transformation, actually that's not the case, and let me explain why. So now I will be dividing my attacking budget into these 2 runs of the protocols. And my strategy will be as follows. So the prover will send the first message, okay? We'll get some challenge, B1, and if this challenge doesn't belong to a lucky set, then I will rewind, okay? And I will repeat this procedure up to q by 2 times till I get B1 that belongs to the lucky set. Okay, and then what I can do is that I say freeze the first transcripts in both of the protocols. So here, the transcripts actually depends on each other, right? So the transcript 1 on the left-hand side is the instance and the first prover's message. And transcript 1 on the right-hand side is actually what the prover got from, it's the transcript from the left-hand side with some additional information like identifier that it's the second interaction, for example. The challenge I got, say I spend this budget q over 2 to get like a good challenge from the lucky set, and then I compute the second challenge, and this second challenge B1 on the right-hand side contains all the information that was exchanged before. So it contains tier 1 from the left-hand side, tier 1 from the right-hand side, and also B1 from the left-hand side. And what I do is that I get this challenge. I send transcript 2 in the first round, in the second round. In the first round, I'm already in the lucky state, so I don't need to care about anything here. And in the second, I'm still not in the lucky set. But what I can do, I can take the challenge B2, and if I don't like it, I can rewind to get a new transcript tier 2, what also would give me a new challenge B2. Okay? So the power of this attack comes from the fact that I can solve the first instance, then get into solving the second instance, and somehow solve them independently, breaking this parallel repetition problem. Okay, so let's analyze the lucky sets in the Fiat-Shamir transformation. So similarly, we have yes. So we have 1 minus eta, the probability that I'm not getting into a lucky set in a single query. Then I need to get it to the q by t power, because that's how many trials I'm willing to make. And then I take 1 minus eta to q by t to express the probability that I'm not going to, sorry, the probability that I'm entering lucky set in this first iteration, the first track of the protocol, right? And I have t iteration, so the end result is q by t times eta to t. So for a concrete example, when I have t equals 10, sorry, it should be t equal 8 actually, and k is equal 2, and q is 2 to the 20, eta is also like 2 to the minus 20. So q here is like really small, but the end result is 2 to the minus 30. So the security dropped from 2 to the minus 44 to the minus 144 to 2 to the minus 30. And actually, there is more caveats when we use Fiat-Shamir transformation to implement our protocols. So there's a result by Trail of Bits, also mentioned this morning by Benny Pincus. So what Trail of Bit realized is that a big number of cryptographic protocols that were used in Web3 don't have Fiat-Shamir transformation implemented correctly. So there were information that were missing in the transcripts that allowed researchers from Trail of Bits to actually break them. And we have like some good examples here. We have like ENG Bank, we have Dusk Network, ident-free consensus. So TLDR is that some implementations of Fiat-Shamir transformation include all the necessary information in the hash function. And one more attack that was very recently published by researchers from Open Zeppelin is they realized that some implementations of Plonk, which is a very, very popular snark-proof system, don't compute the challenges correctly, meaning they don't pick the challenges from the right set. And that also allowed the researchers to break these protocols. So the conclusion of this talk is be careful when you fine-tune your parameters. When you cannot only look at the security parameters for your interactive protocol, you need to account for all the changes you make in your protocol to see the concrete security of the protocol at the end of the day. Thank you.
Thank you very much, Michal. Yeah, question.
What did ING Bank use ZK for?
That's a very good question. I have no idea. But to be honest, I'm quite happy to see that name that they are using ZK, right? Even though they don't use it properly.
Anyone else? Great. Thank you so much, Michal. Our last talk for today, last but not least, is Ellie from Espresso Systems. And she will talk about threshold encryption to prevent MEV, right? Yes. Yeah. Great. So thank you, Ellie. Yeah, it should work now.
Okay. Oh, there we go. Okay. Hi. I'm Ellie. I am the lead researcher, and I'm also an engineer at Espresso Systems. And today I'm going to talk about encryption-based front-running protection in the Espresso sequencing platform. All right, so let's go. So I quickly just want to mention that this is work that we've been doing jointly with Shutter. So we actually have a blog post on this. But yeah, so this is a joint piece of work. Okay, so we have a problem, which is front running. And the problem with front running is basically that builders and whatever searchers, they can see the user's transaction data and they use this against the user. You know, you front run, you sandwich, etc. So you have a possible solution, which is, okay, let's encrypt our transactions. That will prevent the exposure of this information and prevent us from being front run. And then also, maybe this provides some censorship resistance, which is another property that we want. So I'm going to talk about how we can build this today, but it's also, I'm going to highlight that this is a possible solution. I think it's a solution that a lot of people are like, yeah, it's great, let's use an encrypted mempool. But there are some drawbacks and some big open questions that we need to answer. So I'll kind of talk about those as well. All right, yeah, so encrypted mempools are great, but how are they actually going to work? So here's the basic process of what we're going to do to have an encrypted transaction, sequence it, and then decrypt it afterwards. So first, we're going to have a secret key that's generated. It's going to be split into some number of n shares, such that we can recover it with k shares. The transaction is going to be encrypted. We are then going to sequence and finalize the encrypted transaction. At this point, after the transaction is finalized, it can no longer change. Then we'll gather our k key shares and decrypt the transaction. So it's a pretty simple process. But I'd say these two parts right here are the most difficult parts because they require some sort of coordination. And this is where we can use the really good, we can use the coordination layer of the consensus protocol that we're already using to sequence transactions. We can use that coordination to do the coordination of sharing keys. Yeah, so the key idea is let's use the sequencer's consensus protocol to coordinate sharing our threshold keys, and therefore we can reuse a lot of the logic and we can reduce the latency of decrypting the transactions at the end. All right, so now I'm just going to go through like the general process of how this is going to work. So, oh, whoops, skipped. Okay, so first we're going to generate the secret key, n shares, like I talked about. And then we're going to encrypt the transaction. We have multiple transactions here. We are going to have it sequenced by the network. This is going to be finalized, and you'll notice here it's like in a different order. And then finally, we'll gather our k key shares, and then we have our decrypted transactions that can then be executed on any sort of VM or rollup, etc. So a nice thing about this is, if you'll notice, is that by the time we decrypt these transactions down here, that's when they get executed. So we can do this whole encrypted pipeline for any rollup, for any VM, et cetera, because all of this happens before it actually gets pushed to the rollup. And then one thing you'll notice here are that these two steps here are really similar in the protocol. So actually, what we can do is pipeline it. This is actually similar to what was in the talk about Mr. SETI. So you can pipeline this. So instead of having two separate rounds where you have to say, okay, I'm sequencing the transactions, and then I have to go through consensus to get all of the keys. You can pipeline it, and you can overlay it. So basically, in this first round up here, when you're sequencing transactions 4, 5, and 6, you're actually decrypting transactions 1, 2, and 3. And in this way, you cut your latency in half. And this is a really common distributed systems trick, is you pipeline things. So the big part here is that we reuse the sequencer logic to do the coordination among parties. And this kind of seems like a really obvious thing, right? Like obviously the consensus protocol is doing some sort of coordination, so why wouldn't you reuse it? But I would actually say it's not something that's actually used in practice a lot. Some of the current protocols are usually built on, they use a consensus protocol to sequence, and then they have a completely separate protocol that they're using to do this coordination of sharing keys. So with this, we can get, really good latency. Okay, so let's go back to our process and talk about it. So I went through this whole process. But you may have noticed I was very generic. I was very generic over what this secret key is and how it's split and how we recombine these key shares. And so this is what I want to talk about. So, all right, we have this secret key and we have n key shares. And so I think we have a couple of options that we can do. And I'll preface this with I'm actually not a cryptographer. Mostly I work on consensus, but hopefully I can relay the important information. So how can we split this key? So we want to split the key because we want to, make it difficult for people to recover the decryption key before it's finalized, because if people can decrypt our transaction, they can front run us. So we have one option. We can do something like Shamir secret sharing. And maybe this is a possible way that could look. So the user generates a secret key, and you break it into n shares. The user encrypts each share with the validator's public keys, and then they submit it to consensus. Because each share is encrypted with the validator's public keys, only the validator will be able to decrypt them. So this is a possibility. We can also use threshold encryption, which is a different possibility. We can run some sort of DKG protocol every epoch, where an epoch is sufficiently long enough. We can publish the threshold key somewhere. The user uses the public key to encrypt their transactions, and then after the transactions are finalized, you run the threshold decryption protocol, again, using the sequencing protocol already in place. And just to note that these two options and also more options are discussed in these papers that I've linked below. So a quick note, there's actually a lot more advanced things you can do here. You could use something like AvidM, you could use maybe a more complex threshold encryption scheme. But the point is that these two options kind of capture, I think, the questions and the open research that we still need to do about using an encrypted mempool. So let's look at some of the trade-offs of doing this. So if you do like a naive Shamir secret sharing, you can't reuse the key. So once you combine all of the keys, your key is public. You can't reuse it to encrypt something else. So that means that every transaction or every single block, you need to regenerate something new, and that kind of has overhead. You need to ensure that any subset k out of n can recover the secret. So if you're using a Byzantine fault tolerant consensus mechanism, the assumption is that you have less than or roughly 1/3 or less of malicious parties. Well, something you need to make sure is that any subset of honest parties can recover the key, not just one particular subset. So this is where you might use verifiable secret sharing over just plain Shamir secret sharing. Second of all, it's potentially wasteful. So if you'll notice in option 1, if a user is sending a really small transaction that's only a couple of kilobytes, they need to also send all of these encrypted shares around, and that's really wasteful, and it's going to cost the user extra data fees in the network, which isn't great. In this design, it's also just a bunch of extra effort on the user's part. Maybe we have some sort of trusted third party that does it for the user, but that's not really good either. So here's some of the problems with option 1. But okay, let's look for option 2. It's probably impractical to run a DKG protocol for each transaction or block, especially if we're trying to scale to thousands of nodes. So this means that we need to reuse the key. But with threshold encryption, that should be fine because you're not actually revealing the private key. But this leads to the biggest question of all, which is, what about collusion? So I think that encrypted mempools are really, really great, but they have this big open question about what about collusion. So a lot of, for example, the threshold encryption schemes are, they can tolerate maybe up to 1/4, malicious parties maybe up to 1/3. But the problem is that what if people are incentivized to collude? And this opens the question, what do we think actually constitutes an honest party? Because if you consider it, you could say, well, an honest party will not collude. But if an honest party does collude, they can decrypt this transaction. They can extract a bunch of MEV from it. MEV tends to be pretty spiky, but there have been cases where MEV is like quite a lot. And so it very well might be worth it for otherwise honest validators to participate in this collusion. So this is kind of a really big open question. How do we handle this? Well, there's a few thoughts. So one, you might say, well, of course, why don't we use threshold encryption? One reason maybe to use a more naive solution, such as secret sharing, would be you're regenerating the key all the time. If you have really fast consensus, if you're coming to consensus within 1 second, well, maybe that's fast enough that realistically it's too fast for people to collude. Whether or not that's an accurate assumption to make is open for debate, but maybe that's an argument you might make. With threshold encryption, though, since you're only regenerating the key every epoch, and supposedly the epoch is going to be sufficiently long, you actually have plenty of time for parties to collude. So for example, let's say you start an epoch, you generate your new threshold key. That threshold key is good for the next 32 blocks, let's say. Well, someone who submits a transaction, really early on, the network can wait to sequence it and first collude all of their keys, decrypt it, and then build a block that front runs them. Okay, so I think that this is the big open question of this talk, is like, how do we handle this? There are definitely more complex cryptographic protocols that we can use, although I think none of the ones that I have seen have really completely solved this. So we want something that's collusion resistant, which I think goes beyond just the cryptographic protocol. We need to think about incentives. So any protocol that's going to have any sort of honest majority assumption is not going to be collusion resistant if we are under the assumption that parties will act rationally rather than honestly. We also don't want something that relies on users being online. So a naive solution might be, well, okay, the user encrypts their transaction, and then after it's sequenced, the user just sends everybody the decrypt key. But that's not very good for relying that users are online. Maybe this could work if the user has some sort of trusted third party that does this for them, but then again, we're introducing this trusted third party that we ideally don't want to involve. So what to do? To be really honest, I don't have an answer for this. I think that this is an open question, and I'd really like to hear people's thoughts, because I think encrypted mempools are great, but I think that this is like the one really big question that people are not talking about, is collusion. So that's the main part of the talk. But I just want to run through some other quick considerations about encrypted mempools that I think that we should think about. So, okay, we have this problem with front running, and we think that we can use encrypted mempools to solve it. But what about spam? So MEV is very profitable, specifically the top of the block, so how you do like arbitrage, etc. If you do encrypted transactions and you require that all transactions are encrypted, well, maybe you just get a bunch of people spamming because they're hoping to be that first transaction in the block. So that's really not good for the network. It could also cause network congestion. You have spam, it's going to cause network congestion because you have a bunch of stuff that's not actually valuable. That's also not good. Well, I would say that unlike the collusion issue, I think we actually have some solutions to this. So spam can be handled with an appropriate fee mechanism, but I think mainly it can be handled by plain text top of block auctions. So if you're not really familiar with the MEV space, the top of the block is the most valuable because that's where you can do most of your MEV. So just allow those transactions to be plain text. They don't need to be encrypted because they're going to be executed first. And the whole point of those transactions is that they are front-running other transactions. So just let those transactions be in a separate part of the block, and the encrypted transactions can be elsewhere. Second of all, you can use a sequencing platform that's designed for really, really high throughput. So this would be an example of where you'd want to use maybe an external consensus mechanism, such as like a DAG like we saw earlier, or Espresso that has really high throughput, so we can handle any sort of spam that comes in the network. Okay, well then you have another thing here where it's like, well, the encryption adds extra latency to the protocol. Naively, this encryption is going to add 2 times, or it's going to double the latency of the protocol because you have the time it takes to sequence, and then you have to go through consensus again to actually decrypt it, and that's not ideal. And to that, I'd say, well, yes, you can't avoid that. Obviously, you're adding an extra round to decrypt something. You can't avoid that that's going to have extra latency, and that's just like a trade-off that you make when you choose to submit an encrypted transaction. But the good thing is that if you do this in the way that I described, it doesn't add any extra latency for plain text transactions. And not all transactions need to be encrypted. If I am just doing a simple swap with like someone I know, I don't need to encrypt that because that cannot be front run. So in this case, you're only adding extra latency to transactions that actively choose encryption and not other transactions. And then finally, you could say, well, encrypted transactions have to pay high fees. Why do they have to pay high fees? Because you can't extract MEV from them. So you say, well, if a builder is coming, have an encrypted transaction that they can't get money off of, they're just going to charge more to include it. And I think we can actually deal with this by just not having congestion in the network. So if we have a network that can handle all of the traffic that we need, and you don't have congestion, builders will include any transaction they can. The more transactions they include, the more fees that they get. So they actually will not charge extra for encrypted transactions so long as the network is not congested. OK, so this is a fairly short talk, but I just want to give a couple of takeaways, are that encrypted transactions can prevent front running and improve censorship resistance. These are really, really good properties. We can reuse consensus and sequencer logic to coordinate key sharing and decryption. We can pipeline it for even better throughput, and this is really great. This makes this whole system really robust, and we have good latency, et cetera. But we have the huge question of what do we do about colluding parties? So I'd say there's two parts to this question. The one is, do we actually consider this a problem? I have seen some people argue that yes, people could collude, but that's not part of being an honest validator, so we don't have to worry about it. Or is this something that we should actually worry about? If we do need to worry about it, we have to really think hard about how we're doing this threshold encryption cryptography. And then finally, encrypted transactions have different economic incentives than plain text transactions, and that's actually totally fine, because we can design protocols that allow both of them to coexist and for encrypted transactions and plain text transactions to not actually affect each other. And we can do that through using a top-of-block auction, designs, like I said, et cetera. So really quick talk. I would really love it if anybody had any opinions on how to solve this collusion thing, or if you have any opinions on if that's not a problem at all. I'd be really interested in that. All right, so thank you. That's it.
Thank you, Ellie. Anyone wants to chime in?
What's a verifiable Mamiya secret sharing, and how does it
Great. Thank you so much, Ellie. So, thank you everyone for staying with us so long. This concludes the first edition of Encrypt, which we're very excited to have had. We are planning to have many more. And so please stay tuned, and thank you for all our speakers, all our co-hosts and sponsors. And it was a real pleasure to have you all here today. So thank you very much. There's like I think drinks and stuff and like happy hour networking, whatever. So feel free to, yeah. Oh, Omer, you want to say something? Oh, that's okay. Thank you.